The tech industry is going through the dominance of artificial intelligence. There are numerous AI products out there which are making an impact on each and every aspect of human life. Everyone is talking about how disruptive these tools are, but have you ever wondered how these tools are made? What technologies is driving them to produce such an amazing products? Well, the answer to that question will be machine learning. Machine learning is like giving machines the power to learn and improve from experience without being explicitly programmed. The field is everywhere, from voice assistants on your phones to recommendation systems on streaming platforms like Netflix, or even the logical units running behind AI tools such as ChatGPT, Midjourney, and DALL-E. Currently, since the AI industry is dominating the IT sector, there is a huge demand for professionals who understand machine learning and can integrate ML into products and services companies offer. According to Glassdoor, even the beginners in the field earn an average salary of 10 lakh rupees. If these facts excite you, then you must discover machine learning as a career option. Today, with this extensive live session, we are going to provide you guys with a fundamental overview of machine learning. Before we begin with that, I would like to request you guys to enable both the subscribe button and the bell icon for our Intellipaat's YouTube channel. Having said that, let me tell you about the agenda for today's session. We will begin the session on a friendly note by looking into what is machine learning. Then we will get you introduced to data science and ML, different types of data, types of machine learning, algorithms, etc. Later, we will be going through classification algorithmic setting known as linear regression algorithm. Here, we will learn what is multiple linear regression, how to prepare data, how to train the model, advantages of linear regression, and assumptions of regression line. After that, we will cover logistic regression, sigmoid function, what is best S-curve, and also model training with logistic regression. We will also cover what is confusion matrix, what is decision tree algorithm, and also what is Occam's razor. Finally, we will also take you through the most commonly asked machine learning interview questions and answers. I hope I have made myself clear with the agenda, so let's dive directly into the session.
Machine learning was just considered to be just a niche subfield of computer science, but technology giants have been using it for years. Machine learning algorithms power Walmart product recommendations, search pricing at Uber, fraud detection at top financial institutions, content that Twitter, LinkedIn, Facebook, and Twitter display on social media feeds or Google Maps. Machine learning products are being used daily, perhaps without any realization. A report from TMR mentions that machine learning is expected to grow from $1.07 billion in 2016 to $19.9 billion by the end of 2025. Machine learning is a branch of artificial intelligence and computer science, which focuses on the use of data and algorithms to imitate the way the humans learn and hence gradually improves their accuracy. How machine learning works? Step 1. A decision process. In general, machine learning algorithms are used to make a prediction or classification. Based on some input data, which can be labeled or unlabeled, your algorithm will produce an estimate about a pattern in the data. Step 2. An error function. An error function serves to evaluate the prediction of the model. If there are known examples, an error function can make a comparison to assess the accuracy of the model. Step 3. A model optimization process. If the model can fit better to the data points in the training set, then weights are adjusted to reduce the disparity between the known examples and the model estimate. There are 3 methods of machine learning. First one is supervised learning. In this type of learning, algorithms build a mathematical model of a set of data that contains both the input and the desired outputs. The data is known as training data and consists of set of training examples. Each training example has one or more inputs and the desired output, also known as supervisory signal. Second method is called unsupervised learning. This method of learning algorithm take a set of data that contains only inputs and find structure in the data, like grouping or clustering of data points. The algorithms therefore learn from test data that has not been labeled, classified or categorized. Instead of responding to feedback, unsupervised learning algorithms identify commonalities in the data and react based on the presence or absence of such commonalities in each new piece of data. Third type of learning is called as semi-supervised learning. This falls between unsupervised learning and supervised learning. During training, it uses smaller labeled dataset to guide classifications and features extraction from a larger and unlabeled datasets. Machine learning is used in day-to-day life, like speech recognition, customer service, computer vision, automated stock trading, discovering data trends, and lot more.
So now we will be moving forward to the machine learning topic. So you must have heard about the theoretical part of that we predict this, we make recommendation system, we make the object detection, face detection, a lot of things. We predict the future outcome. You have heard about the theoretical part of what we do in data science. But I'm going to show you exactly what that means, what we are talking about when we say that we do this and we do this, how that is done. So we'll be talking about that. Let's get started. But one suggestion I want to give you, if you are investing your money and time into something, you should never go through a hype. There's a hype around data science and machine learning, right? And a lot of people are talking about it. Everywhere you see the advertisements are there for different courses and everything. But don't ever invest your money and time before understanding is it even for you or not.
Let's have a quick quiz question, guys. And the question is, what is the primary goal of supervised learning? And your options are minimize model complexity, discover patterns in unlabeled data, making predictions based on labeled data, or generate new data samples. Please mention your answers in the comment section below.
Because what I have seen in data science, a lot of people just join for the hype. They put their money, but they just get bored with it, and or it has so much mathematics that they are not able to cope up with it, and they leave. Their time is wasted, money is wasted, everything. Now, what we have starting from here, why do we have data science in today's time is the main topic of discussion. Why do we have data science? Why everyone is running towards data science? What is so good about it? If you think about around before, yes, if you talk about before 2014 or 2013, or if you talk about any time before 2011, 2010, no one has heard data science terminology, or there would be very few experts in the field of this, in the IT field. They might have heard about something machine learning is there, something like data science is there, but that were the number of very few people were there who have heard about this terminology. But if you take a look from 2014 in India, if you talk about, starting from 2014, people started to discuss data science more and more. It started to come into picture. People started getting into data science roles. Companies started to hire for these data science roles. But it was not there like 10 years ago, if you talk about. Not so much. So what happened suddenly that it came into the industry and it became one of the most powerful things that you have today in the field of IT technology. What was so good about it? So actually one very important thing happened is the type of data that we started to get. What happened is there's something which is types of data.
Just a quick info, guys. Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
Now, what is these types of data? There are these two broad type of data. In statistics, I discussed about you have numerical data, categorical, that's a different thing. But in a very broad perspective, if you don't go into details, you have two type of data mainly that we see in the industry. One is a structured data One is a structured data and one we have unstructured data. Unstructured data. These two things are there. What is a structured data? Structured data is basically a data which is in tabular form. Tabular form means what? When you have rows and columns, any data that you see where rows and columns are there. Like CSV files we were working on, we had rows, we had columns. If you see databases, anyone who has seen databases, you would see there is also the tabular form of data. Rows are there, columns are there. So if a data has a structure in the form of rows and columns, that is called a structured data. Right? So that is what you see. Now, what is unstructured data? What do you think would be unstructured data? What would be unstructured data? Unstructured data is something which does not have a form of a tables, which does not have the rows and columns. So what would be a data which does not have rows and columns? We have images, right? Videos. We have text. The text files, like messages you see on the internet, on Instagram, the captions you're writing, the comments you're writing, those text, right? Images, videos, text, and audio files, the signals which are there, yes. Any audio signals that you see. So if you talk about something, images, videos, can you put images, videos, text, audio in the table and row format? Not possible. So we can't put these data into row and column format. That is why they are called unstructured data. They don't have a form. They are just some type of data. So the tabular form of data and unstructured data, we have these two broad type of data that you're going to see in data science. You will be using both of them, but what basically triggered the data science is this unstructured data. After year 2010, if you see, in year 2010, actually Instagram was launched, the platform Instagram. And when Instagram launched in 2010, before that Facebook was existing. There was a platform Orkut, if any one of you remember. Some platforms already existed before that also, before 2010. But they were not being used a lot. But what happened when Instagram started for the first time, it made other platforms also very popular. When people started using Instagram, they also started to use Facebook, Orkut, and all the other platforms which were existed for social media. They started using it very frequently. And if you talk about 2014 or 2013 like that, in India, if you talk about specifically in 2014, something happened. Our internet became very cheap. Okay, if you remember for Geo, it came in 2014, and suddenly we got a very cheap internet. That was very expensive, and after year 2014, it became very cheap. Everyone was able to access a lot of video. They were able to upload a lot of images, download a lot of things, comment on that. So they started using all the social media a lot. That same thing happened around the worldwide also. The internet started to become more accessible throughout the world in the other countries also around that time. So what happened suddenly, the number of unstructured data started to increase exponentially. And today, the thing about this unstructured data is that we have 80% of all the data which is available today with anyone, any company is collecting the data, anyone who is collecting the data. Out of 100%, 80% of this data is unstructured, is in the form of either images, videos, text, audio, or some type of that unstructured data, 80%. Now, there was no tool instead of data science that can study this 80% data or that can extract any information out of this 80% data. Before data science, people were using Excel very frequently to work on this structured data. Excel can work on structured data very properly and it can give you a lot of information. But there is no other tool apart from data science which can study this much data. Now, suppose if companies have not adopted or they have not created this field of data science that we see today, Would they be able to use this 80% for their advantage? No. 80% of that data will be just going to waste. What companies do with this data? They study the pattern, they study what is uh, what is something being shown in the data, how customers are behaving, what they are liking, what they are not liking, what they want to see more. So companies study this data to find out patterns of someone's behavior, of something happening in the real world. Once they understand what is happening in the real world, they can launch a product related to that. They can improve the product related to that, but they should be able to study this data. Got it? They should be able to study this data, then only they can launch a product according to that. Any company. So every company started to see that they are getting 80% of the data on their servers, which are all in the unstructured format. And without data science, they're able to only study that this 20% of that. So it was a very important case, or it was very important to get something which can work with this unstructured data. That is where data science came. And today you see so much of data that we see today that has been created in the last 2 to 3 years. Got it? Whatever amount of data you see today, you can say almost all of that is created in the last 3 to 4 years. That is what the amount of growth of the data is. That is the type of data. So there, our data science came into the picture. Now you know data science is there. But what exactly do we do in data science? What are the processes to follow to make a complete project from the start to the end? For that, you need to understand components of data science. Components of data science. Project, you can say. I was talking about a few steps yesterday, if you remember. Those steps are actually going to get you the components of data science. Let's see. So the first one, the very first thing you do to make a data science project is, problem statement. Understanding the problem statement. Never forget this step. If you mess up this step, if you don't understand the problem statement properly, whatever you do after that does not matter at all. Always remember this one thing. This might seem like a very simple thing, understanding the problem statement. But if you mess up this point, then whatever you do, any analysis you do, any reading of the data you do, any machine learning that you apply is just going to be waste, and your project will be thrown away. It will not be used at all. It does not matter you've invested 6 months of your time to do it or 1 year, it will just be thrown away. Now, every project that you make in this data science field is not going to be accepted to be launched into real world. Why it is not accepted? Because a lot of data science projects are experimental projects. The company try to see, they take a data and they try to do some experiment. Are we able to get something out of this or not? Sometimes you get something very interesting. Sometimes you get the answers which already the company knows. So all of your projects will not be taken into the real world. They will not be used. But your task is to do that experimentation. That process is very interesting for anyone. Right? That is why understanding the problem statement is of a lot of importance. Why? Because everything you do after that is dependent upon this problem statement. What you do next is collection of the data. You go ahead and collect the data. So you don't collect the data before knowing the problem statement. Before knowing the problem statement, if you're trying to collect the data, then you will not collect the correct data, which is actually going to help you. So if someone has told you that we have to solve a credit card fraud detection, that's a very small statement someone has said to you. If you just hear this term, okay, credit card fraud detection we have to do, and we are going into the further step. So that is not going to help you much. What you have to do, you have to see which company is telling you to do that? Is that company from a banking sector, or is that company from e-commerce sector? E-commerce also faces fraud, credit card fraud, because if you go to Amazon, some people purchase the product on Amazon with credit card. So there a fraud can happen. If you talk about bank, if I go to a banking website, or my credit card can be hacked from the bank site. So different places a fraud can happen. Now you have to understand that which company is facing this problem. A banking sector is facing this problem, or an e-commerce, or something other. Dependent upon that, you will be collecting specific data for a fraud. If a banking sector is facing this problem, why would you collect a e-commerce credit card fraud details? That is not something to be done. After collecting the data, you will have the next step, which is called the cleaning the data, right? What is the next thing? Processing and cleaning the data. What is this processing and cleaning the data? I have told you that there are two packages which are used for that. Yesterday also I discussed about it. So one is our NumPy and Pandas. Okay, and how you have to process the data, how you have to clean the data, that is also dependent upon the problem state. Like if for a particular problem statement, you should do this cleaning and not this cleaning. That becomes very important to understand in the perspective of a problem statement. After that, what we do, we explore and visualize the data. And visualize the data. This is step number 4. So for visualization, what we have seen some of the things about it. Basically, we try to get relationships in the data, as I have told yesterday also. These 4 steps that you're seeing. Step number 1, understanding the problem statement, collecting the data, processing and cleaning the data, and explore and visualize the data. These 4 steps is what? When you collect these 4 steps, you have basically done data analysis. This is what data analysis is. You collect the data, you clean the data, and you analyze it. That what are the patterns in it, how my data is behaving, what kind of correlations exist. This type of information, if you're able to visualize, that is data analysis. After you do data analysis, what is the next thing you will do? With data analysis, we basically study the past data. What happened in the past is what the analysis gives us. After you have understood the past, you now want to predict the future. So for predicting the future, you come to the step number 5, where you apply the machine learning algorithm. Okay, apply the machine learning techniques. That is step number 5. So as you move forward to step number 5, now you can predict the future outcome according to the past data. So for predicting the future, you should always have a past data. Without the past data, you cannot predict the future outcome. Not possible. So we have done data collection, we have understood what are the patterns, and according to that, you will be able to understand which technique you should exactly use. A lot of machine learning techniques are there. Techniques basically mean algorithms are there. I'll be explaining that to you. And you will be making a future prediction. Now, when you make a future prediction by taking any ML technique, will you be able to make 100% correct prediction ever? Can an algorithm make 100% prediction? Of course not. No one can make a 100% prediction. It is not possible. What is going to happen in future? You can make a prediction about that. You can be close to what is going to happen in future, but you cannot predict exactly 100% that this is going to happen. Right? Not sure. So what happens is, whenever you apply a machine learning to a data, sometimes you will get very low accuracy, sometimes you will get a high accuracy. So let's take, you have taken one data and you got only 80% accuracy. You got some data, you get here 92% accurate. You take a data on that, you got only 62% accurate. Why you get different accuracy, why sometime high, why sometime low, we will be talking about all of that in much detail. But you will not be getting a proper accuracy. You cannot predict 100% accurately. 100% you're never going to see in industry, not at all, ever. but you can get as closer to 100% as possible. So how do we do that? We need to test the performance of the model. Okay, test the performance of the model. What is this model? I will talk to you about. But whenever you apply machine learning to a data, it makes something called as model, with which it does the future prediction. So whenever you have made a model of a machine learning model, basically, what it will do some prediction. If it has done a prediction, how do you know it is accurate? So you have to test the performance of that model first, that how accurate it is. Then you can say, okay, the answer it has given is only 80% accurate. It might be 20% wrong, right? Yes, of course, we will be testing performance with the past data, So if you have tested the performance of the model, what we will do, let's suppose you got 80% accuracy only. But what you wanted to do, you want that at least 90% accuracy should be there. Then only it is helpful for me. If it is showing 80% accuracy, it is not helpful for me. So what you do now, you tune the performance of that model. Or you can say you tune ML model. Tune means you start to make your result better. This is what you have got when you applied a technique, a machine learning technique, and you give it a data. It by default, it gave this much accuracy. It was only able to give an prediction with 80% accuracy. But what you want is, you know, that if I have to use this solution in industry, or if I have to use this solution in the real world, I should get at least 90% accuracy. Below that, it is not going to be helpful in the real world. So what you do then, you try to tune the ML model. Tuning means take a certain accuracy and start to make it better over time. That is what you need to do. And that is where the tuning process comes. So I'll explain you how to do tuning also. A lot of techniques are there for that. And what would be the step number 8? After you have tuned, and sometime when you're tuning the model, sometime you will get the desired accuracy which you're looking for. Sometime you don't get it. If you are looking for 90%, sometime you will be able to achieve 90% accuracy. But sometime on some data, you can simply not get it. Not possible. Whatever you do, whatever techniques you know, you try all of that. But after that also, it will not give you the desired accuracy. So then you have to take a decision. Do you want to still use it in the real world, or do you want to remove that, or just close this experimentation we have done, not use it at all, right? So that also happens. The last one is present the result. Whatever we have got, the prediction we have done, the tuning and everything we have done. So last is we present the result. So we were working on this project and we went through this, and we identified that these are the things that we see when a fraud has to happen. So when a fraud has to happen, it has been observed that these things happen. That is what your presentation of the result. Now, we are going to change the technique if one is not giving accuracy. But even after changing the ML technique, a lot of other techniques are there. If you tried all of them, whichever you thought I should try, even after that, sometime you will not get your desired accuracy. That happens because it's a data. You don't have any control on the data. If it is able to give you desired accuracy, good. If it is not, then you cannot do anything about that. You can only wait to collect more data, to collect wide variety of data. You can just do that at time. Let's see. This is one thing. I told you that it is data, and data sometimes can give you accuracy, cannot give you that much accuracy. Maybe you don't have enough amount of data. That is one of the very frequent problems that we see, that we don't have the specific data which is required for that task, or we don't have enough data. Now, what is this data science? Data science is just a combination of two things. One is machine learning, and one is data analysis. When you have this data analysis, that is basically a study of the past data. And when you combine it with machine learning, what do you get? You get that we call as data science. So if you are studying data science, you will be able to get job in both the roles, as a data analyst also, as a machine learning engineer also. And I think yesterday or day before yesterday, we were talking about that the gap between data analysis and the data scientist is reducing, because this data analysts also have to have the knowledge of machine learning in today's time to be able to do their analysis properly. Earlier, they don't had to know machine learning at all. They just had to work with Excel, SQL, and Tableau, these kind of things. But now they need to have both of them. So data scientists, data analysts are quite of becoming same in today's time. Okay. So now let us understand the process of prediction. I've talked about that we take a data, we study that data, and we make a future prediction. How that exactly happens? So you study the past data, as I told you. If you don't know the past, if you don't know how something happened in the past, you will not be able to predict what is going to happen in the future. And that goes for every industry, every use case that you're going to work in data science, for everything. So your machine learning is something, machine learning is what? It is basically a way to make a prediction by using some technique. So whenever you have a technique that might that does not know about your data, a machine learning technique is just a written algorithm, you can say a mathematical algorithm that does not know what your data is. So you have to teach that machine learning algorithm that this is my data, and in this data you can see what has happened in the past. And once you have studied the patterns from this data, you can now predict the future outcome. That is what we do in machine learning. So how we teach the past data to our machine learning algorithm? Let's see. So an example we are going to take, that example will be for, let's see, we have a heart disease prediction. Heart disease prediction. Using this, we will understand the process of that machine. So what do we have? How do we solve this problem? Basically, we'll have a data for using that. What kind of data we are going to have? Let's take some data. Now, for a person, for any machine learning algorithm to identify that this person is going to have heart disease in the future, what you need to do, you need to have the past. You need to have the medical conditions of a person. Let's say what data you will be collecting in this case. One, you can collect the age of the patient. One, you can collect, let's say, the chest pain of a patient. One, you can collect the sugar level of that patient. Maybe it is helpful, maybe it is not. I don't know that, but I will be collecting the data which we have. And we might collect blood pressure. No, food habits are too broad. You need to have something specific. Like they have acidity issue or something like that. That will be much better. Yes, cholesterol level. Perfect. Cholesterol level. Like this, you can think of multiple health related conditions. How much is their sugar level, blood pressure, cholesterol level, or chest pain level? What kind of things do we have? So suppose this much is the medical conditions of the patient. And at the end, what you will have, at the end, yes, this is the past cases of the attack we are studying about. At the end, we know the output. So this is any data you see, it is about the past. So if you are collecting this information, it is for the patient who have come to the hospital. Some of them had heart disease, some of them did not have heart disease. So what we have to identify now, that a person who did not have heart disease, what were their medical conditions? And how they are different from the person who had the heart disease in the previous case. So let's suppose I have talked to some patients, and the patient number one I talked to was having age 32. Let's say chest pain is, I'm talking about in levels, not in the magnitude. I'm talking about, let's say, from level 1 to level 5, the chest pain happens. It is the medical terminology. Chest pain level 1 means it is very low, not something to be worried about. Chest pain 5 means in 1 month, in 30 days, around 20 to 22 days, a person faces a chest pain that is going to be level 5. That chest pain is very frequent. So let's say the person is having age 32 and chest pain level 5. Now, what is their sugar level? Sugar level, let's suppose, is 110. I don't know what is the actual sugar level. Just see the numbers and you'll understand. Let's say they have a low blood pressure. And let's say they have a blood cholesterol level 45, just as an idea. And now output is what? This person who has come to the hospital in the past, and we talked to them when they came into the hospital for a complaint, for checking whether they have a heart disease or not, or whether they are going to have heart disease or not. What we observed that when this patient came to the hospital, he actually had a heart disease according to these conditions. So we'll say yes for this patient. For patient number 2, let's say a few cases I'm taking, 35, say 27, 45, and 38. These are the age of the patient. Say second one faces chest pain level 1, level 3, level 2, level 4. And we have sugar level, suppose 78, and suppose 130, 66, and now we have 98. These are the sugar levels. And the blood pressure level, let's say low, high, low, low, high. And cholesterol level, I can just mention some numbers like 45, 65, 73, 42, and 59. Just basic numbers. Now, the first person had yes, second person no, third person also no. And suppose we have yes and yes. This is an example of the past data. And how you can create a past data, you can just go to some hospitals, some medical institutions. You can ask for the data from them. If they are ready to share, they will share it with you. If they're not ready to share this data, then they might encode in some format and then share it with you directly. So you can have a lot of things. This is just an example of the things that we have taken. Now, what we have from age to the cholesterol column, this much. What are these? These are your input data. And the last one is your output data. So what your machine learning will be understanding that if these inputs are given, what I have to predict in the future, that is what it has to learn. Right? So we have the output and input. This is just an example I've taken. Let us see what we are going to. Suppose, so this data you're going to give to a machine learning algorithm that learn it. Okay, learn that when someone has chest pain, what they have, when someone has this much sugar level, blood pressure level, cholesterol level, with a certain medical condition, what a patient is going to have, or what patient had in the future, we are actually teaching the machine learning that according to this much chest level, this much sugar level, in the past, we have seen that that person had heart disease. Similarly, you're teaching that according to this much chest level, this much sugar level, this much cholesterol level, the patient did not have heart disease. That is what we have seen in the past. This is all past data. And your machine learning will do what? It will learn this pattern. It will try to understand this pattern. When something is high, when something is low, what causes the heart disease? It will learn according to these examples which is given to you. These are 5 patients of the past. It will learn. Now, after learning what it does, what our machine learning algorithm does after learning, let's suppose we have a new patient that comes up into our hospital. A new patient comes up. And when a new patient comes up, do you know whether they are going to have heart disease or not? By looking at them? No, we don't know whether they have a heart disease or not. What we do now? We have a machine learning algorithm created for us. We have trained our machine learning algorithm and it has understood the pattern. So if a new patient comes up, I don't know the output of that. I don't know whether it will be no or whether it will be yes for a future patient. But I can collect these all data, right? I can ask the patient, what is your age? What is your chest pain? We can measure that using some devices. We can measure the sugar level, blood pressure level, cholesterol level for a patient. So all of these inputs are there. We can calculate that. We can collect that for a future patient, but I don't know what will be the output. That is what our machine learning model has to predict. So what will we do? For a future patient, so a future patient comes, let's say their age is 33. Their chest pain level is 4. Their sugar level is, let's say, 125. Their blood pressure level is this. And now the cholesterol level. See, all the input are there: age, chest pain, sugar, blood pressure, and cholesterol. I'm collecting the data according to that. 5 inputs I have to collect. I have collected this for a new patient, future patient. I will show this to now my machine learning algorithm who has learned the past data. I will show this data to that machine learning. Take a look at this data. What do you think? Is this patient going to have heart disease according to what you have learned in the past? So they will give 2 answers. Only 2 options they have. They will either say yes or they will say no. Only 2 options they have. Right? So they might be correct, they might not be correct. They are just making a prediction. They are just making a future prediction. So they might be correct, they might not be correct. We need to know how much is the possibility that they are correct or not. We need to find that out. So what we will do in this case to find out in this whether they are correct or not, whatever past data we have, we take some example of the past data to train the algorithm. I'll be talking about that. I'll be explaining how things happen. But for now, it has only 2 options. Either it can say yes or it can say no. Let's suppose it has predicted 80 patients correctly out of 100. 80 predicted correctly and 20 of them predicted incorrectly. Right? If 100 patients were taken, if 100 future patients were taken, 80 of them were predicted correctly and 20 not predicted correctly by our machine learning algorithm. Correctly means those who had heart disease were predicted as having heart disease. Those who were not going to have heart disease were predicted as a normal case. They are not going to suffer. Incorrectly means if they were supposed to have heart disease, my model said that they are okay. That's an incorrect prediction. So now 80 correctly done, 20 correctly done. So the performance of the model will be what? Performance of our trained ML model will be what? It will be 80 out of 100. 80 correct predictions were made out of 100. So then we will say that our performance of the model is 80%. It's a very basic idea I'm giving for now. I'll be going into depth and telling you about all the technical details. But at this point, 80% cases were predicted correctly. So our performance of the model will be obviously 80%. Now, what do you think? Is this much accuracy good enough for this use case that I'm talking about? Do you think this is good enough performance of the model or this is very bad? So see, whenever accuracy has to be seen, it is not seen that what is the percentage. Percentage does not matter at all. Yes, it matters to some extent, but percentage has to be seen according to the problem that you're solving. What is the problem I'm talking about? What is the use case that we are trying to solve? Is a medical related issue. And if a model is doing incorrect prediction, then there is a chance that that person might lose his life if you are doing incorrect prediction of something. If we say that this person is okay, but actually this person is suffering from heart disease. My model did incorrect prediction. So at the correct time, they will not get the correct, those, what I can say, medications, right? Correct medication could have been done at a good time. They would have been saved. But after 2 years, 3 years, they get to know that they had heart disease, but we had said they did not have heart disease. So after 2 years, the condition of that patient will become very critical and they might not be saved. So when you're talking about such critical cases in the industry, which is basically a medical case, so 80% is considered to be extremely bad prediction, extremely bad performance of the model. Why? Because you're still having a chance that 20% patients will be predicted wrong. So will you take a chance that we are making 80% correct prediction, but 20% patients we are predicting incorrectly? No one will take a chance on that. It is going to be a very bad solution. It is not good. It is very bad. What is the accepted performance in the medical industry? The accepted is going to be around 97%, 99%, or 99.2%, something like this. So what you will have to do, as I told you, you don't get 100% accuracy. But this is the beauty of machine learning, that you can do something which can take you closer to 100% accuracy. Because data, when you study data, and when you're studying a lot of data, you can get a higher accuracy like these. It is possible to achieve that, right? So you might not get 99.2, but you might get 97, 96, 95, something like that. But your chance of error should be as low as possible. And 80%, you will never move forward with a model which is giving you 80% accuracy. That's very bad, right? This is just one example. This is just one example. I'll be talking about the other use cases. There are a lot of use cases that you have in industry. So in some cases, you can work with 80%. In some cases, you need to have at least more than 95%. So industry decides, the use case decides how much percentage of the accuracy you need to have. So I was using a term called as model. What is that model exactly? See, you need to always remember machine learning algorithm. Whatever machine learning techniques we are going to study, they are nothing but they are algorithm. Algorithm is what? Algorithm is just mathematical formulas put together in such a way that they can do something very interesting. Mathematical formulas. Algorithm is simply mathematical formula. So any machine learning technique, it is just mathematical. A lot of formulas are there to create this algorithm. Nothing. No code is there, nothing like that. An algorithm, if you're talking about, it is just mathematical formula. So when you take an algorithm and you use a data set with that, an algorithm is just a normal mathematical formula that is just put somewhere, that is created somewhere. But if you give a data set to that machine learning algorithm to learn that data, got it? It will not know any data before. You take an algorithm, you show that this is the data set using which you have to learn the pattern and you have to predict the future outcome. So when you combine these two things together, then you get the result that you get is a machine learning model. What does this machine learning model do? Basically, this machine learning model is something trained on the data set to make your future prediction. So when I say model, it does not mean I'm talking about machine learning technique. I'm talking about a machine learning algorithm being applied on a data set. So then it creates a specific model, which is trained model, right? This one is trained and it is ready to be used in the real world at this point. This is what one of the things is. Now, so if this is clear, let's see what next you're going to have. All perfectly fine? Yes, great. Let's see now what. What is next now? So how is that process basically going through in machine learning when we talk about what is the process being followed? So in ML, some of you might have seen basically software development. Okay, software development. In software development, if something has to be made, what basically happens is you have some input data, right? You have some input data, you write code, and what do you get? You get output. This is in a very broad perspective. If I have to explain what happens in software development, some input data is given, and you write a code to get an output about something. But in machine learning, what happens differently is we don't write that code, right? We don't write that code because why we are not writing that code? That code I don't understand. That for this input data and to get this output, what should be the code written? I don't know that because I don't understand my input also very properly. That is where the ML comes in. So ML says that, okay, don't write the code. Just show me what is the input and what is the output. Show me those two things. I will figure out what is the code to be written to solve this problem. Just give me input and output. So input and output, you give it to whom? To an ML algorithm. You give it to what this ML algorithm is going to do. It will create a code. What will be the code? Not like the Python code we have seen. The code in this format is some mathematical function it is going to create. And if you take this mathematical function, using this function, you will be able to predict any future outcome. And at this point, your model is said to have learned the pattern. See, input and output given to ML algo, it will basically write some code, and that code is not like a Python or C++ code, as I told. It will be some function. I'll show you what that looks like, but it will be a mathematical formula kind of thing. Once we have got this function, then what we do next? We will be able to do predictions. So to do predictions, we basically should have the function created, and that will be done by machine learning algorithm. I don't have to do. So function it creates to understand the pattern, to represent a pattern in a mathematical formula format. Okay. One example of that, let me show you. So linear regression is also going to have a function for that. A function will be created, and it will be in the form of this. It will look something like this: beta naught plus beta 1 x. It will not be exactly this equation, beta naught plus beta 1 x, but it will be in the form of this. What do I mean by that? Let's say this beta naught and this beta 1, we have to find it out. But our equation will look like this. So let me show you one example of this equation. Suppose we have found out that this beta naught is 5. And suppose we have found out that beta 1 is 2.1 into x. So our equation will look in this format, but it will be exactly this, like this. So beta naught plus beta 1x, but beta naught will have a numerical value and beta 1 will have a numerical value. This numerical value can change, and it is going to change for data to data, but it will be in some format like this. Suppose I have given a data set and my linear regression is saying this. Suppose I'm talking about house price prediction. So in house price prediction, you have a lot of things, lot of inputs are there: number of rooms, number of floors, number of bathrooms, bedrooms, lot of things are there. So here, this is the formula create. So I have given input and output to the algorithm. Input and output means, so all the previous houses that has been created, you would know that suppose you have taken 1,000 houses. You went to United States and you just go to a city, let's say New York. And in New York, you have to do house price predictions for the houses which are being created new. Predicted how much will be the price so that you can purchase before and you can earn some profit. So you studied 100 houses. You went to 100 houses, you saw that this house had this much room, this much bathroom, this much bedroom, this much floor, and the price of these houses are this much, this much. So input is there and the prices are output. What do? You show that, okay, these are the houses which has these many rooms, these many bathrooms, and this is the price of that house that you show to the ML algorithm. What it will do, it will create a function for that to represent the pattern between the inputs and the output. And this pattern will look like this. What you will be able to do with this, let's suppose I'm just talking about number of rooms. And our algorithm has created some function like this. Suppose a new house you are taking a look at, and you have to predict how much should be the price of this house. And suppose that room has 4 houses. What will be the price of this house? How do you identify that? So this rooms, this is an input. Now, this future input you are going to give to this function. How that input will be given to this function? So this 4 will be taken at the place of x. So now your formula will be 5 plus 2.1 into this 4, into that number of 4. This is the input. So input, we place that into x. And what is something where, what is the value we'll get? 5 plus 4.8.4. Okay, what do we get now? 13.4. 13.4 is what? Suppose we are talking about these prices in $1 million. That's a very huge price. But this number that we are going to get, 13.4, is the predicted price of this house. For which house? For a new house which has room number 4 in New York City. For that, we have understood that it is going to have $13.4 million price. And this is the predicted price. How we have predicted it? So we gave an input and output, the past input and output to our algorithm. It created a function. And this function looks something like this. But this beta naught and beta 1, this is beta naught and beta 1 I've written into x. They will have some number. These numbers will change. We have to find it out. Will it be 5? Will it be 2.3? Will it be 1.8? It can be any number. But something like this you will get at the end, a number. So when you get this, you have an x. What is this x? X is the future input. So future input you give to this function, and what you will get a future prediction output. And this is going to be correct or not correct, but you have predicted this output. Are you all able to understand this flow? How a prediction is going to go through? We'll be talking about in depth a lot, but this is the basic idea how a prediction goes. Right, and this is what ML does. ML takes the past input and output, takes an ML algorithm that you have to decide which ML algorithm you will take, and it will create a function, and that function will be in this format. There will be different format. It is just one algorithm I'm talking about. So it will be created in this. You give input to that, and it will give you a predicted output. So everything happens mathematically. A prediction is not given like a random prediction. It goes through a mathematics. Because when you do something mathematically, you can be sure that it is not going to be wrong. Mathematics is never wrong. Now, so this is the basic idea. We will be doing that from Tuesday. We'll be going into depth of that. Okay, let's see what next. Next, we have some types of machine learning. Types of machine learning. What are the types of machine learning? There are basically 4 or 5 types of machine learning that you will see. One is called supervised learning. One is called unsupervised. Okay, supervised, unsupervised. Then you have reinforcement learning. And next we have transfer learning. Now what ML does, ML basically learns some pattern. So the learning of the pattern happens in different ways. These are the learning techniques. Inside every learning technique, in supervised, unsupervised, reinforcement, transfer learning, in all of these broad techniques that you see, there are a lot of algorithms inside. So for now, you have to only study these two. interviews, anything that you're going to do, you only have to study these two. The number third and number fourth is very advanced techniques. You don't get to do that in starting 2 to 3 years of your work as a data scientist. This is something which will be done by people who have around 5 years experience, 6 years experience, 7, 8, 10 years of experience. They work on reinforcement learning and transfer. A fresher is never going to work on these two techniques. A fresher, if you're joining as a fresher, you will be working on only supervised technique around 80 to 90% of the time. Maybe few cases, 10%, 5% time, you might do unsupervised learning, but 80 to 90% you will work on this supervised learning technique. What is this basically? We'll be talking more about that, but these are different type of problems come in the field, and these are the techniques to solve that problem. So most of that problem that you see in today's time, they fall under supervised learning. Then you have unsupervised learning, and reinforcement and transfer are very specific tasks. They are very expert based tasks. You don't see them a lot in the industry. So types of machine learning. What is supervised learning that I'm talking about? You need to focus on this supervised first. Supervised learning. What is this basically? So supervised learning is a task where you know the past input and output both. Okay, when you know in a data has been given to you. You know the input and output both. Like the house price prediction. You have studied the past houses in that area, and you know that how many rooms, bathroom, car, what is the area of that house, how many floors are there. Those are our inputs. And output is the price of that house. Similarly, if I'm talking about heart disease prediction, you know the medical conditions of the patient, and you know this patient is going to have heart disease or not, or he had heart disease or not in the past. You know input and output both. So in that case, you have to use supervised learning techniques. What are the techniques in here? What are the tasks given to you? Basically, inside this, you have two smaller tasks. One is called classification task. Classification task. What is a classification task? So if I give you a data which has a categorical output, okay, categorical output. What will be a categorical output? So if you take a look at this problem we were talking about, this is the output of that. Is this categorical? Yes. What we have, yes and no, yes and no, yes and no kind of thing. Heart disease prediction. So this kind of data, if I'm studying about, which has a categorical output, this is called a classification task. So your output will be yes or no, or you will have fraud, not fraud. Okay. So if multiple transactions are given to you, multiple orders are given to you, so this order was fraud, this order was not fraud. If you're talking about a categorical output, yes and no, fraud, not fraud, loan should be given, not given, yes or no kind of. So they are called classification tasks. So what kind of things you will see in classification tasks? What kind of problems? So problems you will see is you will have heart disease prediction. Only 2 outcomes will not be there, but it will be categorical. Sometime we will have 3 outcomes also, but it will be a categorical type of outcome. Yes, no, maybe, or I'll show you different type of things. That it is not mandatory that you will have only 2 outcomes, yes or no. You can have third category also as the outcome. The next can be loan approval. So which customer of the bank should be given a loan, which customer should not be given a loan. That approval, when you're doing that, yes and no. Basically, you're deciding this customer, yes, this customer, yes, this customer, no. So when you're doing this kind of task and the output is in yes and no format, a categorical format, this is also that. The credit card fraud detection. Here also you say yes and no, that this is fraud, this is not fraud, this is fraud, yes and no. These are few examples of that. What are the algorithms? I told you that every task that you're going to do, there are some algorithms for those tasks. So we have some classification algorithms. What algorithms are there in classification? We basically have one. The first algorithm you will study is logistic regression. Logistic regression is one of the most famous algorithms which are there, used for classification tasks, used for credit card fraud, loan approval, those kind of things. And it is used, in which industry it is used, I will talk to you about that also. For what cases you should be using it, where you have to learn it, I'll be explaining about all of that. Then you have decision tree. Then you have random forest. Okay. And after that, we have some more. There is K nearest neighbor. So today I'm making all of your idea clear that what we do in machine learning. So you read any article, you see any video, you will be clear about that. And we have support vector machines, SVM. And we have this sixth one called as boosting algorithms. There are some boosting algorithms, and they basically are, one is called XGBoost, and one we have AdaBoost. Now, so these are classification algorithms. Let me quickly tell you about the regression also, then I will talk more about them. The second one was, what would be a regression task now? A regression task would be some task where we have, where we have what? The output will be continuous output. Okay. How do you decide that you're doing a regression task and which algorithms have to be used? You basically take a look at the output and you will understand what type of task you're doing. Continuous output. So continuous output will be what? Like a house price prediction. House price prediction. That is a continuous task. When I'm talking about any examples, sales prediction. Okay, how much sales we are going to do in this month, in this year, sales prediction, that is going to be a continuous number. It will not be yes and no kind of things. And if you're talking about stock price predictions, stock price prediction, how many cars this company is going to sell, how many products, how many mobile phones are going to be sold. So when you talk about any use case like that, which has continuous output, all of these tasks that we are talking about, they will have a continuous output. So that is called a regression task. And if you're talking about these, then algorithms which you are going to use for them are this. Algorithms for regression task. The first one here would be your linear regression. This linear regression is a very old algorithm and it has been working quite good for a lot of time. But in today's time, it suffers from a lot of problems since our data is very complex. So you'll have polynomial regression. Okay, and then we have some decision tree regressor. Then we have a random forest regressor. And then we have SVM regressor. And we have neural networks. Neural networks is something which you can consider, or let's remove that for now. We'll be talking about that. That comes in deep learning. So now these are the algorithms that has to be used for a regression task. As I told you that there will be input data and then there will be output data. So there are some names which is actually given to your input data. They're also called independent variables. Independent variables. Or they are also called features. If you see independent variable being used anytime, or you see feature being used, these are the names for input data. For output, we have the names, they are called dependent variable or target. What is this dependent variable? See, output of something depends upon input. If input changes, the output changes. That is why the output is also called dependent variable. And input is independent. Input does not depend upon anything. Age of a person does not depend upon anything. But whether the person is going to have heart disease or not, that yes or no is a output. So that yes or no depends upon the age of the person, the cholesterol level, the chest pain level. Those are input. That is why this output is called dependent variable, since it is dependent upon the input. Input changes, output changes. This is also called target column, output, input, independent features. These are all the names you are going to hear for the data. Now, out of that, if I talk about which is mostly used in industry, see, every domain has different tasks. I'll explain about that, but these two and this, the decision tree, random forest, and boosting algorithm, this is used a lot in the industry today. They are very powerful.
Just a quick info guys, Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
Now, most of these algorithms which you are going to study, that has been created like 20 years ago, 25 years ago by some mathematician. Computer scientists have not created these formulas. This has been created by mathematicians. So mathematicians have understood a way to structure it in such a way that if you give a data to a mathematical formula, so mathematical formula is going to find out some way to make a correct prediction, and it will not be failing in most of the cases, right? So it is not very theoretical. It consists of mathematical approach to understanding how a particular algorithm works. It is just mathematical. But there are some terms that I'm going to use you might not have studied, or if you have studied, you might have forgotten that. So just remember that much. You don't need to know the background concept of that or any forward concept of that. Whatever I tell you, just remember that much. If you can explain that much, that will be enough in any interview, whatever I'm going to cover. Okay, so let's get started for this. Everyone, you focus on it now. We are starting now. So what do we have now is we are going to talk about linear regression. Linear regression is one of the regression algorithms, and it works on when a data has continuous output. Continuous output, like if you are predicting house prices are like this. It will be either 24.3 lakh rupees, 34.2 lakh rupees, 70.8 lakh rupees. It will always be in a continuous format. Prices are never in this integer format. So if your data has something like that, if your data is solving a problem like that, where the output of the data is expected in the continuous form, so that is your regression problem. That becomes a regression problem. And in regression problem, we have a lot of algorithms to solve it. Different algorithms are there. So for some data, some algorithm will work fine. For some data, another algorithm will work fine. We have different solutions for that. So this is the very first, very basic, very popular algorithm we are going to talk about. That is called linear regression. How does it work? What is the approach we follow here in linear regression? We are going to talk about that now. So let's see, we have few things now. And let's see. Now we are taking some data, some X and Y values, and we have, if you see, right, some data points are there. Now, what are we trying to study? We are trying to study, let's say, we are taking a very simple data for now. And that simple data is between a marketing budget spent by the company, marketing budget spent by the company, and the revenue slash sales, or the revenue earned by the company. So if a company spends more for marketing budget, they are going to get more revenue also. That is observed in many cases. Sometimes it cannot be same. But of course, when a company is spending more for marketing, they are going to observe that they are getting more sales. More people are coming to purchase their products, since more and more people are getting to know about that. Now, what do we have is we have taken some examples of that. When the company spent some amount in marketing, they got some amount of revenue. So this is a scatter plot. We have talked about it, but just let me give you an idea about it. So what we have seen, if I take any point, what does this point tell me? That the company has spent this much for marketing budget, some amount, like let's say 3 lakh rupees they have spent for marketing budget, right? Marketing. So in that case, let's say they did marketing, some Instagram marketing, some Facebook marketing, some television marketing on some channels. It costs money. So they have spent 3 lakh rupees for doing marketing on different channels. And with that, they observed that they have got actual revenue this much. It turned out to be that this many customer came and total revenue they earned was this amount. Whatever this amount is, let's say for 3 lakh they have spent, they got 2.8 crore of revenue, right? 2.8 crore. Similarly, what they're doing, if I talk about this point, then company has spent this much marketing budget. Marketing budget has increased. So when I talk about this axis, I told you before also that the numbers increase in this direction. So marketing budget is increasing in this direction. If here it is 3 lakhs, so here it might be 3.5 lakh. Numbers are increased. So similarly, you get this much of revenue. And on y-axis, the numbers increase in this manner. If it is 2.8 here it might be, let's say they got 3.2 crore of revenue total. So this is what our scatter plot is telling us at this point. Now, what we do with this scatter plot? This scatter plot is now going to help us make a future prediction. How exactly? Let us talk about that. Has anyone studied this linear regression before? You've seen it or you have done any bit of that? Little bit, okay? No. Now, so what do we do? When we take a scatter plot like this, see, this scatter plot, all of you must know what it is representing: marketing budget and revenue. So what we do in linear regression is we fit a regression line through that. And what is a regression line? A regression line is such a line which is passing through the data and representing the trend. Can we say that this line is representing the actual trend of the data? This line going through the data points in the upward direction is representing the trend going in the upward direction. And when you make a line through this, this is called a regression line. This is called a regression line. What we do with this is we will be able to use it for making a future prediction. Now, how is this line created? If you take a look at it, this line is created by studying the previous data points which are there, which are these scattered points, right? And now, this is there is also a case that there can be multiple lines. Why am I saying that this is the line that should be there? Why I'm saying that not like this? Why I'm saying not like this? Why not like this? Why not like this? There are different lines that can pass through those data points, right? If I have to make a regression line representing the trend, I can make different lines, correct? So why am I saying that there is this kind of line which is representing the trend, correct? So there is a concept of best fit line. Best fit line. And what does this best fit line do? This best fit line is going to help us to make a correct prediction. Now, how this best fit line has been made? It is created in such a way that it is closest to all the data points. These scatter dots are what? These are your past data. when the company spent some amount in the past, you know what happened? That company spent this much, so this much revenue they got. That is a past data. So when you're taking a past data and you're making a trend line with that, you're making a regression line through that. So how is that regression line created? A regression line is created in such a way that this line should be closest to all the points. And there is no other line which can be closest to all the points like this one. I can make this line. But this line is not a best fit line, because if I talk about the distance of this line from all the points, then what would you observe is it is little bit far away from these points as compared to the previous one. It is this much distance, this much, this much, this much, this much, this. It is observed that any other line which you take, and when you take the total distance of all the points to the second line, to the line number 2, it is more as compared to our line number 1. Can you see this much at least? You're getting the idea. So this, when you take a data point and when you have scattered dots, you have a trend line. And trend line can be created in multiple ways. There can be multiple trend lines. But there is one trend line which is going to be called as your best fit line. Why it is called your best fit line? It is called a best fit line in such a way that all the distance of point to the line, if you take, it will be minimum for that best fit line as compared to any other line present. The distance can be small, the distance can be big, or the difference can be small or difference can be big. But our best fit line will always have the minimum distance, total minimum distance as compared to any other line. Do you understand this much? Slowly we'll move forward. Clear? Perfect. Okay. Let's see. Now, what do we have? Let us talk about this line. How is it going to help us? The concept that I'm talking about, how is it actually going to help us? Let's see. So once I have seen, I have created many lines. I created this. I created, suppose, this line. I created this line. I created this line. I created this line. Thousands of lines are there, which I have made. And out of thousands of lines, what I observed that there is only one single line which will always have the minimum distance. There can be only one best fit line possible ever. That's the concept. There can be no other, there can be no two lines which have the same amount of distance from all the points. And that is how we make our best fit line. What the best fit line do for us, right? So it is going to help us for prediction. We'll come to that now. But let us see, what is this exactly? The distance I'm talking about, what that distance is. So the distance I'm talking about is from a point to the line in a vertical direction. Like this, like this, like this, like this. This is the distance. And we have to take the distance of all the points. Now, this is the line which has been created by studying the past data, and this is the line given to us. And now my Python says that, the algorithm says that, use it for your future prediction. What will it do? You see, this is the point. If you take a look, this is the maximum amount spent by the company, right? This is the maximum amount spent by the company, which is, let's say, 4.8 lakh rupees. Company has never spent more than this in the past. They have spent till 4.8 lakh. Now, 2 months later, they want to spend somewhere around 5.3 lakh rupees, suppose. They have never spent 5.3 lakh rupees. They have only spent till 4.8. And they know when they spend 4.8 lakh, this much is the revenue they got. Okay, this much is the revenue they got. For 5.3 lakh, can anyone tell me what would be the revenue? Can you predict what would be the revenue? Just randomly, not taking in consideration any such line like that. If you have to randomly think about it, can you make a correct prediction to that, how much actual revenue we are going to get for 5.3 lakh by spending this much? It is not possible, right? It is not possible. You can make a random prediction, but you will not be close to the correct prediction. So when we have created this best fit line, which is created in such a way that it is closest to all the dots. Now, what we do with this best fit line, we take a 5.3, which is somewhere on this line, and we will have to match it on our axis. Okay, what do? We now touch it upon our best fit line. Let's extend our best fit line a little. We touch it upon that. And where it touches? Here. Now, we just make a parallel line to that and we touch it on our this. Now, this is a point which tells that when the company spent 5.3 lakh, they are going to get this much of revenue, whatever it is, but this company is going to get this much revenue. How do we know that? So we studied the past data. If you remember the Friday's class, I told you that a machine learning studies a past data. And by studying a past data, it understands the pattern. The pattern which I was talking about, that pattern is represented by this best fit line. It has understood the pattern. So when a machine learning understands the pattern, it represents that into one of these, somewhere line it will make, somewhere curve it will make. Here in the linear regression, it always makes a line to represent that pattern, whatever it has learned. So for these are your past data. For it has created a line, best fit line, to show you that this is the pattern which I have understood from the past data. Now we take the same pattern which your machine learning has learned and give it a new data which it has not seen. We are giving this new data, and what we are doing, the pattern which we have made, we are using that pattern, which is a line. And now we are saying 5.3, when we touch on this line, we touch similarly on the y-axis. This is the point, this is the revenue that we can expect in the future to happen. Now, our prediction can be wrong, it can be right. It all depends upon how better your linear regression has learned the pattern. If it has not been able to learn the pattern properly, so it will give me a best fit line in an incorrect way, right? And if it is giving me a best fit line in incorrect way, I'll get incorrect prediction. Let's see how. So I know that there is this best fit line which is giving me this much revenue. Let us take another line which is not the correct best fit line. Let's suppose this is not my best fit line. I know that. So what this line will tell me, how much revenue according to this line we are going to get. So what we do now, this black point, this black line we are making for 5.3, it will touch it here. For this line, it will touch it here, right? Like we made for the line number 1, it touched here. So for line number 2, which is not my best fit line, it will touch it here. And according to this line, see what is the revenue it is telling us. It is telling us that this company is going to make this much revenue in the future. Now, can you see there is a very big difference between the answers of both? Now, which one is correct? You don't know that. You don't know which answer is correct, but we have to trust something. Where we trust? We trust the best fit line, which is created in a correct way. And we leave it upon to this algorithm to learn the pattern properly. We give it good amount of data. We give everything we can from our side. And we say that a linear regression is going to create a line for us, which will be a best fit line. And it is going to help us to make a correct future prediction. But if the best fit line is not created in correct way, or if you don't have a best fit line, you're taking any other line, which is not best fit. So that any other line will give you this much of revenue. And that is incorrect answer, because this is not my best fit line and the revenue given by this is not correct, because this is not what my pattern was telling, the past data was telling. So what is this distance called? Let us see. we are now clear about our best fit line. So the distance I was talking about, it is not a normal distance, right? The distance I was talking about, it is not a normal distance. It is actually called some error. Let's see. So suppose I take a point. Now this line is going to help us to predict any value on anywhere. Let's say I can take this much. That company want to spend this much for marketing, how much they can expect. So you just touch it on the line. Let's say here it is touching and this much is the revenue. So you can get anywhere, any value you can predict, a higher value, a lower value, any value you can predict. That this much, if we spend, how much we can expect the revenue. But to understand it, to make this best fit line in a very correct way, what has been done is, let's suppose, let's take this data point. Okay, let me take this data point. This is where this interesting concept comes up. Let's suppose this is a data point. Now, we know that there is an answer for this, which is on the, so company has spent this much amount. Let's say it is 1.8 lakh rupees the company has spent, and they have got this much of sales. This is the actual revenue which has actually happened. That is why a dot is there to represent the actual data point. But now there is a line also we have created. What will the line tell me? The line is going to tell me that, okay, the revenue is not that much, but if you have to predict for 1.8 lakh, the prediction will go where? On the line. Okay, the prediction for this 1.8 lakh, according to my best fit line, is what? This is this much, and which is touching here. What I'm doing now, I am now verifying whether my best fit line is good or not. How better my best fit line is, I'm trying to verify that. How? So whichever values I know from the past, I'm trying to see how much error it has done in understanding the previous data. What is the error now? Let's see. So for 1.8 lakh, this is my actual value, but my line, or which the regression line I have taken, it is telling me that this is this value. And for this value, this is the point you get for revenue. But what is the actual? The actual is this black point, and which touches it. Now, there's a difference. There's this much of difference in revenue. So for this 1.8 lakh, when we are studying about what 1.8 lakh, how much we can predict. So my line is predicting this much amount, which is my predicted value. Okay, see, this is your predicted amount, and this is your actual amount. There's a difference between them. So for this point, we know an answer. We know what is the actual and what my line is predicting. So what this is going to tell me that for a single point, how much error a line has made. And if my line has made least error in the previous data points, in the understanding the previous data point, then it is going to make less error for understanding the future data points also. That is the idea we take. So how much is the difference? Let's say the predicted amount was, let's say it is 2.3 crore. Let's say the predicted amount was this much. But my actual, what we have seen, when the company spent 1.8 lakh, we have actually seen that we got around, suppose 2.58 lakh crore rupees of revenue. How much is the difference? 2.85, 58 minus 2.3. So this 2.58 minus 2.3 when we take, that is called error. This is called error in prediction by our line, right? And how much it will come? It will be 0.28. So what my line has done? My line has done an error of 0.28 crore in prediction. My actual prediction was 2.58, but my line said that it is 2.3 for a previous data point. So that's an error. So if my line is making this much error in the past, so we can expect that my line to make this much of error in the future prediction also. So for 5.3, let's suppose the answer we get is this much for 5.3 crore. Let's say this is the revenue for 5.3 lakh is suppose 6.2 crore. So is 6.2 crore the pinpoint answer, exact answer that we are going to see in the future? Of course not the exact answer. But it is going to be closer to the exact answer because we are using the best fit line. It will be closer to that. We can never predict an answer with 100% accuracy, but it will be closer to that. How do we know that? Because from the past data points, we have seen that there was not much of difference. There was 0.28 of difference. So maybe my answer that I get is 6.2. So it might be 6.5 or 6.3, but it will not be like 6.2 we have got, but actual comes out to be 4.8. That's a very big difference. So that much will not happen. And that is what my line is actually telling us. Now, what we do, so to understand that this is the best fit line, what we do now is we take the difference of all the points. Similarly, for let's say for this data point I'm talking about. So for this data point, what will happen? The actual amount is this much. Right, this is the actual for this data point. Or let me take a clean one, just not over there. Let's suppose this. This is my actual data point, let's plot it here. But for this same data point, what my line is telling. For this same data point, my line is telling, if you touch it on the line, and if you make a black line on top of that, this is what your line is predicting for this exact data point. So when the company spent, let's say, this is 4.7 lakh, when the company has spent 4.7, 4.8, suppose. So my actual is this. But my predicted value is what? My predicted value comes out to be this amount. Here is also a difference. So here also would be some difference between actual and predicted, because there is a difference between this and this line. So there is a difference in revenue given by my line and the actual prediction. So what we do, we sum up all the distances. The distances are called what? This distance that we have between the actual dot and the dot which is given on the line. This distance is called what? Error in prediction. Error in prediction. So see, here we have 0.28 of error that we have seen. 0.28 total error we have got. The distance between my dot on the line and the dot which is actual, 0.28. Let's say this is 0.25. This is error 0.25. So what we do is we will do the same thing for all the dots. Every dot will give me some number like this, somewhere 0.28, somewhere 0.25, somewhere 0.83, somewhere 0.19. All the dots will give me some error. Got it? Some error. And what we need to do, we need to sum up all the errors. We need to sum up all the errors made by our best fit line. When we sum up all the errors made by our best fit line, it will give you what? We will get total error. We get total error. Total error by what? Total error by our best fit line. Best fit line. And let's say this comes out to be how much? Suppose total when we combine 0.28, 1.9, 3.8, let's say the total error comes out to be somewhere around 27.2, a number. Prediction of the data is higher in actual. I'm telling that, just I'm coming to that. So see, when I have taken all of these data points, see, then what are we getting? We are getting some numbers like this, and we have to sum it up. But the problem here, and when we sum it up, all of these numbers, when we sum, we get a total error that my line has made this much total error, 27.2. And it is said that how we know that this is my best fit line and not any other line, we compare the total error made by all the lines. So I will make another line, let's say. Let's suppose this is the, let's say this is one more line I'm making, which is not my best fit line. This is line number 2, which is not best fit line. So the total error made by this line is always going to be higher than the total error made by my best fit line. It is always going to be higher. There is not a single line possible whose total error is going to be lesser than best fit line. That is the concept of the best fit line. If you are able to find out any other line where the total error made by that line is less than best fit line, so that line is actually best fit. You make that line as your best fit line. You don't have to do these kind of things in actual. You just need to understand this concept. There are algorithms written for you which will do the task. But when you go to interview, this is the exact thing that will be asked from you. You'll have to explain it in such a manner that we have a scattered points. We make a line. How do we know this is the line we should be making? Because for these dots, there can be thousands of lines possible that pass through these dots. So we know that we have a best fit line and this is our best fit line. How do we know that? We actually do what? We take the total error made by this line by taking the distance of a dot and the dot on the line. We check the total distance of all the dots. And when we check the total distance, I get a total error. Because a distance that I'm talking about between actual value and predicted value is an error in prediction. So when we get this total error, there is no other line which can have the total error lesser than my best fit line. Not possible. That is how I know that this is my best fit line and not any other line. If you understood this, you understood most of the concept of linear regression. Right? We understood most of it. Muthu, you don't have to make the best fit line. The algorithm will take care of that. You don't even have to see the best fit line, how it is created. Algorithm will do everything. There is some code written for you. You don't have to write any code. You don't have to do it. But the best fit line is created in such a way that it is passing through the data points. Now, so now the concept is, if you have the dot on the bottom side of the line and somewhere you see the dot is on the top side. If you talk about this dot, it is on the upper side of the line, right? And then there is a dot, which is this, which is on the bottom side of the line. Will there be any difference in the sign of the distance? Sign of the distance, that will some distance be negative and positive? Let's see. Yes, there will be a difference in sign. Why? Because see, this predicted value that we have, right? The predicted value that we have, error, how do we identify error? Error is, the formula of error says that P minus A, predicted minus actual. You can take actual minus predicted, no issues about that. But let us see, the error we say is the predicted answer minus the actual answer. Okay, that is the idea. Now, here, if you take a look, our predicted is on the higher side and the actual is on the bottom side. Got it? Now, so sorry, we don't take predicted minus actual, we take actual minus predicted. Sorry. Actual minus predicted. So if you take a look, the predicted is on the higher side. It's a larger number and actual is smaller. So what will happen? Let's say the actual is 3.7, but the predicted is 3.86. Will I get a negative distance? Because my predicted is higher value and the actual is lower value. So actual minus predicted we get. So I will get an answer in minus. It will be minus 0.16. Correct. For which dot we are getting negative. So any dot which is on the bottom side of the line will always have a negative distance. That error we are going to get will be in negative terms. And for all the points which we have on the top of the line, we'll have a positive distance. Why? So let's talk about this dot, which is the actual, this one. This is my actual. It is where? It is on the top of it. So what is the actual answer? We get 2.5 it. That is my actual. And predicted is on this line. So can you see the predicted is lesser and actual is higher for a dot which is on the top of the line? Yes. So somewhere we are getting positive errors, somewhere getting negative error, the distance. But I don't have to take the minus and plus. I have to take all the errors and I have to convert it into all positives. Because if I don't do that, what we are trying to find out? We are trying to find out total error, right? And total error, if I'm trying to find out, and if I do this 0.28 plus minus 0.16, if I do something like this, if I'm adding a plus and minus, what will happen? They will cancel out. And the way they cancel out, sometimes they can become zero also. So can my value become zero, 100% zero? The total error made by a line, it can never be zero, not possible. So it is giving me incorrect answer. So that is what I do. We can take a modulus. Modulus means take the negative value and make it into positive. Take a negative, make it as a positive. But the thing that we do here is we don't take the modulus exactly. There is a reason for that. What we do, if I have to make a negative value positive, so what we do, we take a square of that. If you remember in variance also, I have told you the same thing, that when I am calculating variance, so variance of the values will be some will be negative, some will be positive. So they should not cancel out. Variance, if you remember the formula. So there also I said that you don't take the modulus, you take the square of the negative to make it positive. The problem of taking the square is that the numbers start to become big. And why do we do the square? There's a reason for that. We don't just do it randomly. There's a reason. So remember that whenever we have to make a negative point as positive, we don't take modulus in most of the places in machine learning. Modulus does not work properly. So we take square, right? So we take all the distances, we do the square of that. And when we do the square of it, you get a number like this. That is the total error made by our best fit line. And total error is always going to be in least for the best fit line as compared to any other line. That is the final answer. So we have understood the main concept of linear regression with this main concept. Now, there's a concept of line. There's an equation of line. If some of you have studied mathematics sometime, if you remember that, there's an equation of line which is given by mathematicians. Yes, positives will also be squared and negatives, both of them will be squared. So when we do the squaring of the value, what will happen? There is another problem going to happen where the values start to become very big. So we'll take some measures to handle that so that the values don't become too big. We will do something just in a few minutes. So now what we do, we have an equation of line. That's a mathematical equation of line. For any line that you make, its equation is given by this equation of a line. That is called y is equal to mx plus c. What is y? Y is the output. What is x? X is the input. And when we take input, I multiply input with something and add something to it. I get the predicted output. So y is the output that I get. That same thing we represent as in our linear regression. So linear regression does not use mx plus c exactly. Linear regression says that your y is going to be given by an equation called as beta naught plus beta 1 into x. It is the same equation mx plus c written in a different way, where c which was represented for a line. C is beta naught here, and M is the beta 1 and X is X. Just a different notation. There is no difference between that. Now, do you know any, can you find out that line with just beta naught and beta 1? Sometime it is also represented as theta naught plus theta 1x. Just a representation, you will see different representation. These are just symbols used. If you use C plus mx, no issues about that. You can use C plus mx. But in machine learning, we just use this notation, beta naught plus beta 1x, where beta naught is similar to C, beta 1 is similar to M, and X is your input. So we multiply something to the input. This is my input. We multiply something to input. We add something to input. Then we get our predicted output. We don't get the actual output. We get predicted output. So Y is written as Y cap, and this is called predicted output. But this equation is not completed. Why it is not completed? Suppose you are doing a house price prediction, and let's say I give a house. Okay, there's a future. A house has 4 rooms. House has 4 rooms. Now you have to predict the price of this particular house, which has 4 rooms in a area. You have a area, like you're taking a city. It can be New Delhi, New York, or California, Mumbai, whatever city you want to take. You take a city. Now some cities are expensive and some cities are not that expensive. So you take a city. Now let's say a city has a house which has 4 rooms. Now, can you tell me the price of this house just as it is? Randomly, by just looking at a house's 4 rooms, can you predict the price of that? No, we cannot predict. Now, what I have said is, there is a equation. What is this equation? This equation is going to help me for predicting something. What I just told. You get a predicted output by taking this equation. That is what we have been studying. How do we get this equation? This equation is the best fit line equation. When you make a line, that gives you equation like this. But so let's see. If I tell you the Y predicted value is beta naught plus beta 1 into X. X is what? 4. Now take a look. Can you predict the answer here at this point? No, we cannot predict. Because why we cannot predict? What will we multiply 4 with? To multiply 4 with this beta 1 should be a number. And when we are adding here, beta naught should be a number. I cannot multiply 4 with beta naught, and I can add beta naught with that. So this beta naught and beta 1 should be a number. So it means that our equation looks like this. Okay, our equation looks like this, but beta naught and beta 1 should be a number. How exactly we get that number? So when we make a best fit line, this best fit line will give me an equation in the form of Y is equal to mx plus c, or beta naught plus beta 1x. So it will give me, let's say the answer is 4 plus 1.9x. Okay, it will give me such type of equation. Is it in the form of beta naught plus beta 1x? Beta 1x, where beta naught is 4 and where beta 1 is 1.9. Right? This equation is in the form of beta naught plus beta 1x, and this is the equation we are looking for. We know the form, but for beta naught and beta 1, I have to get some number. Now, is this number same always? No, of course not. This number is going to change according to your best fit line. If I take another line, let's say this is another line. So the equation of this line is going to be something else. It might be, let's say 3.7 plus 2.3x. Every line is going to have different set of values for the equation. every line has different formula, every equation. Which is correct? So my correct one is 4 plus 1.9x in this case, and this 3.7 is not correct. Let's see. So now what we have to find out by running this linear regression, what learning actually means in linear regression. What is machine learning? So machine learning is actually finding out that the number is 4 and the number is 1.9, which we can multiply 4 with, and I can get an output. Can we multiply now? So we have 19 into 4, 80, 78, 76, right? So 4 plus 7.6. Now I have been able to multiply. And this number, when I add it up, will I be able to get a predicted house price? Let's say 4 plus 7, 11.6. So 11.6 crore is the price of the house which has 4 rooms in a particular city. Let's say I'm talking about Mumbai. So in Mumbai, we have a house price for 4 rooms. I'm able to predict the price of the house, that is 11.6 crore. How am I able to predict? Because I have understood the past data. We have studied all the houses which are there in Mumbai city, for which we know the prices. We understood those prices. And what we did, when we understood the pattern, we represented that pattern in this form, which is 4.1 plus 1.9x. How do we get this? This we get with our best fit line. Okay, let's summarize what we have done in a step-by-step way. We took scattered points. Scattered points between what? Marketing budget and sales. So we said that, okay, let's take a company. There is a company who wants to predict their future revenue. If they spend some money, how much revenue they can expect in the future. They want to make a machine learning model for that. How is that machine learning model created? So we first started, okay, we know the past data, that in the past, when this company spent some amount for marketing, how much actual revenue they got, they know that actual values. Those actual values are represented by these dots. That is the first step. So that is my scattered dot, and that is the representation of the past data. What machine learning does? Machine learning studies the past and understand the pattern so it can represent or predict a future outcome. It understands the past data, past patterns. How does it understand the past pattern? By making a line. Now I told you that if you want to make a line, there can be hundreds of lines possible, which passes through these data points. Hundreds of lines possible. If you make small changes like this, hundreds of lines are possible. But I cannot take hundreds of lines. That's not possible. I can't use hundreds of lines. There should be one line that is best. What is best? How do we define best? So a line is said to be best fit line when it makes least error in past predictions. When I take the past data point and when I see what is the distance of this dot from the line, that is the error it has made in understanding the past data. So whichever line has made the least error in understanding the past data, the total error we get, that is our best fit line. And once we have found our best fit line, there can be no other line possible. Whatever you try, there is no other line possible which can give me total error less than my best fit line. That is step number 2. Once I get my best fit line, what is the best fit line? What I do with this line? How do I make a prediction? So I can say that, okay, 5.3 I take. I have to touch it upon here and I touch it upon here. I get my future prediction. But you will not do this visually. There should be an equation which takes 5.3 and gives you this revenue. There should be a mathematical equation to help you that. Because when you are running an algorithm, it will not show you this kind of plot. Not possible, because you are going to apply this for how much? You're going to apply this for a very big data. where there will not be 10, 20 dots. There will be 10,000 dots, 20,000 dots, like lakhs of dots. So there should be a formula which takes a input. This is my input. The company says that now we are going to invest 5.3 lakh rupees for marketing. So give that input to a formula and gives you output. So that formula looks like how? That formula looks like this. Okay, this is the formula for that, where the x is the 5.3 I'm talking about. This is that input I'm talking about. So you give that input to this formula and it gives you what? Predicted output.
Let's have a quick quiz question, guys. And the question is, which algorithm is commonly used for clustering in machine learning? And your options are decision tree, linear regression, k-means, or gradient descent. Please mention your answers in the comment section below.
Just a quick info, guys. Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
But can you make a prediction at this point? If I just give you beta naught plus beta 1x, can you predict the output from this? Not possible. So I said that we need a number like this. And this equation looks like this, but it will not be exactly that. It looks like this, where this 4 is your beta naught, 1.9 is your beta 1, and x is x. Same equation, beta naught plus beta 1. Now, values must, that is very important to get now. So once we get this value, can we give 5.3 now? So I can say that, okay, 4 plus 1.9 into what? X, that is my input, into 5.3. When I do this, can I now get a predicted output? Now it is possible, because I have now numbers which can be multiplied, added together to get some output. This output that we get is my predicted output. That is my future prediction, which a machine learning does. Prediction. Is this much clear to all of you? I'm going to talk about how do we get these numbers. I'm coming to that. But is this clear to all of you? This much. I'm coming to that. How do we get exactly that number? That it is 4 plus 1.9. Why not any other number? How do we get that? I'm coming to that. Don't worry about it. Okay, clear? So if you are able to explain this much to anyone, good enough. That is good enough explanation which you can get. I'm going to share this with you. You can study that, but I hope you got the idea. Let's see. Let's take a small break because we have been talking about a lot of things. So total error will be calculated by algorithm. Yes, I'm coming to that. The total error will be calculated by the algorithm itself, and we don't have to do anything. We just need to know the concept. Let's see what happens. In a simple manner, we talked about the complicated things. In a simple manner, what happens is, let's say this is your best fit line. We can see that, right? And we can tell that when the data points are less. If 10 points are there, 20 points are there, then I can make this line easily. But if there are thousands of scattered points, tens of thousands of scattered points, can you make this best fit line by yourself? Humans are not capable of making a best fit line when I give you 10,000 scattered dots like this. Because let's say you are saying this is the best fit line. Your colleague comes up and says, no, this is not the best fit line. Actually, this is like the best fit line. Is there much difference between both of them? No. But when you make a prediction using both of the lines, it will be a difference in prediction. So if two people are looking at it and they're saying this is the best fit line, this is the best fit line, two people can have two different opinions about best fit line. Correct? This can happen. So we said that we give this to mathematics. Mathematics will not will never be incorrect. So I say to the mathematics that take a look at this dots. Some dots are there. Use a formula and give me a best fit line. So the best fit line which is given by a mathematical formula is going to be always same. It will never change. Whoever sees that does not matter. It is going to give us a best fit line. That is what mathematics do. Who is taking care of that? Beta naught plus beta 1x, that's an equation that is taking care of making our best fit line. Yes, Mrityunjay, this is the concept of linear regression. I'll come to that. If something is not linear, then what? I'll come to that. Don't worry. That's a limitation of linear regression, that it always makes a linear line, even if the data is in some other pattern. Got it? Yes. Now, so what we have is we have a line. Suppose this is my best fit line. So how this algorithm, my linear regression algorithm we are studying, how it comes to this as the best fit line. So what it will do, it will not be able to find this best fit line directly. I start my algorithm and it is not going to happen that in the first time itself it get this best fit line. That is not how it works. What my linear regression does is it is going to make many lines like that. It will make this line, this line, this line, this line, thousands of lines, hundreds of lines it is going to make. Sometimes hundreds of lines, sometimes maybe 1,000, 2,000 lines. It is going to make many lines. My linear regression does not know that which one is exactly your best fit. Does not know, cannot know in the start. Not possible. What does it do? It makes hundreds of lines like that. So what we do now, after making these hundreds of lines, we check the total error. Total error for line number 1 will be something. Total error for line number 2 will be something. Total error for line number 3 will be something. Total error for line number 4 will be something like that. Total error of line number, let's say 700. 700 line it has made, suppose, and total error we will get. What we need to do now? How linear regression knows that which is my best fit line? So the line for which the total error is minimum of this, minimum amongst these, right? How I'm getting a total error? A total error is for a specific line. Do you understand that? If I'm saying total error, this one, this must be for a single line. Total error for line number 1, total error for line number 2, total error for line number 3, total error for line number 4. Every total error that I'm getting is for a particular line, for a single line. So if I suppose have found out that there is a line number somewhere in the middle, there is line number 72, which has the least error. And least error is that, let's suppose 27.2 we were talking about. So line number 72 is having least error. We made hundreds of lines, and when we compared those total error, we found out this. So there must be a line which giving me this total error. So that line my linear regression will pick and say this is your best fit line, and then delete all the other ones after that. And it will take that this is your final line which is going to be calculated. You can get a very big number, small number. There's no limitation on that number you can get. You can get a total error in thousands, lakh, millions, any number. But I'm giving you an idea to understand. This much clear? How a linear regression exactly find out the best fit line? Is this clear? So you know how to find out total error. We have just talked about it here. So like this, my linear regression is going to do this thing. This thing we talked about. This thing my linear regression is going to do 700 times, 800 times, 1000 times. And after it does this same thing so many times, it is going to find out total errors every time for every line. And once it gets these many errors, it is going to compare all the total error for every single line it has made. And at the end, it is going to get the one line which has the least total error, and that is my best fit line concept. Now, how do we exactly get these numbers? How do we get this number 4 plus 1.9x? Yes, there's a code written for that. So what do we do now? How do we get our best fit line? We don't get our best fit line directly. We make hundreds of lines. If you take any scattered dots, you make hundreds of lines which are passing around that dots. And after making hundreds of dots, hundreds of lines, every line will give me a total error made by that line. We compare total error of, let's say, 700 lines we have made. We compare the total error made by all the 700 lines. The total error where it is least, whichever line has given me that least total error is my best fit line. We come to that conclusion for now. So let's see. We understood few things. What is the next thing you need to know? You got this idea. Next, you need to know what is that beta naught and beta 1 in this whole concept. What is exactly that beta naught and beta 1? What is that 4.4 plus 1.9? How do we get those numbers? To understand this, again, I'll take a simple example. Let's see, you have a equation. And here we are talking about marketing budget. And here we are talking about revenue. This we took, we were talking about that data. Now, what is that number beta naught and beta 1? Suppose this is the best fit line of ours. This is that best fit line. How do we get beta naught and beta 1? When I stretch it a little, this line on this side, when it cuts the y-axis, when it is intersecting the y-axis, when it is passing through the y-axis, we just pass it through that. Now this point where it is touching the y-axis, this is what? This is our beta naught. This is our beta naught. And the tilt that you see, it is tilted in some way. Like this is a line which is tilted in some way. Right. So this tilt that we are seeing is called the slope. Slope of the line. How it is tilted. So sometimes the line can be tilted like this, sometimes the line can be tilted like this. So they have a slope. It is called a slope in a mathematical term. So that slope is what? That slope is our beta 1 in this case. So beta naught and beta 1, we don't just assume that, we get it from our best fit line. Once you get your best fit line, it will be tilted in some way and it is going to be intersecting at some point on the y-axis. It is going to intersect. So when you are able to find out your best fit line, how do you find out your best fit line? You make multiple lines, you compare all of them, whichever is having least total error, that is a best fit line. So once the algorithm find out your best fit line, then automatically you get this beta naught and beta 1 automatically. This will be some number. Let's say this number is your 1.9 we were talking about. This is that number 1.9. How do we get 1.9? You just have to see the values on y-axis. Wherever it touches, it will be a number there. Then that is 1.9 for now. Beta 1 is what? The slope of the line. The slope of the line is different values. If I talk about another line, this one will have another slope. If I talk about this line will have another slope. So every line, the way it is tilted, that is having a number of the slope value. Now, so whenever we take the slope of this, that is what the 4 I was talking about. Got that? So suppose if I compare it with any other line which is not my best fit line, any other line, not angles, it is just a number given, but a line is on an angle, but we don't give that in an angles. It is a number representing how much is the slope, a mathematical number. Okay, now, so let's say I take any other line which is not my best fit line. Suppose I take this line. Now, if you notice here that this is intersecting here, which is higher than 1.9. So I can, let's say it is my 2.3. And this has a slope. So the slope of the line when it is higher, if it is going in this direction, the slope increases of the line when it goes in this direction. So this line is on the bottom side of it. So it is said to have a lesser slope than the line which is on the upward side. So this will have a slope somewhere less than 4. Let's say it is 3.6. So now the equation of this line, which is my line number 2, equation of line number 2 is going to be what? It will be 3.6 plus for 2. And the equation of our best fit line is what? The line number 1 is 4 plus 1.9. Clear? Any line that you make will have some beta naught and beta 1. Automatically you will get it. What is your task? Your task is to just find out that best fit line. And once you find out that best fit line, it will be automatically that. Yes, sorry. Yes. So we have that, what is the number? 2.3 and 3.66. Yes, this is your beta naught and this is your beta 1 into x. These are the numbers. But this is the equation. That is how you get, which you say the beta 1 value, which you say is beta naught value. And what is that specific number? How do you get that specific number? See, there can be infinite number of possible values. You can get 1.1, 1.11, 1.12, 1.13, 1.14. So like that, infinite number of possibilities are there. From those infinite number of possibilities, how do I find out that it is 1.9 and it is 4? How do we find that combination? We find that combination by getting our best fit line. Once I get my best fit line, it is just the result of that. Simple, straightforward. Okay, are we clear about this also? So let us talk about some theoretical term to put into perspective. Where does it all fit in? If you remember, I talked about that we have input and we create a mathematical function, something like that. So let us see. We have the input. Beta 1 is the slope. Beta 1 is the slope. How much it is tilted? There's a number given to that tilt. You don't have to calculate it. See, whenever you see the tilt, this is tilted in some way, this is tilted little on the downside of that. So whenever we know slope, whenever you see the tilt of that, that is giving you slope number. And that slope that you see, that is your beta 1. I've written here slope is your beta 1, that is going to get your number. Automatically, when you make a line, this is your best fit line. So are we doing anything to get the slope? No, we are just making our line. And line is in a way. No. See, why would you make a slope? I am telling you what. How do you get a best fit line? You have a data and you pass your data, the line through that data, right? Pramod. You have a scattered points, right? And the line is what? The line is passing through that. So if the line is passing through that, is it tilted in some way? Of course it is tilted in. So how are we making this line? This line is being made by a linear regression algorithm. There's a code written for that. The code is written for not to get that slope. The code is written to get this best fit line by comparing multiple total errors. Once you get this line, will you not get the slope of it? It is tilted, you see, like this. So that gets you automatically the slope. So for now, I'm trying to make it very simple. No one is going to ask you any formula for slope or anything. How do we get a slope? You take a data point, you pass a line through that. Once you pass a line through that, it will be tilted in some way. Okay, it will not be like a flat line, it will be tilted in some way. So once you see that tilt, that is going to be your slope. And your linear regression is going to automatically give you that number. I'll tell you that code. You will get that number, the 1.9 I was talking about and 4 I was talking about. You will get that number with a code. You don't have to calculate any of this. Okay, there's a code for everything. See, whatever we are doing now, we don't have to write any code for that. The code will give me. There's a pre-written code. We just have to use it. Let's see. So next we were talking about what? Where does this concept fit in? So there is a structure I told you for machine learning. The structure goes like this. So we have input. We have an input, right? What is that input? That is my future input. When I take this input, where does it go? Okay. What does this input does? So let's not start it here. Let's start it here. Let's say we have a training data. What is training data now? The data points by using which we have made a scattered plot, that is my training data. So when I take a training data and I give it to an algorithm, which is my ML algorithm. That's a general idea. ML algorithm, which we are talking about now, is the linear regression. So we have a data which we give to linear regression. What is the work of linear regression? To make a function, in this case. What does it do? It makes a function. What is that function? So this is what we get, that function, a mathematical function. Create an equation. What is the purpose of this function? It is representing the trend. It is representing the pattern it has learned in a mathematical format. That pattern, that what is the relationship between input and output, whatever it has learned from the past data, that pattern it represents into this function, in a mathematical function. Now, this function is also called hypothesis function. Hypothesis function. What is hypothesis function? I'll come to that. But function is also called a hypothesis function. Why this name? We'll talk about it. Now, so we have this, the function that we got in our case was in the format of beta naught plus beta 1x. Got it? Where this x is the input. Now, this function is created in this way. It is going to be created in this way. But it will be in this way, but it has to have a number. What is the number we found out in our case? The number we found out, let's say, was 4 plus 1.9. What is 4? 4 is the intercept. 4 is the value which was cutting on the y-axis. That is 4. And 1.9 is the slope of that. So I have to get what? This equation needs to be converted into these final numbers. Okay, you need to get this into, this is the final. So the linear regression, the learning which we say, this is the learning. That at the end, the very last answer that you have to get is this exact number. That is the whole concept of linear regression we are talking about. That we need to do a lot of things to get to this number. How we are getting this number? Every step that I have covered from the start of today's session till now is just to get this. Making of multiple lines, finding out total error, finding out best fit line, everything we are doing is to get this equation, which is 4 plus 1.9. Because if I take any other line, which is not my best fit line, the equation changes, hence the prediction changes. Okay, what do we do? How do we complete this equation? So we had a data, we gave that data to algorithm, we got a function. And how do I get the answer? The function is this beta naught plus beta 1. To this function, we give a future input. Future input. And what do we get as a result? We get the result as prediction, or we get a predicted output. That function is what? That function is this beta naught plus beta 1x. So we give some input to this function and we get a predicted output. So our function is our, let's say the input was what? Let's say I'm talking about house price prediction. So I told you that we have 4 rooms. The 4 rooms when passed through this equation will give you some answer here. when we are passing input, a house has 4 rooms. That is the input. When I pass it through this equation, will I get an output? Yes. It will be 4 plus 7.6, and that will be 11.6. 4 plus 7.6 is equal to 11. I'm coming to that. What if we have multiple x values? This is just for one input. The house can have multiple things, that it can have number of floors, it can have area. There can be multiple inputs, multiple x values can be there. I'm coming to that, but I've just taken a very simple example for this. This 1.9 is what will be in the getting them wrong on that. 1.9 plus 4, sorry. So your equation will be according to that now. So you're going to get a output, which will be your predicted output. You can calculate it now. 1.9 plus 4 into 4x, that will be your answer. You're getting just, I made one mistake with that if I have multiple inputs, number of bedroom, number of bathroom, number of floors, the area size, the locality, different things can be there. Multiple inputs can be there. I'm coming to that equation. But before that, let me know, have you understood the gist of it? So this is all about the linear regression. At this point, you don't need to know anything else into this. That is more than enough for now. Now, what do we have here is, there is something which I'm going to talk about now, which is this. What if we have multiple inputs? Whatever it is, you can find the answer. You got the idea, right? You have to multiply and everything. You got the idea. That's just an example. It is not a exact input we're looking at. Now, so when we talk about linear regression, there are two parts to that linear regression. One is called simple linear regression, and another one is called multiple linear regression. Multiple linear regression. What is simple and multiple? What is the difference between them? So multiple linear regression, when we have multiple input, and simple linear regression is one when we have single input. Now, what will it look like? What is exactly the multiple linear regression? See. So the multiple linear regression. Suppose you have multiple inputs. You have the size of the house, number of bedroom, number of floors, how long it has been created, the number of years. So different things are there. Different inputs can be there, right, for a house to predict. So we have multiple x values. We have x1 could be there. X1 is, let's say, the size of the house. Okay, in acres, in square meters, you have the house, right? In square meters, the area of the house, the size of the house. That is one input. Then you can say x2. That is another input. X2 is the representation of another input. That is, let's say, number of bedrooms. We have x3. X3 is what? Number of floors. And then we have x4. That is how, what? Let's say, years. Years old. Right? Yes. So you can take different numbers are there. The how many cars we can have, do we have garage or not? Those kind of things. So these are features of the house, and depending upon these features, the price is decided. If the size of the house is big, the price will be more. If there are number of more bedrooms are there, the price will be more. The number of floors are there, the price will be more. But you see, the years old. If the house is older, the more older it is, the lesser the price of the house is going to be. So this one negatively affects the price of the house, and the other ones are positively affecting the price of the house. So there will be some features which negatively affect and some positively affect. So how our equation is going to look like? So the equation of this y cap, which is my prediction, the prediction will now be like this. It will not be beta naught plus beta 1x. It will now be beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4. 4 inputs are there, so 4 beta values will be there. Now, it is not explainable how the slope of that line will look like according to multiple beta. There was earlier only one beta 1, that was my slope. Now we have beta 2 also, beta 3 also, beta 4 also. So how will that slope look like? So it is not explainable. It is a very higher dimension slope that it is going to create, which I can't show you. Not possible to show. It creates some kind of slope like that, which is not explainable because we have a lot of things. Yes, I'm coming to that. But you represent this into this format. But x4 is minus. I'm coming to that. Now, what is this? What are these beta naught and beta 1? Suppose the beta naught is 80. And let's suppose beta 1 is 0.1 into x1. And suppose 4 into x2. Suppose 10 into x3. And now the x4 is what? X4 is the years old. So what will be the beta 4 for x4? That will be some negative number, right? Because it is negatively affecting that. So it will not be positive value. It will be a negative value, x4. Got it? Now, what are these numbers? What is beta 2, beta 3, beta 4, beta 1? That is kind of giving importance to a particular feature. So see here, we have studied the past data, and according to the past data, my linear regression again understood the pattern. And this pattern it is representing through this equation. So what it is saying, I have taken a beta 1 is 0.1, but I have taken beta 2 a high number, beta 3 even higher number. So what is this smaller number of beta, a higher number of beta represent? So it represents the importance given to a particular factor in house price prediction. So we are predicting the house price. Let's see. What will be 80 now? What is the 80 in this case? Can anyone explain what 80 means in this case? If I suppose you forget that these are not there. If I just have 80, which is my beta naught, what do you think this 80 is in the house price prediction? Yes, it cuts on the y-axis, but in the layman term, if you have to explain someone who does not know y-axis, x-axis, what will you say to? Can you say the beta naught is the base price of the house? Can we say this? That whenever other factors I ignore, I don't look at how many rooms are there, how many floors are there, how many things are there. Can we say that if I ignore all of these factors, then this is the base price, this is the minimum value of the house in that city? So 80 lakh, 80 means 80 lakh is the base price of a house in a city, which is very expensive city. This is the base price. I don't look at the number of floors. If number of rows are more, then it will increase more. If number of bedrooms are there, it will increase more. But at least a person has to spend 80 lakh rupees to purchase a house in that area. That is the least amount, that is the base price, when other factors are ignored. Now x1 is what? X1 we have taken as the size of the house. And x2 we have taken the number of bedrooms. And x3 we have taken the number of, I think same, right? Number of bedrooms, number of floors. And this is years old. This is called multiple linear regression. So multiple linear regression just says that if you have multiple inputs, if you have one input, that is called simple linear regression. So you just have beta 1x, beta naught plus beta 1x, only one input x. But if you have two or more than two inputs, x1, x2, x3, x4, More than 2 should be there. That is called multiple linear regression. So in today's time, we don't use linear regression. Linear regression is only used to explain the concept. It is very easy to explain the working of linear regression with simple linear regression. It will not be possible to explain the slope and every concept when I take multiple linear regression. So any explanation that you see anywhere in this world, you will see the explanation of the whole algorithm given by simple linear because it is explainable. And then you just attach these few extra things into that, it becomes multiple linear. So I hope we are clear with this. And this is the completion of the fundamental concept of linear regression. There are a few more things which are there, but I will talk about that in the tomorrow session. But let me give you one more thing before you go. Okay. Now, just go through this 5-10 minutes you can give after the session. Take a look at it. I'm going to share this file with you. Give it 5-10 minutes. Otherwise, if you don't look at it, you will forget it. It's very easy to forget. Yes, here also there will be one line created. How it will be created, we cannot visualize that. It is not possible to visualize. It is a multi-dimensional thing. So no one can explain, no one can show that, but it is going to create some kind of line which will be only one line. And that one line will be created according to all the beta values which we have, but there will be one line, all this. Okay, so that is called plane. The mathematical playlist which I have given you in the last session. So when you take a look at this, this is called a line. But if you make it higher dimension, it is just a 2D. The line that you see, it is called a 2D figure. But when you go 3D, when you go 4D, when you go 5D, when you go to higher dimensions, that is called not a line, it is called a plane. But you can assume for now that it is creating one line, which is helping us to make that prediction. But that is called plane in the higher dimension. Okay, 1 minute. I'll take your questions. Just 1 minute. Last thing. So what was the problem we saw in the linear regression? Linear regression was working fine, but it has a lot of limitations and problems are there. We'll talk about more of the problems in tomorrow's session. But there was one basic problem we observed. That to get to my best fit line, what I told, that this is my best fit line, but linear regression does not get this best fit line directly. What it does, it makes many lines. And how many lines it will make? Do we have a number that 700 lines will be made, 1000 lines will be made, 2000 lines will be made, 3000 lines will be made? There's no number to that. So earlier, what was happening when the linear regression was created in the first time, people were using in this format that they run the algorithm and the algorithm used to make thousands of lines and then start comparing those thousands of total errors. Total error for this line, total error for this line, total error for this line. First, it will create all the lines possible. Then it sit down and compare all the numbers. And suppose this line has given me least total error. This one is the least. So that becomes my, that this is my best fit line because the total error is least for that. That is what we do. But don't you think that in today's time, it will be very bad because a line is created by taking a data. And if you have a lot of data, then it will take a lot of time to create many lines in that. It will be taking hours and hours, days and days to do such kind of thing, to make thousands of lines for such a bigger data. Because when a line is created, it takes into consideration all the data which you give, all the input data. And if we keep increasing the data, the time taken by this process will increase. We cannot wait for weeks and days just to get a simple result like this, right? So there is an optimization done to this problem. That optimization. So how do we come to this number, which we said was 1.9 plus 4x? How do we get exactly to this number? Is not by comparing 1000 lines. There is an optimization process done to that, which is called gradient descent. Now, gradient descent is a very beautiful mathematical formula, you can say mathematical concept, which does optimization. It is used in machine learning and a lot of physics concept. There are a lot of use cases of this gradient descent. It's a concept. What does it do? It optimizes the process of finding the best fit line. It optimizes the process of finding the best fit line. Okay, best fit line. Now, how does it optimize that best fit line? 2-3 more minutes I'll take of yours, so don't leave it. This is very important. How does it actually optimize? So there is a mathematical formula again to do that optimization, but for now you don't have to know that. What it says is, it says two things. Okay, it says two things, that we start somewhere. We start with some beta naught and beta 1 values. Say 0. We start somewhere and we keep updating. We keep updating the values of beta naught and beta 1 until we get our best fit line. We get our best fit line. So what does gradient descent says? Gradient descent says that it just gives a structure to the process. It makes the whole process in a more structured manner so that the linear regression does not have to waste time unnecessarily. What happened before? In 2-3 minutes, I'm going to explain that. What happens in this optimization is, the first point, the gradient descent says that we start with some beta naught and beta 1. What we have to reach? We have to reach to this 1.9 plus 4x. We have to get this number. How do we get this number? I told you that we compare many lines. Then we come to this number. We directly don't get it. So the gradient descent says to linear regression, they are both combined together now in the code that I'm going to show you. They are now combined together and they work together. So gradient descent says to linear regression, they don't do that kind of thing. Don't make random lines and compare them. Start somewhere. So where does it start? Let's suppose my linear regression is this line. This is my best fit line. And the final output that we have to reach is 1.9 plus 4x. That is the final output I have to reach. So it says that start at 0 plus 0x. I don't know this number. I'm just telling you that we have to reach here, but I don't know. Linear regression also does not know that this is the final output. But when it reaches that, it will know. It says, the gradient descent says that please don't make any random line like that. You're not going to make it simpler. It will be complicated. Start here with 0 and 0x. What will be 0 and 0x? What will be the line for that? Okay, yes. If you want to take a screenshot or anything, you can take it. Gradient descent is a process of finding the best fit line. It optimizes the process of finding the best fit line. How does it optimizes? I'm going to explain that. So we say that, just to take a look at this, I'm explaining the same thing which I've written. The gradient descent says that make the first line which is with this 0 and 0x. What will be the line where the beta naught is 0 and beta 1 is 0? What does the slope of 0 means? Here the beta naught is 0 and the beta 1 is 0. Here we start. So the beta 1 0 and beta naught 0 means the line will be on the x-axis. On the x-axis, not parallel, not on anywhere else, on the x-axis. Because when you say your line is on the x-axis, that always have beta 1 is 0. And of course, where does it intersect on the y-axis? The least point is 0. There we start 0, then 1, 2, 3, like that we start, right? So the least point, which is the start of the axis, that is the 0th point. So the first line which will be created, it will be a flat line. Then gradient descent says that instead of making random lines, why don't you do this? You make the first line here and you check whether this is your best fit line. There is a concept to check that. It checks, is this your best fit line? No. Make a line in this direction. Is this your best fit line? No. Go in this direction. Is this your best fit line? No. Keep going. Is this your best fit direction? No. Keep going. Is this? No. Keep going. Is this? No. Keep going. So who is advising that? The gradient descent is actually one of the algorithm is advising that. And when you come to this, when this is my best fit line, and when your equation comes to this point, it will automatically stop. It will not do any updation on this point. It will automatically stop. And when it stops, this is your best fit line. Once you get your best fit line, you automatically get this equation, which is the beta naught and beta 1. So the beta naught and beta 1 is updated simultaneously at the same time. Because you see, when I'm making another line, the y value where it is cutting, that also changes and the slope also changes. So the beta 1 and beta naught are updated simultaneously at the same time. We don't say that first we update beta naught and then we update beta 1. Never say that. That is the wrong answer. And that is where people get confused. We update beta naught and beta 1 simultaneously. Don't you think this is much better than what we did before, what linear regression was doing before? It was making random line first, top, then bottom, then middle. It was making lines randomly. It did not have any structure. Can we say that this is much, much better than that, which we were doing before? And it is going to make the task very easy, and it is going to do that in a lot less time as compared to the previous one. Can you say that? What do you think? Yes, we can say, because obviously when I show you this, does it look better that the line is making randomly first here and there, here and there, here and there? Instead of that, why don't we start at some point? Why don't we start at the least value where the beta naught and beta 1 is both 0? We start from here and we will keep comparing it. And in the less number of lines, we are going to get it. So earlier, if it was taking, let's say 700 lines, but now with this approach, it can do this same task in 120 lines, 130 lines. So that's a very big improvement in this case. Very big improvement. It does not have always the positive slope. Somewhere the relationships are negative, and I'll talk about that.
Just a quick info guys, Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
Now, what did we say? That if I take that input and output, and if I make a plot of that, so you will get a scatter plot. So as I took one input, that was marketing budget, and one output. So when the company spend some money for marketing, how much revenue they are going to get. So we saw that whenever we make present the data between marketing budget and revenue or the sales, they are both numerical columns. So the plot that will be made for this is going to be a scatter plot. Scatter plot is the best representation for two numerical data. That is what we have seen. So we made the scatter plot, and that was visualization. What is a scatter plot telling you? Scatter plot is telling you about a relationship of the past data. What do we know from the past data? So what I do now, I want to take that past data, and using that, I want to predict a future outcome. That is what we do in this linear regression. Taking the past data, understand the pattern, and we represent the pattern by making a line. Now what we do with that line, we use that line for the future prediction. For the values I don't know, I will be able to predict the future outcome. Now, so I said that for this purpose, we make a line which passes through the data. And it should pass through the data in such a way that it is closest to all the scattered dots which are there. Talking about the red line here. The red line should be closest to all the scattered dots. So if it is very close to all these scattered dots, it means that it is going to give better prediction also. That is the idea here. Now, so we said that how do we identify or how do we verify that this is the best fit line? So for verifying this best fit line, what we said, let's take the help of the scattered points to identify or to verify whether this is actually a best fit line. Because there can be many lines that can pass through the data. As you can see, there is a black line also passing through the data and the red line also. So you cannot have two best fit lines. Best means one. You cannot have two best fit lines. So how do we identify that which is that one best fit line and removing all the other ones? So we said that to find that out, that we are correct about our best fit line, we took the help of all these scattered dots. And we said that let's find out the total error a line is making in predicting the whatever the values are present. So least sum of errors we were talking about. So we said that let's see how much is the distance of this particular point to the line, right? How much is the distance of that? So this distance, same, we will be talking about this also. For every point we have on the scattered plot, we take a distance of that dot to the line. So that distance is the error made by the line in prediction, right? That is the error made by the line. So we said that if my line has made less error in the past, that is going to give better prediction in the future. And the best line is that one which is making least total error. So there is no other line which is going to have less error than our best fit line. So that is how we will be able to identify that I have the best fit line and this is the one. So for that, I said that your linear regression just does not get to your line directly. What it does, it creates many lines like that passing through the data. It will create hundreds of lines and then compare those lines. How it will compare those lines? Every line will give some total error. Okay, every line. So for every line, we'll be checking that line's distance from all the dots, the scattered dots, and we will have a total error. So when we have total error for hundreds of lines, then linear regression sit down and then compare. Let's compare which is the least here. So suppose this line was least. So we will say that this is our best fit line. That is how best fit line is identified. Now, so this much was clear. And we said that this best fit line, once we have got, so its equation is in the form of this beta naught plus beta 1x or theta naught plus theta 1x. These are the forms of equation that you get to see for the line. Because line we are able to see, but we will not be making this kind of line directly as a manually. We are not doing this manually. So there should be some mathematical formula working in the background to do this thing for us and give us the most proper result, the most accurate result. So that is why we take the help of this formula to make a best fit line for us. And it will look like this. I said that it will look like this equation, but it will convert down to some numbers like this. Okay, it should have a numerical value for beta naught and beta 1, and that we use for inputs. So we give the input to this equation, we get the output, and that is called predicted output. So the equation is y cap means predicted output. And this is beta naught plus beta 1x. So when we solve this equation, we get the predicted output. That is the work of any regression or any machine learning algorithm. Then we talked about multiple linear regression, and we saw that just instead of beta naught and beta 1, we have beta naught, beta 1, beta 2, beta 3, beta 4. Whatever number of inputs are there, if we have 10 inputs, so we will have 10 beta values for that. Gradient descent is an optimization algorithm. What it does, it is used with linear regression to optimize it. Optimize it means make it faster. So earlier, without gradient descent, the way the linear regression was working, it was actually making many lines, 700 lines, 1000 lines, and then it was comparing those lines. It was taking a lot of time for that. Okay, so what gradient descent says, that don't do that. And let us follow this process. We have to find a particular beta naught and beta 1 value. And beta naught and beta 1 can be any value. It can be from minus infinity to plus infinity. It can have any number of possible values. So how do you find out that exact number to the decimal point, like 1.43, 3.21? How do you get that number? So we said that the gradient descent says to the linear regression that don't make the lines randomly like that. Follow a structured process. The structured process says that we will start with beta naught and beta 1 somewhere. And let's say we start that with 0. The starting value of beta naught and beta 1 will be 0. Then we will update it. And when we start updating it, keep updating it at a point of time, we will stop when we get that perfect beta naught and beta 1 value, which is for our best fit line. So we will start at 0, we'll update the values of beta naught and beta 1, and then we will stop after a few times of running this operation. So in this case, earlier, if my linear regression was making like 700 lines, so maybe with this gradient descent, it will run 100, 120 lines if it is making, and then it might get the answer in a very less amount of this repetition. So that's a very good approach because we are making it more structured and we are reducing the time taken by the linear regression quite a lot with this process. So now let us talk about few of the practical things. We have to, it will automatically run, and when it stops, it means that it has got that particular value. Until then, it will keep running. So now let's move forward to do some practical, and then I'll tell you about few more theory points. Let's do that. See, there is a thing which gradient descent does to know that we have arrived at the best fit line equation right now. So how does it know exactly that when I have to stop? Because it is updating the values, so it should know somewhere to stop. Okay, so I'm going to give you just a basic idea of that. That's a quite mathematical thing to talk about. I'll not go into the depth of it, but let's see. So when you take the beta value, and then there's something called as cost function that I'll be talking about today. Cost function is an equation which gives you the best fit line. Whichever line has least value for the cost function, that is going to be your best fit line. So cost function is something which tells us which is the best fit line. So whenever you take a beta, any beta naught, beta 1, beta 2, any number of beta values you take, and if you are plotting a relation between beta and cost function, so what you will get, you get a curve like this. That is the property of the gradient descent. Okay, this curve is called the curve of gradient descent. So how exactly gradient descent knows when it has to stop, that it has arrived at that particular value, is in whenever you're taking the beta value and the cost function means a line with the least error. Okay, basic idea. The cost function means a line with the least error. So there will be one point in that curve which will be representing the best fit line. If beta comes to this point, then it has basically got the best fit line. So I'm explaining this, suppose for beta 1. Suppose your beta naught is 0. That is the assumption taken to explain this. Beta naught 0 means, if you're making this line, that it is passing through the origin. That is what beta naught means. Beta naught 0 means it is passing through the origin, not any other point on the y-axis. So it is easy to understand this way, otherwise we'll not be able to understand. But it does not matter. So let's suppose beta naught we have taken as 0, and we need to find out what is beta 1. Got it? That is what used for explanation. Beta 1, I don't know. How do we find beta 1, and how gradient descent knows when it has to stop? So whenever you have gradient descent is kind of having a curve, a mathematical curve, which looks like this always. And what do you see here is there is a point in that which is the best beta. So here you're plotting the beta values, right? There's a, yes, calculus working for that. Now, there is this beta value. Suppose this is our 1.9 we were talking about, right? This is that 1.9. So let's suppose, where did you start? You start with 0. Beta naught 0 and beta 1 0. There we started. Beta naught 0 and beta 1 0. There we started. And where your best fit line is at 1.9, how will that gradient descent knows? It makes a curve like this. It's a lengthy process, but you don't have to go into depth for now. It will be confusing. So it is going to have a point where it will automatically know that here I have to come. So here the values are starting from 0 and it is going till some number. So whenever your value is 0, this curve will be extended a little. And this curve also will be extended a little. See, 0, beta naught 0, beta 1 0 means there will be a point here. So what is this? A line which has beta is 0 will be represented as a dot on this curve. A line which is having a certain beta value, in our case beta is equal to 0. If it is beta 0, we are talking only about beta 1. We have assumed that beta 0 is 0. We are talking about beta 1. How do we get 1.9? How does gradient descent know when it has to stop? So beta 0 is 0, and gradient descent knows that the point is here. Where it has to come? It has to come from here till here. So it has to keep updating till it reaches a point. So what gradient descent will do? Gradient descent will do that, okay, beta 0 is 0, and that is very far away from this point. This is the point of best fit line. So what it will do, it will start updating the value. So when it start updating the value, let's say it made is equal to 0.1. It goes to this. So if it is goes to this, then your line will come here. If it goes to little more, a line equation will come here. Line equation will come here. Line equation will come here. It will come here. And that way, if it keeps updating, keep updating. So then after few times of repetition, what will happen is it will reach to this point in the gradient descent curve. And when it comes to this particular point, it will know that this is the best value of beta. There can be no other best value of beta. So it has come to that, it is going to stop. So this is a curve of gradient descent. It is a inside property of gradient descent that whenever a line is created for a particular beta, it will put that on this curve. And then from there, it starts to come towards the best fit line point. This is what is kind of happened. It starts somewhere and then gradient descent has this curve kind of thing inside of that equation. And that curve tells you that here your best fit line is. That curve has a very good properties that it tells here exactly is the middle of that. The least value is present here. So how does it know least value? The least of this curve is this point. So here is your best fit line. And whenever you have a point and then you come to this beta 1, 1.9 is beta 1 I'm talking about. when I said that there is a gradient descent working with it, so gradient descent has this curve. And when you have this curve, see, this is the point which is the minimum of this curve. See, this you see, there is no point which is higher than this. If you take a look, this is the point, some number is there. Is there any point which is going to be lower than this? Is there going to be any value which is going to be lower than this? You check it, and anywhere I point it. So it will be little higher than that. So the middle of that, exact middle of that, if you're talking about, that is how the gradient descent tells to the linear regression that this is the lowest point of this. So it is your best fit line. The lowest point is considered to be your best fit line in this curve, and here you have to reach. So when it makes the curve, it automatically knows that since this is the lowest point of this curve, this is going to be your value of the best fit line. That is what it is. Equation, I'll come to that. Let's do some practical and then we'll see the equation. Now, so lowest point is denoting that there is a line with the least error. Let us see that what is the process of doing this. What is the process being followed exactly? And you're going to understand a lot of things here, what way a particular algorithm works. Let's see. So we are starting by reading the data that we do first. Whenever we come to machine learning, before coming to machine learning, we do our analysis part. Analysis part, you remember the steps of a data science project. You collect the data, you read the data, then you do some basic data analysis, data manipulation with pandas, and then we do data visualization. After data visualization, we come to machine learning, right? So first, you take a data, you do manipulations, whatever you know, whatever you want to do, you can do your manipulations. We're not going into depth for now. Our main agenda is to understand the process of the machine learning in the very basic form. Let's see. Now, I have a data. This is a marketing data for which we were talking about the marketing budget and the actual sales. One input and one output we are taking to understand this process. Let's see. So you will check about the head and tail, the info, all of the things which are there. You're going to talk about that. So these all things we have covered. Describe and everything we have covered. Now, so see, I took the data, I just checked the few things about that data, and then I'm just making a visualization. This is the scatter plot for that. And when we have the scatter plot, what is our task in this case? Our task or the machine learning task is to fit a line through this, something like this. And that line will be used for regression task, for prediction task. So the process of machine learning starts here. What we do now, let us see. You should be clear about that. What we do first, read the data. Second, we have what? Data manipulation. Data manipulation / cleaning. So whatever I've discussed in pandas concept and the NumPy concept, you will be following those processes and doing something. Whatever you want to know about the data, like sorting the data or selection of data or grouping of the data, whatever is required for that particular project, you do those kind of things, data manipulation, cleaning, analysis with pandas, you do that. And then you do data visualization. Okay. And once you have done the data visualization, then comes the machine learning. Then comes the machine learning part for this, right? So when you do data visualization, when you're doing the data manipulation and analysis with the pandas, you get to understand what kind of data you have. And with that, you get to understand which kind of machine learning technique I should be applying to the data. You get some idea about that. So now, when you're looking through this process, here comes the machine learning, and that is what we are starting with. So before that, you would observe when we start the machine learning process, Before that, you would observe that we have done visualization and some basic pandas thing has been done. That is what always will be done. What is this preparing the data? When you come to machine learning, you cannot apply machine learning directly to the data. It is not allowed. It is not the way to do that. Why? Because before coming to the machine learning, you have to prepare a data in some way. Some of the things you need to do, that is called preparation of the data. Let us see what processes are there for preparation of the data. The first process is identify input columns and output column. We have to identify which is the input columns and which is the output column. So input columns are going to be multiple. They can be any number of input columns, hundreds, thousands, but there will be always one output column, always. That we have to identify. So how do we identify that? We identify and put it into these two variables, x and y. X is going to be all your input columns stored here, and y is going to store the output column. That is what you have to store. After doing this, we have to split the data into 4 parts. We have to split the data into 4 parts. What is this 4 part? See, there is something called as x train, x test, y train, and y test. What is all of these terms? Let's understand them one by one. What is x test, x train, y test, y train? What is this? So the first thing which is required, we identify the input columns and output column. We split the data into 4 parts. That whatever data you're taking, you have to split that or basically divide that into 4 parts. Once you have divided that into 4 parts, then you apply machine learning on this. How exactly that is done? Let us see. To explain that to you, I'm going to take a simple example of one data. See, whenever I was explaining you the process, the steps which are taken for making a data science project, I have said that there is one process where you apply the machine learning. Applying the machine learning technique. So machine learning technique, one of that we have studied here, that is our linear regression in this case. Apply the ML technique or ML algorithm to a data. That is the step I told you when I was talking about those data science process steps. Now, after this point, I told you about the performance of the model. This ML, when we apply to a data, then what does it do? ML algo plus data set. When we apply an algorithm to a data set, what do we get? There was a term I used. When I apply ML algorithm to a data set, what do I get? That I get a ML model, machine learning model. So that result we get, the trained algorithm that we get is called machine learning model, trained model, right? That is what it is called. Now, when we have made this model, what is this model going to do? This model is called a trained model, which is ready for making a future prediction. How it is ready? Because we have taken linear regression, we use that on a data set. What was our data set? The marketing budget and the sales, the revenue. That was our data set. We took the data set and we applied the machine learning algorithm to that. So it understood the pattern, it made a best fit line for us. And that best fit line it has created is going to be used for that future prediction. So whatever equation it creates, using which we can do the further analysis. Let's say that was that is like a 1.9 plus 1.2 into x. Beta naught plus beta 1x. If I take this equation, that is the ML model. ML model has learned the patterns and it has created something like this. This is the equation. So this is called a machine learning model, which is ready for future prediction. Now, as I said, that whenever you are making a model and you're using for the future prediction, it might not give you 100% accuracy. It might not give you 100% accuracy. So let's say I take an input of 4 rooms. There is a house which has 4 rooms. I give this input to this equation. What it will do to that, it will just use it 1.2 into 4 and some result we are going to get. That is the prediction, whatever result we get. Now, what is this prediction? Is this prediction 100% accurate? That if I take many houses like that, and if I give it to my ML model or this equation, is it going to be 100% correct? Like the actual price of the house is suppose 4.1 crore. So will we be able to identify or say predict the 4.1 crore exactly? No, we might be like 3.96 or we might be like 4.21. Will be little off from that, but it is not going to be 100% accurate. But our idea is to understand what we can do best is to get this number closest to the actual that can be there. We don't know the actual, but we can do the best to make it as accurate as possible. Whatever this function we are making, we have to make it as accurate as possible. Now, so what do we do here? We check the performance of the model. Okay, after applying the ML algorithm, the next step would be to check the performance of the model. How do you check the performance of the model? Performance of the model. So what do we do that? Yes, by running it. We run the model on some data to test how better it is. See, so how do we test that? Because if I use it on a data for which I don't know the output, there I won't be able to test that, right? If I run this ML model on a data for which output is not known, I will not be able to test it there. We apply that later, but before that we test it. Where do we test it? See, a data set which is given to you is actually broken down into 2 parts. One is called training data, and there is some part of this data taken for the process of test data. Okay, some part of that main data set is training data and testing data. The very common case is that 80% of that data goes for training purpose and 20% of that data is kept for testing purpose. Now, this training data which you see is shown to the algorithm. It is shown to the algorithm that, see, this is your data, learn the pattern from this data and make an ML model. The ML model which is created gives ML model, right? And this ML model has never seen the test data. So what it will do, this ML model which is going to be which is created will be tested on this data. Tested on this. So why do we do this? See, this test data is a very similar type of data to the training data, since there was one data set and we have split that one data set into 2 parts. So this test data is something which is very similar to training data, but not exactly the training data. And our model has seen this training data, but it has not seen the test data ever. Now, what happens with this when we have the test data? How exactly that look like? See, I have this much data, suppose. A very small example I'm taking. This much is my data set, complete data set. What I will do from this complete data set, I will break it down into training and testing. So what I might do, 80% of this is, let's suppose, this much. I take that for training. And now what this becomes my test data. This is something which I hold out. I keep separate, which I never show to my machine learning model during the training whenever the that algorithm is learning the pattern, whenever it is creating that equation, that it never sees this part of data. So some data, you keep it separate, which you never show to the ML model. What you do, your ML model is trained on this. This is your training data. So what it will see, it will learn these patterns. What pattern? That when the marketing spend was this much, the sales was this much. When the marketing budget was this much, the sales was this much. Marketing budget this much, sales this much. So if we look at that, we won't be able to say any kind of relationship. But my ML is going to see this data, the input and output it will see, it will create a function for that. Create the function. Then how do we check that how better it is for the prediction purpose? Is it giving 80% accuracy and 70% accuracy? That is the thing. Yes, Pramod, of course that is going to happen. I'll talk about it. Now, so what do we do now is we have divided our data into two parts now, the training and test. Training and test. After dividing our data into training and test, we divide our data into few more steps. What is that? So this input, okay, this we break it down into, this is called X train, this is called Y train, this is called X test, and this is called Y test. What is this? See, I am coming to that, Vipin. I'll explain how do we decide 80% and 90%, whatever it is. But see, what we have done, we took a data, we divided that into training and testing. Train and test data. So this upper part you see from here to here, that is your training data. And this lower part you see is your test data, which has. So what does this X train means? X train means input training data. And Y train means output training data. Right? X test means input test data. Y test means output test data. What we do here is very interesting. How do we exactly find the performance of the model is something interesting. So what do? We give these two things to an algorithm. X train and Y train, we give these two things to the algorithm and it learns the pattern. Then on the ML model which is trained, we show the X test and it then finds out some prediction value. Right. So what it will do now after this, let's see. In few minutes, you will understand everything. See. Right. So here, taking a look at this data, my model has learned the pattern. And now after it has learned the pattern, we show the X test. We never show the Y test value to our data in this case. What it will do, by taking a look at X test, it will predict something. And that we say as the Y predicted or Y cap I was talking about. It will predict some values. So for this, suppose the input, when a company spent 2.223 lakh, see, there's a number. So when companies spend this much amount, how much sales we are going to get in the future? That I am telling my ML model to predict. What it will do, let's say it has predicted some amount which is, suppose 17 crore. For 235, how much it is going to be? Suppose it predicts 15 crore. Just taking some numbers. 15.2 crore, 17.8 crores. And for 200, my model has predicted that it is going to get around 14.3 crores. This is what my model has predicted. So how do we check the performance of the model? How good it is? Now we compare what? What should we do to check the performance of the model? We took this for training, and after the model has been trained, we have this X test. X test is shown to the model. Y test is not shown to the model. So we give the X test, which is the future input. We give the future input to our ML model. And X test is my future input. So what we do now, we compare y test and y predicted, which is my y cap. Y predicted is what? When my model has been made, model sees the future input. So when I show the future input to the ML model, it will predict something. So this value which you're seeing here, this is what my model has predicted with this future input. I'm not showing this y test. It is never shown to the model. So once it has predicted it, what we do now, we compare the y test and y predicted, how close they are. So this is your actual result, which is your y test. And this is what your model has predicted. So see, the closer they are, the better is the performance of the model, the closer they are. So actual was 15.5, if you see. And what my model has predicted, 17.2. Actual is 13.5, model predicted 15.2. Actual is 12.5, model predicted 14.3. So they are not very far away, but they are not very close also. So we can say that it is giving us not 100% accuracy, but I can say it is around 80%, 85% performance of the model is there. That it is around 85% accurate, but it is not very good. Very good would have been like 15.5 is there, so it predicted like 15.7, 15.8, something like that. This is the process being followed to check the performance of the model. Why do we check the performance of the model? So if it is giving bad results, we can do something to make it better, to improve the performance of the model. We first need to know how it is performing. Once we know how it is performing, then we can improve its performance better and better. We can keep making it better. So Pramod, I'll come to that. So this is taken from the data. Whatever amount of data you have to work on that itself. And if you know that this is not enough for you, then you will be collecting more and more data by going to internet or by going to the process. No, Nitin, why are you confused about that? We never take normalized data. See, we are not focusing on the normalized data. When we have to do that, I'll be explaining that to you. But every data you don't have to normalize. Normalized data is also same data, but it comes at a place. When it will come, I'll talk to you about it. Don't worry. Everything that you have doubt, I'll be coming to that. Have I shown this data to model? See, what do we do? When you create a ML model, you create it. Correct? What do you have to do with this ML model? Release it in the real world. That is what you have to do. Any ML model you create, this is going to be released into the real world. So before you release it to the real world, would you not test that? Can you just simply trust that ML model which is created, it is going to be very accurate, very good, and you just release it for the real world, and it is very bad. It does not give a correct prediction. So would you want to do something like that? No. In the real world, whatever data is there, that will for that we don't know the output. Whatever my model predicts, we have to trust that this is the input and this is the output given by my ML model. We have to trust that. But how can we trust it? We should know that the predicted value is accurate or it is close to accurate. How do you know that? So before releasing it to the real world, we have a process where we take a part of the same data set for which output is known, but we don't show this output, right? What we show that, okay, let's test how my model will perform on an unseen data. This is your unseen data, right? So what we do now, this is not my actual future input. Actual future input will be when we release to the real world. But we are trying to do simulation that how it will do in the future world, real world. We have to see that. How do we see that? So we take a data for which output is known, but we never show this to the ML model. ML model has only seen this much data. So for that, it is the only data that it has seen. And this data for at that ML model is a future data, which is a new data. So now why are we doing this? Here, since we know the output, we will be able to check its performance. Got it? Now, so I show this. This is my, this is I consider as my future input. And for ML model, this is also a future input because it has not seen this data ever before. So what we do, we never show this. We give this future input to my ML model, it will predict something. So we compare that predicted value with this actual value to see, to validate that my model is actually ready for the real world. That is why we take it. Let's see the process. So for now, we'll not be writing the code. We'll run the code for it, and then you just understand. Okay. For now, just understand this. See, when we are doing this preparation of the data, the first process is you identify the input and output column. The input column is going to be multiple columns and output is going to be one column. So here, since we are talking about one input and one output, so we are taking that one input into this X and that one output column as Y. But you see, I have converted that input column to the data frame. I've said pd.data frame and then this. Why did I do this? Because X requires a data frame. X is expecting a data frame. Data frame means when you have multiple columns in the input, it is automatically a data frame. But when I'm taking only one column for input, that is what it is, a series for now. Since we are taking only one input column, it is a series for now, and X always expect a data frame to be given to that. Why expect that you give it a series? Because Y will always have one column. It will always be a single column. So we don't worry about the Y. For X, just for this example, we will have to convert this series to a data frame and then use it. Later, when I take multiple linear regression, when multiple input is there, so automatically it is a data frame, then we will not do that. Don't worry, we'll see many examples of that. You'll be clear about it. So for now, we are taking the input and output. We are selecting the input columns and the output column. That you have to identify. So from wherever you are collecting the data, you need to see what is your input column, what is your output column. You have to put it like this. Once your X and Y is there, then next what you do? You break your data into 4 parts: X train, Y train, X test, and Y test. So how do you do that? There is a code written for that. What is that code? There is a function in a package. Like we were having pd.merge, np.array. This is what? This pd.merge, this merge is a function in the pandas package. It's a function which is doing something for us. Similarly, there is a package which is sklearn.model selection. This is a package. From that package, we are using this function. What this function will do? This function will help us to split that data into 4 parts so that we don't have to do that manually. If we do that manually, it will be very difficult for us. We'll have to write a lot of things, a lot of code for that. So this function has pre-written code for you, which is going to take care of breaking your data into parts, 4 parts. So what do we write here? How do we do it? We do this. We have to make these many variables: X train, X test, Y train, Y test. We have to make these variables. How do we get? So we use this function, which is train, test, split. What do we mention here? We mention here first the data, which is my input and output column. We have to split this data, input and output, into how many parts? X train, X test, Y train, Y test. So X will be broken down into 2 parts and Y will be broken down into 2 parts. Now, we mention either the train size or the test size. We don't have to mention both things. So test size is 20% we have taken. So for that, it will be 0.20. If you want to mention train size, so there is a parameter called as train size. You can mention that it is 0.80, but we don't have to mention both things. When your test size is 20%, then automatically your train size is 80% that your function understand. You don't have to write both. So we do that. We take this function from a package and then we do the splitting of the data. When we did the splitting of the data, now we move forward to the training part. Because those two things I have done, identifying input and output, and then the splitting of the data. Now comes the process where we start the training of the model. What we do in that? Every algorithm that you're going to use, I will explain the background concept of that, the mathematical concept of that, but you don't have to implement that by writing a code. Whatever I have explained it to you, the process, the comparison and everything, and gradient descent and everything, that is written for you. Okay, the people who are working in this domain, they have written down that for you so that you can use it and you can save a lot of time for yourself. So there is a package which you can see. This is sklearn.linear model. Inside that package, there is a function. This is a function linear regression. Like someone has created def linear regression. And then inside they have put all the code which is there. So when we have taken this, then what we do? This function, we take the linear regression. This is my model. This is my learning algorithm, ML algorithm, linear regression, which is saved inside this function. So this is written like that. What I have to do with this function? I have to give my training data to this ML algorithm. So how do we give a training data to this ML algorithm? We say dot fit xtrain, comma ytrain. Dot fit means on this algorithm, means apply this algorithm to my training data to learn the pattern of the training data. What it means? Apply the learning algorithm, this linear regression algorithm, to my training data to learn the patterns. When we run that, what it will do? It will start the learning process. Whenever I execute this code, it will start the learning process and it will make that best fit line for you. That is what it is doing. Now, since our data was very less, it's not even 20 lines of data. We have very small data, so it is just completed learning in few minutes. Okay, it came in few minutes. So what do we have here? Our model is trained. Whenever you see input like this, it is saying that I have learned the pattern. I'm ready to make the future prediction. Now, what we do with this? So basically, whenever I do this process, you have to break it down into two steps. So what we do basically, this function is the algorithm. So this algorithm, we load it into a variable. That is the step taken. Whatever I have written that is also going to work fine. But what is generally followed is I save that function into a variable. I load that algorithm into a variable, which I've written linear here. And I say linear.fit. Okay, you do this. Why do we do this? I'll explain that better. So we have this linear regression is there. It would fit xtrain and ytrain. So this linear now is trained. That is my trained model. That is saved into this variable linear. What I do now? I have to find out y predicted. How do I find out y predicted? So I take that linear. Linear is my trained model. My trained model is saved into this variable, my trained model. Dot. We'll say predict. The trained model predict what? X test. What do you think will be the prediction value for the X test value? Predict that for me. Okay, now I'm running it. So this is that X test. I'm showing that X test to my trained model now, and it is going to give you that y predicted. Once I get this y predicted, let's see. This is my y predicted, and the y which is there, sorry, y test. This is your y test, which is your actual result, and this is your y predicted, which your model has predicted by learning the pattern.
Let's have a quick quiz question, guys. And the question is, what is overfitting in the context of machine learning? And your options are when a model performs well on new unseen data, or when a model generalizes well to different problem domains, or when a model captured noise in the training data and perform poorly on the new data, or when a model has few parameters. Please mention your answers in the comment section below.
Just a quick info guys, Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
X test is here. When we broken it down into this 4 parts, right? X train, X test, Y train, Y test. From here, I am getting it. So I said that you take X and Y, or you take your data, you break it down into 4 parts. So here I have broken it down. X train, X test, Y train, Y test using this function. This code is given to you. Got it? Now, so what did we do? I loaded a package. This package has a function which is linear regression. This function is nothing but our model, which is written by someone. So what we do, we take that function and we load it into a variable. That's a thing which is done. Why it is done, I'll explain. But we take that model and we load it into a variable. Then we say that variable linear.fit x train and y train. So linear is nothing but the linear regression. That's a model is loaded into that. Now, when this code runs, we have a trained model. So this linear is now trained because it has learned the pattern from the x train and y train input training data, input and output. So we say that this is my trained model now, linear. We say on the trained model, show the X test. It will give you the future prediction, what it thinks. What did I say? We compare the Y predicted with the Y test. This is my predicted value. This is my actual value. Predicted result. And this is your actual result, actual output. Now we compare that. How do we compare it? So there is a function which is going to do it for us. That's going to show it to you. Okay. There is something which is going to test the performance of the model for us. R2 score. What is this R2 score? I'll explain it. So R2 score, what do? We give X test, comma, Y test, comma, this Y predict. We give this to. So it is going to do the task for us. What task? To check how accurate it is. It is 80% accurate, 90% accurate. It will do that task for us. So when I run that, this R2 score will give a number between 0 to 1. 0 means 0%, 1 means 100%. Now it will give me some number. What it has given here? 0.42. 0.42 means 42%. This 42% tells me the performance of the model. Why it is so low? Why we have just 42% as the performance of the model? What might be the reason? Less data. Perfect. So we have very less data and we have not shown enough examples to the training algorithm to learn the pattern properly. Very less amount of data we have. So now how this score you're getting, how 42% you're getting? See, this 13 is the actual value, but my model has predicted this number. 13.5 was the actual, but my model predicted 16.2 for this. 17.4 was the second answer, but my model predicted 18.8. Third is 10.0, then fourth is 11.8, third, and actual is 12.5, my model predicted 14.4. That's bad. Got it? That is bad. So now, this is what we have. This is just a basic idea. That's a very basic program I have taken to give you the understanding of it. Like here. Yes, so Pramod, what we do there, we actually do pd.merge. So I can write it like this. I can, which I have written here, R2 score. So I can write it like this also. See, if I just say from sklearn dot metrics, sorry, if I just say import sklearn dot metrics, if I just say this. Now, what I have done here is, you see, when I say just import sklearn dot metrics, then what I will have to write sklearn dot metrics dot R2 score, and then give my y test and y predictor. Right. So if I do this kind of thing, then I have to write this much. Similarly, what we do in the pandas, we say import pandas, right? Import pandas. So don't we write this pandas dot merge? As PD, we do it. We do it as PD, but basically we do what? Pandas dot merge. Same thing we are doing here also. But what I'm saying, when I'm writing it like this, from sklearn import R2 score. So this package has a lot of functions. Many functions would be there inside this package, since it's a collection of functions. So I'm saying that from this function package, give me only this function. Okay, so if I say here, instead of import pandas, if I say from pandas import merge, then what will happen? I will not be able to use any other function on that. Right? So because I'm saying that from the pandas package, I only want the merge function. Don't give me any other function. I don't want to use any other function. So then what you can do, you don't have to write pandas.merge. You can simply write merge, and then you can write your customer and the market data frame. It will work like that. That is what it is. Okay, that is what. So when we have written this, we got 42% score. Once we got this 42% score, why is this happening? The first very basic reason is that we have too less data for my model to understand the pattern. That is why this is happening. Now, this answer will be different for all of you. If I'm getting 0.42, you might get other answer. Why that happens, I'll explain that also, why that happens. But you might be getting some different answer. You might be getting some different number. So now what we have done here is we have done few processes. Now what has happened at this point, what my model has done, it has made that best fit line. If you want to see that best fit line, those beta naught and beta 1, you can see that. Okay. You have to say, see, coefficient and dot, see, what is this now? The coefficient and the intercept. What is this? This is your, is this your slope or the beta naught? It is your beta naught. And this is your, sorry, it is your beta naught. And this is your beta 1. So as you can see now, we have got a equation. When I ran the algorithm, when I ran this training process, it made a best fit line for us. What best fit line it has created? It has created a best fit line in this form, beta naught plus beta 1x. What is beta naught now? Beta naught is 4.1083 plus 0.051x. That is the best fit line it has created. It learned the pattern, it has created that best fit line for us, and this is the equation that it has come to. And whatever x test you are giving, x test is going here. And when all the x test values are going here, test goes here, then what are we getting? We are getting a y predicted value. Those 3 and 4 y predicted value that we have got is gone through this function. Now, this equation we don't have to see whenever we are making our model. We don't have to see this equation. There is no work of that. The only work is that how better your score is, how better your performance of the model is. We need to improve that. So we don't generally check this. You will never be checking that. It was just a concept explained to you that a best fit line is created and prediction is done through this equation, but you don't have to see this. Okay, it is not making the complete line at this point, but you see it will be something like this. It will intercept somewhere here and is going like that. This is the best fit line that has been created for us, and it looks like a best fit line. It seems like it is closer to all the points which are there, and that is the best fit line for us. So what we have done is we came to the final conclusion that when I ran this data, when I ran a learning algorithm onto this data, which is very small, I got a very bad score, which is 0.4. Now, you would be getting, if you run the same code, you would be getting a different number. Like I've got 0.42, you might get different number. Why that happens, I'm going to talk about that. And I think the process would be clear. We were having this process where we have to identify input and output. All the input column goes into X, output goes into Y. Once we have identified X and Y, then we break it down into these 4 parts. So there is a function which helps us to split our data into these 4 parts so that we don't have to do it manually. And we give it X and Y here and test size. Test size is one of the parameter where we mention a number from 0 to 1. 0.20 means 20%, 0.15 means 15%, 0.30 means 30%. We have to decide how much data we take for testing purpose. But that is with a reason, you have to decide. Once we have taken that, then we do the training of the model. Training of the model, whatever we have understood about linear regression, that is coded here. All the logic, all the operation that a scatter plot is made, then a best fit line is made, the gradient descent optimizes it, everything that I have explained in the theoretical part, the code is written for that into this function. And then when we take that function, the general process I told you is we load that function into a variable and we use that variable to fit it. So basically linear is the linear regression model fit inside. So we fit that on the training data, and this fit means we are starting the learning process. We are applying a linear regression onto the training data. That is what is happening there. Then once we have done it, then next step was take that trained model. Linear is now trained. Once this is completed, this fit part is completed. So this linear variable, which is my linear regression, that is trained now, trained model. So I take this trained model, predict X test, and it is going to give me Y predicted. What it thinks is the prediction value. So we compare Y predicted, which is predicted output, and the Y test actual output. And whatever is the score is the performance of the model. How do we increase the performance? We'll talk about that. And what other factors are there which affect the performance of the model? We'll be talking about a lot of that. This is just the starting bit. Now, talking about that number of the split between train and test, what that number would be. So if I say there is a very basic one. So there is this type of split that happens. 80-20 split, 75-25 split, 85-15 split, 19-10 split, and 17-30 split. 85 and 15. Now, these are the common ways to split your data into 2 parts, training and testing. The first number means training data, and this much is the test data you want to take. Now, on the basis of what it is decided, basically, yes, less than that, we don't take it because that will be too less training data. Now, so what do we need? When we are training the model, we need as much training data as possible. Testing is just for the validation purpose. That is also important. But more than testing, what is important is the training of the model. So whatever amount of data we have, we need to take as much data as possible for the training purpose. Testing, we can do in a small amount of data also. That's not a big problem. But we should give priority to the training part. That more and more examples, more and more data should be shown to the training when the training process is being done, so it can learn the pattern properly. So when we have this kind of data, on this data, what should be the good split that would have been done here out of these five? On the data that we have currently, that's a very small data. You're not going to see anything like this in the real world. It will be very big. But for now, this seems to be the best one, 90-10 split. Best for our data. Why? Because I need to show 90%, which is more and more example I need to show to my training. And for test, I can keep 10%. That's not an issue. Then generally we take, if your data is moderate size, if it is not very small, it is not very big. Yes, if the data is big, you can take any amount for splitting. It depends upon the size of the data always, the training and testing we do. Split that we're doing. See, if the data is very big, you're dealing in millions of data. So in millions of data, you can take any one of that. But what we do generally is we either follow 80-20 or 75-25 or 70-30 when we have too much data. Because we give enough amount of data for training also, and we have enough data for testing also. Because we have a lot of data, no issues about that. But the constraint comes in when we have small size of data, then we need to take care of this very carefully. Now, in most of the cases, you will have moderate size of data, like 10 lakh rows, 5 lakh rows, 15 lakh rows, something moderate size of data you'll have. So this is the most common one take. Okay, this one, most common. So you take enough for training, enough for testing. That is the most common, because you will have most of the time moderate size data. Okay, so it totally depends on if you have very less data. So follow either 90-10 or 85-15 for a very less data. If you have too much data, you follow 75-25, 70-30, 80-20, any three of them. And if you have moderate size, you take 80-20 normally, totally dependent upon size. So we have understood this. Now, let us talk about few more theoretical part of the linear regression. Okay, let's see. I think you have now got little bit more idea about it. We'll be talking about other algorithms, more about it. So your process, your understanding will become better and better over time. But you don't have to worry a lot about it for now. So here, exploring beta. Whenever we are taking beta, sometime beta will be negative, sometime beta will be positive. What does it represent? So if beta is greater than 0, then there is a positive relationship between the x and y. If beta is less than 0, then there is a negative relationship between x and y. What is negative relation? If one is increasing, second decreases. Let's see where we saw that. When I was talking about this multiple linear regression, there was a input which is years old. How much years old a house is. So this is what? This x4 when I take with beta 4, this beta is going to be what? It is going to be negative. Why it will be negative? Because obviously we know that the input which is taken for that x4, it is years old. So this years old is going to affect the house price negatively. The older the house is, the lesser the price of the house. There are exceptions, which is like some very traditional kind of thing is there. We are not talking about it. But in general case, what will happen? If a house is older, then it will affect the price of the house. So that is why this beta 4 is taken negative. That this years old, which is taken, that is given a negative weightage. Other than that, the number of floors, the number of bedroom, the size of the house, they are given a positive beta, because we are giving a positive weightage to those numbers, those values. Higher the negative, higher the positive, the more weightage we are giving to them. That is a different thing, but positive and negative means that thing is affecting the output negatively, and positive means it is affecting the positive, the output positively. That is what is beta. Now, it is very interesting to understand what are the advantages and disadvantages of linear regression. Now, here comes the concept of simplicity, complexity that is going to be used a lot in the machine learning world. Let's see what. So linear regression is very simple to implement and easier to interpret the output coefficients. We have understood now. So what is beta 1, what is beta 2, what is beta 3, what is beta 4? If you have any number of beta, you can interpret it, what they are. What they are? Weightage. You can understand that they are weightage given to it. So if I say that this is 0.1, 0.1 is the beta value which is given to size, which means that we are not giving a lot of weightage to the size of the house. Just an idea. You can give a lot of weightage. But if I say 0.1 to x1, x1 is the size of the house. So it is that size of the house is not important in that area to predict the house price. Maybe all the houses are of the same size. If you go to some colonies in Dubai, if you have seen any videos like that, there are a lot of colonies, there are a lot of areas where the house areas are same. The land size is same. So it means that in particular that area, the size is not given that much of importance. It is constantly same. It is not affecting the price. What is affecting? The number of bedrooms, the number of floors, that is mainly affecting the price of the house a lot. So bedroom affect it a lot and floors affect it even more because a 10 weightage is given to the floors. So you can interpret the result of linear regression very easily, and it is very simple to use. Linear regression. It's a very simple algorithm. When you know the the relationship between input and output is linear, this algorithm is best for that. Independent means input, dependent means output. So when you know that input and output is linearly related, then this is the best algorithm to use in that as compared to any other complex algorithm. It is going to work very well. I'm going to talk more about it. But if you see, it works well irrespective of data size. So linear regression does not have the demand of giving a lot of data to it. It does not demand a lot of data. If you have moderate size data, it should not be like very small, what we have seen for now. It's a very small data. You don't get that kind of thing anywhere. But if you have good amount of data, like 15,000 rows, 20,000 rows, 30,000 rows, that's a small data considerably, but it will work very well in that case. There are some algorithms I'm going to talk about in future sessions. They are very demanding. They want that at least 5 lakh rows should be there. At least 10 lakh rows should be there, very demanding. Otherwise, they don't give you the desired results. So linear regression is not demanding. It works very well irrespective of the size. There should be just a linear relationship between input and output. That should be there. So that is why before applying the linear regression, we should make a visualization between input and output, and we see that whether there is a linear relationship or not. Yes, it will automatically find that. Whatever beta values are there, it is going to find that out automatically. It is going to identify that. It will run the process, everything it will do. You don't have to give anything at all. Because that is the work of a machine learning algorithm. Machine learning is used for that purpose itself. Where we don't know what should be the pattern, we are not able to understand the pattern. That is where we bring in the machine learning. Otherwise, we would be using a software development. If I know the pattern, I can code the pattern and I can create a software out of that. But the machine learning is used for that kind of purpose where we don't understand the pattern, where we are not able to get the pattern of the data. So we bring in a machine learning algorithm. We say, learn the pattern. I don't know what is the pattern. I just know that this is the input, this is the output. I have that data. Take this data, learn it, tell me what is the pattern. Everything that it tells you, the beta naught, beta 1, the equation, the predicted output, everything it does, we just have to give the data to some code written, pre-written code. That also we don't have to write. Yes, it should be linear relationship. If there is the relationship is not linear, then it is not going to work. We are now talking about that. So now, there are some limitations. The very first limitation of linear regression is that the outliers can have a huge effect on the regression line. Let's see. So when I'm talking about lot of dots. I have this, and multiple data points are there. So all the data points are suppose like this. They're kind of like this. What will happen in this data? There will be such kind of line that will be passing through it. That's my best fit line. Correct? Now, this data is a balanced data. There is no value which is very different from all the other points which are there. Suppose now we have a data which is somewhere here. That is little different from all the points, which is kind of an outlier. It is not following the trend. It is not closer to any other scatter plots. So outlier will always show some kind of property like this, that it will be far away from all the general data points. So what will happen to my best fit line? Best fit line has a property that it takes into consideration every point, that it tries to be close to every data point, every single data point. That's the advantage of it, and that is going to cause the problem to the linear regression. So when this best fit line tries to be close to this point, then what will happen to my best fit line is it will readjust itself. And when it readjusted itself, this best fit line will shift towards the outlier, so that its distance is closer to this, and its distance is closer to all the other points also. So even one outlier is there in the data that can affect the linear regression line a lot. It can throw it off the balance, and it can give us very wrong prediction results. That is the very big problem with linear regression. So when you're using linear regression, you have to do the data cleaning. You have to remove the outlier, or if you cannot remove the outlier, if it is a very important information, then you have to use any other algorithm which is not affected by the outlier. So there are other algorithms which are not affected by it. We'll be talking about that, but this is the first very big limitation. The second limitation is that linear regression assumes a linear relationship between between input and output. It assumes that there is a linear relationship, which is not the case in most of the problems in real world today. Right now, the linear regression is created in such a way that it has to be closest to all the points. It cannot ignore itself, because there is a code written for that. That's the property of the linear regression, that it tries to be closest to all the data points. It does not matter if that is one data point or 100. It has to be closest to all of them. So even if one is there, even if one outlier is there, it will be shifting towards that. It is going to take that also into consideration. It cannot leave it, will not leave that. That's a problem. Now, linear regression assumes a linear relationship between dependent and independent variable, which is not the case in most of the things. This is very important to me. In today's time, we rarely have a linear relationship. Our data in today's time is too complex. The relationships between input and output are too complex that we rarely see the linear relationship between that. So linear regression was very good like 7-8 years ago, but linear regression is not used much in today's time. We have better and much more robust algorithms which do regression tasks. I'll be explaining that in the upcoming sessions. But linear regression is not used much in today's time. Whenever you go to interview, the interviewers ask the linear regression because it is very interesting concept. You understand a lot of things when you understand linear regression, but it is not going to be used. Why? Let's see. So suppose I'm taking an input and output. The relationship might be like this kind of relationship is there, which is not exactly linear. So what kind of things should be done here? What should be done exactly is there should be a line like this. There should be a line like this, and there should be a line like this. This kind of thing should be created. But what my linear regression will do to this, it will just do, it will do this. What do you think? Is the red one better or the black one better? Which line is more closer to all the data points in this case? Red one, of course, the red one. Why do you think the black one? See, the black one here, if you observe this much area, it is very far away from the black, from all the green dots which are there. But the red line, it is passing through the data from the middle of the data very properly. Right, okay. Now, what our linear regression will do? Linear regression does not care what type of data we have or what kind of relationship is there. It will do its task. What it will do, it will just make a line through it. Is this better? No, because it is far away from these points, it is far away from these points, it is not exactly passing through the data. But linear regression works like this. It will try to make a best fit line in this case. This is the best fit line. But is the best fit line actually good for this case? No. Best fit line is a best fit line which is better than any other line which could be created for that data. That is a best fit line. But best fit line does not need to be a proper working model. It is just going to create a best fit line on any data that it thinks should be created. And there is no other line which can do better than that. But when we check the accuracy or the performance of this, it might come down to be just 60% or maybe 55%, because it is not passing through all the data. So that is why the linear regression assumes that there is always a linear relationship, but sometimes not. So, but it tries to make something like this. What we do, so we'll be talking about a very robust algorithm, decision tree regressor. That's an algorithm. Decision tree regressor, random forest regressor, those are very robust algorithms which are going to work in today's time. So this decision tree regressor, if I apply, so it will make this kind of line. One is this, one is this, and one is this, which will understand the pattern much better than the linear regression, and it is going to give us much better accuracy than the linear regression in most of the cases. So that is the problem with linear regression. The concept of simplicity, because of which linear regression was created, becomes the limitation for that in today's time. Okay, the goodness of it becomes the problem for it. It is prone to underfitting. Linear regression sometimes fails to capture the underneath pattern in the data properly due to simplicity of the algorithm. There are two very big problems in machine learning. One is called underfitting and one is called overfitting. Underfitting simply means inability to learn properly. Okay, inability to learn properly. The red one is another algorithm. It's another algorithm, some other algorithm, don't know which one, but if you take some other advanced algorithms, it will make a red line like that. But linear regression is going to create a black line. So we have to take an advanced algorithm which is going to work better. We cannot take linear regression. That is what I said. So underfitting is what? Underfitting is the inability of a machine learning algorithm to learn the pattern properly. As you can see, linear regression, this black line is what? It is suffering from underfitting. Why? Is it able to learn the pattern properly? The pattern of the data is like this zigzag, but it is fitting a straight line to that. It is not able to understand the pattern properly. It is not able to represent the pattern properly by making that line. That is why it is said to suffer from underfitting. So this is underfitting, and then there is a problem of overfitting. What is overfitting? So overfitting means, underfitting means not being able to learn properly, and overfitting means learning too much. What is learning too much? Let's see. Suppose this is your data. So on this data, the correct model or the correct line that should be created, this is the best form in this case. But there is a problem when you take some algorithm, they are too advanced, that what they will do sometimes, they will try to do something like this. They will try to make a model like this, which is that they're trying to learn too much. They're trying a lot to learn it, which should not be done. So when they are trying too hard, then what they do, they end up mugging up the data. Instead of understanding the pattern, they try to remember the training data. And what is the problem when they remember the training data? When they remember the training data, so they only know about that training data. And when you show them the testing data, they will say, I don't know anything about it. Like, See, so you can understand that with two students in a university, they are all both studying for examination. There's student number one and student number two. Student number one does what? He learns some questions and he understands what is the way to solve the problem. Right? He understands that this is a mathematical question. I have to do this. I have a formula. I am going to do this step and I can solve any problem. He does not remember the solution of the questions. But what student 2 does, whatever has been taught to the student, he tries to remember the exact solution of the questions which has been taught to the student. Will that same question come in the examination? No, that same question will not come in the examination. So when a new question is shown to the student number 2, he will not be able to answer because he have mugged up the solution of the first of the training questions. So that is what overfitting means. Overfitting means you learn the answers, you don't understand the concept, you're learning the answer. And if you understand the proper concept, it means that you learned correctly.
Just a quick info guys, Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
So we have this assumptions of linear regression. What is this assumption of linear regression? So these are few things which linear regression assumes that it is there in the data set, then only it is working. If any one of these things are not there in the data set, if any one of these properties is not there in the data set, so if it makes the best fit line, then also that best fit line is going to be very bad for prediction purpose. Like I have shown you, if you have the curve type of relationship and you're trying to implement or use a linear regression there, that won't work properly. So what are the things we need to talk about? So the first assumption of linear regression, it assumes that the relationship between dependent and independent. Whenever I use these concepts, these words, dependent means output, because output column is dependent upon input columns, and independent means input columns. Input is not dependent upon anything. These are independent. So relation between dependent and independent variables, variable means column, should be almost linear. Okay, so if your relation is like this kind of thing, which is not very linear, and if you're trying to fit a linear line through that, it is going to be very bad. Because as you can see, it is not linear. It is like going straight, then there is a line, then there is a line. So it is not a straight relationship, linear relationship. So here, if you make your best fit line is not going to be good enough for this case. Second assumption is that the mean of residuals should be 0 or close to 0 as much as possible. So now, what we need to check is, like in this case, if you make your best fit line, is it good enough? No, this is not good enough. So what is best fit line? Best fit line is a line which is better than any other line that will be created on this data. But even if you make your best fit line does not mean that it is going to have higher accuracy or higher performance. It just means that whatever data you give it, if your data is like this, if your data is kind of like this, it is not a linear relation. As you can see, what our best fit line will try to do, best fit line might try to make something like this, because this best fit line has to be closer to all the data points. So it might try to make such a kind of line. So this is my best fit line. Best fit line says that it is better than any other line that can be created on a data. But since this is not a linear relationship between this input and output, so even if you make a very good best fit line, whatever the best you can do, then also that is not good enough. So what kind of relationship should be created in this? You should have basically a curve kind of thing. That is a quadratic relationship you need to make, not the linear relationship. So that is the first assumption. Now, so in this case of data, you need to check whether it is done to check whether our line is actually the line of best fit or not. Right. So what do? We need to check the mean of residuals should be close to 0. So what does this second point mean here? That I told you that if you have multiple data points, right? If you have these data points, suppose these data points are there, what will you do? You will just make a line for this. Now, what do you check? You check the distance of this, distance of this, distance of this. So these are called what? These are your error. The distance between the dot and the line, that is your error. And it is also called a residual. That's a term used for that. So like this, you have this error, these are distances. Distance in some numerical number will be there. Like this is 2 point away from that. This is 1.3 point away from that. There's a distance. So if suppose 1,000 points are there, you'll have 1,000 error or distances like that. What you do, if you take these error numbers, whatever the residuals are there, and then you what do? You make a distribution of that. You make a distribution plot of that. And if you are able to get a normal distribution curve by plotting the residuals, by plotting the errors or residual as a distribution plot, it means we can use a best fit line on this data. So this is second point. The second assumption says that if you make a plot of the errors, how do we make a distribution plot? If I give you some numbers, some numerical values, you take those numerical values, you make a distribution plot of that. Any numerical value, if you have 100 numbers, 200 numbers, 5,000 numbers, if some numbers are given to you, you can make a distribution plot of any numerical data. So when you make a distribution plot of these error terms, if you get a normal distribution curve, it means that you can use a best fit line here. That it means that you have a linear relationship between input and output. If you don't get a normal distribution, if you get a skewed distribution, left skewed, right skewed, that kind of distribution, if you get when you plot the errors, then it means it might be the curve relationship or some zigzag kind of relationship, and it is not linear. So even if you apply best fit line here, it does not make sense because the data is not such that where we can fit a best fit line. This is the second assumption. The third assumption says that there should be homoscedasticity or equal variance in a regression model. What homoscedasticity means? See, these are 4 points which are very frequently asked in the interviews, the assumptions. That is why I'm talking about. Now, so there should be not multicollinearity present in the regression. This is one of the most important points that you should know about regression. That there should be no multicollinearity in a regression model. Multicollinearity is a very big problem that happens with the regression models. And whenever your data has multicollinearity, it creates a lot of problems. So whatever predictions you are going to get, that will be incorrect predictions. So what is multicollinearity? It generally occurs when there are high correlations between 2 or more independent variables. See, multicollinearity occurs when there are high correlations between 2 or more independent variables. Now, what we should have is, what is important is you should have correlation, high correlation between input and output. You should have high correlation between input and output. The higher the correlation between input and output, the better your result will be, the better your model will be, the regression model. But if there is high correlation between 2 input columns, the one input column is very highly correlated with another input column, then that's a problem. Right? Like, So if we talk about area, the house price prediction, suppose we are talking about, and we know these two information about the house. One, there's a column given that is the length of the house, the area on which that house is built up. You know the length of that plot, and then you know the width of the plot, and then there is a column called as area of the plot, area of the house, size of the house. So don't you think that the length and area is related to highly correlated to each other, and width and area is highly correlated to each other? Whenever the Yes, so whenever you are having more length in a house, it means that your area will be more, right? And if you have more width in that area, means in a plot, if you have more width, that also means that more area will be there in that house. So they are correlated. These both, if you combine these together, what do you get? If you do length into width is equal to area, right? If you get length into width of any plot, you get area. So the length and area and the width and area, they are correlated with each other, highly correlated. They have the similarity. When one is increasing, the second also increases. If the length of the house is more, then it means area of the house is more. When the width of the house is more, area of the house is more. So in this case, what can we do? We have to delete one of the column. We have to drop one of the column. Why? Because there are two things which are telling me same idea. So why would I need something which is repetitive, which is telling me same? That's a waste of time to use that kind of column. So what do? Either we delete this area column and we use length and width, or we keep the area column and we delete the length and width. Because with the area, I can get the information about length and width of the house. We can make an assumption about that. So that is what multicollinearity means. Multicollinearity means that these are all the three input columns. If there is high correlation between input columns, that is a problem. And you need to delete one of the columns out of whichever is highly correlated. That is a very big problem. But this is called multicollinearity when one input column is related to any other input column. So third point we were talking about, that there should be homogeneity in regression model. This assumption means that the variance around the regression line is same for all the values of the predictor variable. So when we have this, suppose this is our best fit line. So what is said is that whenever your best fit line is created or you observe the scatter plot of the data, you should see something like this. That now you see that there is equal width from both the side of the line. At every place, you have equal width of scattered dots. They're scattered in the same range, same distance on the left side of that, same distance on the right side of that. So everywhere, you see the dots are kind of same on the left side and right side, like at the same distance. That is what should happen. That is how the scattered plot should be. If you see something like this, that around your best fit line, if you have your best fit line like this, and here you see the dots are very close, but as soon as you start to go away, the scattered dots are moving far away, right? So now, if this kind of scattered plot is there, where you see that here these scattered points are very close to the line, not very scattered, but as you go on the further side, you see that the dots are very far away, scattered far away from the linear regression line. So this is a problem. So this suggests that there is some kind of biasness in the data, and it is not purely independent. Some kind of biasness is there. So if you get an answer that will be biased upon something, and it is not going to give us some clear idea about something. So this problem is called heteroscedasticity. So we should not have heteroscedasticity, we should have homoscedasticity. Homoscedasticity says that when you take your data points, you should have the data points should be scattered equally on the both side of the line. It should not be like that somewhere it is very far away, somewhere it is very close, and then somewhere it is very far away. That should not happen. That is the indication of some kind of biasness present in the data. So these are 4 assumptions that is very important for you to know. Don't have to remember it. After a bit of practice, you will be able to remember them very easily. But first is that there should be linear relationship between input and output. That is first. Second, the error terms, when you plot the error terms, if it makes a normal distribution, then it means you can use a best fit line on that data. It is kind of a linear relationship present. There should be homoscedasticity. Means the dot should be equally, the scattered point should be equally present on the both side of the line. Third assumption. Fourth is there should be no multicollinearity. Multicollinearity means if you have high correlation between input, that should not happen, because high correlation between input and another input means they are both telling me the same thing. Delete one of that. Multicollinear. So this tool is like a function. A function is written for you, which is called variance inflation factor. So if you apply this tool on the data set, it does not matter you have 500 columns, 1000 columns. It is going to give you that correlations. Which column is highly correlated with another input column, it will tell you that. So you don't need to do that manually. It is not something you should worry about. There is a tool which will do that. Okay. Now we are talking about this matrix. Whenever you have created a model, you have to evaluate it. Okay, we have to evaluate it. Now, so for this, you need to take a look at the data. You need to make a plot of multiple input columns with each other. When you make correlation plot and when you get this, right? The correlations, you remember, we were making a correlation matrix of that. I said the data frame dot CORR. So when you do that, you get to see the correlation between all the input columns. Okay, suppose my data frame is the market data frame. And if I say dot CORR, what does it show me? It shows me the correlation between all the input columns which are there. So when you see this correlation, you'll be able to figure out where the correlations are high, between which column and which column the correlations are high. So when you get something like that, you delete one of that, which are correlated with each other. Now, so there is something called as regression model. So we were talking about regression model yesterday, and whenever I have applied the linear regression algorithm on the data, when I said linear dot fit X train and Y train, when I did that, I created a machine learning model. Algorithm applied on a data set creates a model, it created that. So once the model is created and we found the Y predicted, the model made my prediction. So how do I know the predicted value is good? It is better and it is ready for the real world. It has high accuracy. How do I know that? So there are some evaluation metrics which is used for all the regression algorithms. Linear regression is the first regression algorithm we have studied. There are more of them. So these are few metrics which will tell you about the performance of the model. You don't have to use all of them. One or two you use and you just get to see whether your model is performing better or not. It will tell you that. So yesterday I used one of that, which was this R squared. R2 score or R squared, this is called. We use this. So what do they mean? See, mean squared error, then you have root mean squared error, mean absolute error, R2 adjusted R2. So see here, what is mean squared error? So mean squared error is nothing but how do you know which line is better? Okay, how do you know which line is better? So in this case, what happens is the mean squared error tells you what? Suppose you have taken a data set. On any data set that you take, if it is for a regression task, if it is a regression type of data set, you will not be just applying one algorithm to a data set. You apply multiple algorithms to the data set and then you see which one is performing very well. Now, so what we do now, mean squared error. So suppose there is a linear regression which we have studied now. And we have suppose used decision tree regressor. Tree regressor. This is another algorithm which will do which will be helpful for predicting the output in the regression task. This is another algorithm. Now you have taken a data and you have applied both of these algorithms. Now, once you have applied these algorithms, what do you want to see? That which algorithm is giving me better answer in this case? Whether linear regression is giving me better answer or decision tree is giving me better answer. So somewhere linear regression can work well. On some regression data, the decision tree regression can work well. It depends upon the characteristic of the data. So suppose we are working on a regression task. Regression means house price prediction or stock price prediction or sales prediction, revenue prediction, profit prediction. These kind of things we are doing, which are all continuous data, continuous output. So there, suppose the relationship is like the curve relationship. So I told you that here the linear regression will perform very bad. But decision tree regression is a very dynamic and robust algorithm which can work and which can identify this pattern. Linear regression cannot identify. So you apply multiple algorithms on a data and you see which is performing best. And if decision tree is performing best, then you delete the linear regression one and you keep this one. So you are going to apply multiple algorithms like that onto a data, not just one thing. So how do you compare them? How do you compare the performance of linear regression and decision tree regression? One of the tool is this mean squared error. Okay, and this is called the difference between input and output and 1 by n. So you know that how do you get a best fit line? So if I'm talking about a best fit line itself, let's see. How do we know that this is my best fit line, not any other line? How do you identify that particular line? So we said that it should have total least error. The total error should be least for my best fit line. So how do you get a error? You take the y cap minus y. Y cap minus y is what? Y cap is the predicted value and y is my actual value. So when I take predicted minus actual, then what I get, how much is the error? So for if let's say 10 data points are there, 10 scattered points are there. You do this for all of them, what my line has predicted and what is the actual. So you get multiple error terms. And then what I said, you have to add them up. So adding is given by the symbol sigma. This means that add up all the data points which are there. Right. So I'm talking about what? This one. So these are the points which are available here. We are using all of these lines, these lines, these lines. So what does this mean? This point, you see the green one, this is your y. And what you get on this line, that is your y predicted. So for every dot that you see, for every scattered dot, you do what? Y cap minus y or y minus y cap, whatever is, same thing. Actual minus predicted, predicted minus actual, same. Then what you do, this you do for every dot. Every dot has one actual, one predicted, one actual, one predicted. So you do that for every scattered dot which is there. 10,000 points are there. So you do this 10,000 times. Then what we do, we get multiple error terms. What we have to do, we have to add them. So when you add the total error, you are going to get this total error which we are talking about. If you add the error terms which are created. But what is the problem with this? I told you that somewhere the result of this will be negative and somewhere the result of this will be positive when you do actual minus predicted. So it should not cancel out. The positive errors should not cancel out the negative errors. So what do? We just do the squaring of that. Okay, we do the square of that. So this is called this sum squared error. There's a term used for that. Don't need to remember for now. Just I'm telling you that there is a term used for that. Sum squared error. The error, you square it, then you sum it. So when you sum up the squared errors, then you get some number. And whichever line has the sum squared error least, that is my best fit line. Now, so what is the problem with this formula? The problem with this formula is when you're doing y minus y cap and the square of that. If the error term is, let's say, minus 10, right? And when you're doing the square of this, it becomes 100. So there is a very big difference between minus 10 and 100. So when you're doing the square of that, you're able to convert the negative values to positive. But with that, there is a problem happening, that the number becomes too big. And suppose you do the same thing for 50,000 data points, 5 lakh data points, 10 lakh data points. So this number, every number will become big numbers. And when you add it up, it will become a very big error term when you add them. So what is said basically? So we take the sum squared error and we take the average of that. Okay, what do? We take y cap minus y, predicted minus actual. We do the square of that. We do this. So this is called SSE, sum squared error. And when we take the average of it. Why are we taking average of that? It will not affect the working of this formula. It is just going to reduce the number a little bit. So whatever comes out here, whatever the total error comes out here, you divide it by number of data points. So 5 lakh is there, divide by 5 lakh. And so you will have a mean squared error, which is reduced number. So then what you do, you compare the mean squared error for one line to another line to get that mean squared error. And that is how, using this mean squared error, you can identify which line is better and which line is not better. How will we know that error is this? Yes, as I told you that the comparison is done, right? Multiple lines are created and the comparison is done. That will be done. That will be done. So we are just saying that instead of comparing these SSEs for all the lines, we compare MSEs for all the lines. And then one of the line will have least MSE, mean squared error. And that is my best fit. The working is same, just there is a formula now to represent that kind of work. That is what I said. Residuals will not be always normally distributed. If your data has a linear relationship, then your residuals will be normally distributed. If your data does not have linear relationship, if it is a curve relationship or zigzag kind of that, then it will be skewed. So when you make the plot of that, it shows skewed. You will get an idea that you don't have linear relationship between input and output, and you should not be using linear regression in that. Maybe use any other algorithm which can handle that. That is what I say. Now, this MSE is something and gradient descent is something else. What gradient descent does? So MSE that I'm saying is, if you have multiple lines like this, what does a linear regression do? Linear regression makes multiple lines like this and checks what? Total error. Right? So total error for this one, total error for this one, total error for this one. That you understand, right? So my linear regression in a normal way create these many lines. It will create many lines, 700,000 lines it is going to make, and then compare the total error of every line to identify which one is my best fit line. So total error is nothing but it is also called sum squared error. It is calculated using this formula, which is my sum squared error. You take y actual minus y predicted, you do the square of that, and when you sum it up, that is what your total error is. If you remember, I told the same thing. So total error is nothing but your SSE sum squared error. Getting it? So now we are saying that instead of calculating sum squared error for every line, why don't we calculate MSE? Why don't we calculate MSE? So MSE is going to be small number. See, Suppose the total error of this line is suppose 2167. I'm taking small number. This is the SSE of that total error. So when you take the average of this, what will happen? Suppose there were 10 data points. So it will become what? 216.7. Now, suppose the total error of this line is somewhere around 3049. So this is my SSE, the total error. If I take it by 10, so what it will become? It will become 304.9. That is MSE when I am dividing by the number of data points. So is it affecting my comparison? It is affecting my working of the linear regression? No. Because you see here, when you're taking average, the average of this line will be higher than the average of this line. So still you're able to say that this is better line as compared to better line. Getting it? So the MSE or SSE or total error, all of these terms are what? They tell you that how much total error is being made by a line. How much total error is being made by a line. That is what MSE, TE, SE, they all say. What is gradient descent? Gradient descent just says that why are you making 700 lines? Make only very few lines and you're able to get that easily. You're getting it now? Okay, so what is dividing 1 by n means number of data points. So if your scattered dots are, if you have 10,000 rows in your training data. So 10,000 rows in training data means every row is represented by a dot. Got it? So the number of dots, that is n, number of data points. Clear? So this is MSE. MSE is just a way to compare multiple models and then see which one is better. Root mean squared error. Those who have a doubt, you can ask me after the session also, but this was just thing. Wherever you calculate total error, instead of calculating total error, I'm saying we calculate mean squared error because that's some smaller number and comparison becomes easy. Then root mean squared error. So you just take the mean squared error and you take the square root of that, you get root mean squared error. It is just done to reduce that number even more to compare the total error of multiple lines. So what is now this root mean squared error? So MSE, let's say, came out to be 216. So instead of comparing 304 with 216 and saying this line is better, we root mean square says that take the square root of these number and the square root of this will be higher than the other one. So of course, this tells me that the root mean squared error is the total error made by this line. So these are just different calculations which you can do to compare which line is better, which line is not better. Now, we have the most famous one. This R squared is the most famous metric which is used in regression. What does R squared? How is it calculated? So R squared says that the metric helps us to compare our current model with the constant baseline and tell us how much our model is better. Now, so the formula of R square is 1 minus MSE of the model, our model that we have created, upon MSE of the baseline. What is this? How our R squared is calculated? That you should understand. See, SSE is sum squared error, Archana. Sum squared error is nothing but total error. SSE is equal to total error. This is just another name for that. Sum squared error, which means total error. Another name. Now, so if you have, let's say, these data points are there. How R squared is calculated, I'm telling you about that. Understand this. See now, when you don't make a line, suppose you're not using a machine learning model. And if you're not using a machine learning model, if you're using just a very dumb calculation on that to make a prediction line, okay, to make a best fit line. So if you're not using machine learning, then what is done? There is something called as baseline model. Okay, something called as baseline model. This is the dumbest model that anyone can create, where you're not doing any learning. And then also, you're just able to make a model which will be used for prediction. That's a very bad model. And any model that you make should be better than this baseline model, should be much better than this baseline model, because this is a dumb model. How do you create a baseline model? Model means that line in the linear regression. So baseline model is created by, you see, these scattered points are there. So when you take the average of these scattered points, it will create this kind of line. Some kind of flat line it is going to create. And how is this line created? By taking the average of all these scattered points which are there. When you take the average of that, this is something how that line will look like. And when you make a model from that, this is called a very dumb model, where you're not learning anything. Are we learning the pattern? No. We're just saying that take these scattered points, calculate the average of that, and see where that average is. So the average is going to be sum of the number on the y-axis, and just related to that number, we have made a line. So now, do you think this is a very good line for that, for making a prediction? Of course not. This is a very dumb model. It has not learned any pattern. We're just taking average of it. Average I can take anywhere. Why do I need machine learning for this? That is why it is called a baseline model, a dumb model, based upon which we try to see the performance of our model. So the better it is, the higher the performance of the model is. Suppose we make one model which is this. We make one model which is this. Do you think we have done a lot of improvement? No. If we make this model, this is better improvement if we make this model. So which line do you think has made the most progress as compared to baseline model, which has done a lot of improvement? The line number 3, line number 2, or line number 1? Which one do you think has made most progress? Yes, so line number 3. Line number 3, right? So we are saying that when we take a baseline model, which is a dumb model, and we compare our model with that, how better has it become as compared to that? So you see, which is a flat line, and from flat line, it has just become better, and it is understanding the data point properly. It is covering, yes, most of the data point. So this model is better than the model number 2, model number 1, and the baseline model. So the better the fit of the line is, the better the R2 score will be. This is represented by R2 score, or R squared score, that is called. So R squared says that we compare the performance of our model with a baseline model, and the better it is from the baseline model, the higher the performance of the model is. So this is one of the most important metric which is used, one most common used metric to get us the performance. It will give you a number between 0 to 1. 1 means 100%, 0 means 0% is the performance. If you get 0.8, 0.8 means 80% of the data points it is able to cover properly. 20% it is not very accurate. So that is the performance of the model, 80%. There is a small problem with this R squared. Small problem. What is the problem with the R squared is that the more input columns we take, the higher the R2 score will be. This is very important. R2 score has one problem. This problem says that suppose we have taken a data, and that data has, let's say, 10 columns. Okay, I have taken a data, I have 10 input columns here, 10 columns input. Only talking about input columns. So when I took this 10 columns, I did my linear regression, we understood the pattern, and suppose the performance of this model came out to be 0.8. 83% is the performance of the model with 10 columns. Now suppose tomorrow I collect some more data related to that house price prediction, and I collect 2 more columns, and I add that to my data set, and I again calculate the R2 score. So if I now have 12 columns, the 12 input columns, so for that, always the R2 score will be higher than 0.83. It might become 0.85, 0.858, but it will be higher always than the 10 input columns. The more the input column you take, you will observe that the R2 score is increasing in that case. But this is not something good. This happens because the R2 score, the formula of R2 score is created in such a way that the more input columns you take, the increase in the R2 score will be always happen. Now, this is having a small problem. Suppose the two columns which I added here, the two extra columns which I added, they don't help me at all in making prediction. They are not contributing to make prediction. They're just two extra columns which I collected. I thought that there is this might help me to make a better prediction, but they are not helping me to make a better prediction, right? So if it is not helping me to make a better prediction, then also R2 score will consider them as important, and it will increase the R2 score with those two columns by adding those two columns. So then we bring in a very robust R2 score, which is called adjusted R2 score. Adjusted R2 score. So what is adjusted R2 score? It is the modified version of R2 score, which says that if you're taking 10 columns, and if it is 0.83 is the R2 score, and you add two more columns, and those two columns are not helping me to make a better prediction when I'm making the model, it will all happen automatically. You don't have to do that. Model will be created, performance you're checking. So ML is good, smart enough to identify these all things, and it will identify whether adding two extra columns is helping than previously or not. So by adding two columns, if you get 12 columns, when you're using adjusted R2 score, it will stay same, 0.83. It will not increase the performance of the model, telling you that the two columns which you have added is not at all helping for the prediction. You can delete those two columns, bring in some more data if you want, but those are just bad. Remove them. No need of that. So adjusted R2 score will take care of that. Got it? So if you're not doing such kind of thing, if you're not updating the data, then you can use the R2 score. But whenever you do the updation of the data, previously 10 input columns were there, now you have got 12, you added 2, then you go with adjusted R2 score to get whether those two are performing better or not. You can compare a model with 10 columns with the model of 12 columns, and you can just see whether improvement has happened or not. If we update the data, if you bring in more columns in that, you should go ahead with adjusted R2. And if you are not doing anything like that, if you've just taken same number of input column from the start to the end, then you can use R2 score. Yes. So 0.83 signifies it is not exactly the accuracy. This is not the accuracy of the model. It is called that R2 score of 0.2 means 20% variance in Y is predictable from X. And at R2 score of 0.40 means 40% variance in our model is predicted by that line. Variance means the scattered dots which are there, my line is passing through most of these scattered plots. It is very close to those scattered plots, and I'm able to identify how much is the change in numbers if I add something, if I delete something. So it is said that 20% variance in the output is predicted by the input. So the more variance you are able to predict using the input, that the better the model is. I'll explain more about it. What does this basically mean? But R2 is some 0.83 means you're able to identify the answer 83% accuracy. Something like that you can understand for now. 83% you can say is a score which is saying that you are able to perform with 83% accuracy. Just as a basic idea, it is not said like that, but for now, for your understanding, you can think it like that. 40% is of course less, so you should be aiming to get close to 100%. The more you can get close to 100%, the better. Multicollinearity is, if it is there, then also it is going to increase in that case. So before using the R2 score, we always do something which removes the multicollinearity from the data. Then only we check the R2 score. We have to go through that process. Okay. So now we have completed the basic fundamental concept of regression, but linear regression for now is complete. Let's see. So let's move forward to understand first.
Let's have a quick quiz question, guys. And the question is, which type of neural network layer is typically used for reducing the spatial dimensions of input? And your options are fully connected layer, convolutional layer, recurrent layer, or a pooling layer. Please mention your answers in the comment section below.
Just a quick info, guys. Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
Classification model. Let us see what does it tell us. Let us see what all things are there. It is going to be interesting. And we are going to talk about the first model, which is called logistic regression. See, this logistic regression is the algorithm for a classification task. But for some reason, its name is logistic regression. Why it is called logistic regression when it is used for classification, I'll be explaining that. But this logistic regression is not for regression task, it is for classification data. RMSE and MSE is just that. Again, if you're updating the data, then it means you're again training the model. Training the model anytime means what? For that updated data, a new model will be created, a new line, all the new lines will be created according to the updated data. So when you update the data, after updating, you don't check the R2 score directly. You train the model first and then you check the R2 score. So when you're training the model, the line which is going to be created, the best fit line and any other line, they will take into consideration that updated value. So we are going to talk about logistic regression. So before talking about any algorithm, any new algorithm, there's a question being asked. Why do we need this new algorithm? Can't we do this task with the previous algorithm that has been created? Why was there a requirement of creating a new algorithm in total? Because it's not easy to make any algorithm which we are studying today. There has been a lot of research papers written, a good amount of research has been done to get what we see now, what we are using in today's time. Every algorithm which is created, there has been a lot of research done to create that. How they are working, what are the concepts behind that. So why people have taken effort to create another algorithm when we already had linear regression? Linear regression is one of the first algorithms which was created. And why did people create logistic regression? So we are going to understand about that. So if I use linear regression for classification task, this algorithm, what is problem? What is the problem? Does it create any problem because of which we needed to create a new algorithm? What is that problem if there is any? So we're going to talk about that first, and then we will understand what is logistic regression. Logistic regression is very simple. If you study on YouTube, if you see multiple videos for that, you will see that different explanations are given. And a lot of the explanations you will find is very complicated, but I'll give you the simplest and the best explanation, which is given by the people who have actually created this algorithm. So those professors, they have taught at MIT, Harvard, Stanford, these kind of universities. So they have given this explanation that I'm going to give you, and that will be very easy explanation to remember. Okay, logistic regression explanation is very difficult, very complicated in most of the. So the first question is why linear regression we don't use. Why it is bad for classification, we are going to understand about that. Linear regression can be used for classification by defining appropriate threshold values, but it is not the right algorithm for the classification problem, because the outliers can affect the best fit line and thus the decision boundary. we create something called as decision boundary in classification models. Why it is what it is, let's see. But the first problem with the linear regression, and it is a very big problem, that the outliers can affect the best fit line, and that's a very big problem. So when the best fit line is affected by the outlier, then your predictions are affected, right? If your best fit line is affected, the predictions are also affected with that. The value predicted by linear regression will be continuous, whereas expected result will be discrete. What I have told you about the classification model, we have seen about the classification model that their output is like this. This is like yes, no, no, yes. These kind of output is there. Or you encode yes as 1 and no as 0, no as 0, yes as 1. So sometime you will see output like this, 1, 0, 0, 1, something like that. No, 0 means no, 1 means yes. This kind of encoding is done. Now, you are expecting in a classification output like this. But linear regression is created for what? Linear regression is created in such a way that it is going to give you a continuous answer. It will tell you about like 2.1. That is the output it has predicted. Let's say 13.9. So is 13.9 yes or no? Is 2.1 yes or no? How do we know? These are continuous output which my linear regression is going to give for any data. If it is a classification data, regression data does not matter. But our linear regression will always give an answer like this. But what I have to predict? I have to predict yes or no. Like a person has heart disease, or a person has, or transaction is fraud or not. I have to find an answer as yes and no. So if a future input is given to this linear regression, it will not tell me the answer as yes and no. It will give some number like that. Is how it is supposed to work. So can you tell me whether this number is yes or no looking at this? Not possible. I don't know what is 13.9. It is yes, no, not possible. So that is why this is one of the very big problem with linear regression, because of which we cannot use linear regression. But before creating the logistic regression, there was one effort done to somehow use it. What was that effort done? We are going to talk about. So the effort says that somehow we can take some kind of threshold value and make it work. We can convert the continuous output to the yes and no type of output. We can do that. How will that be done? Let us talk about it. See, with the linear regression, you put a polynomial through the data in the example below. What is the type of data we have? What is the type of input data we have? We have been given some input columns and the output column is yes and no. So suppose I'm just talking about one input column and one output column. That is easy to understand. We have a tumor size and we have the output column, which is malignant. Malignant means serious. It is at the final stages or not. So there is one input column. This is your input and one output column. When you plot the relationship between input and output column, it will not be like those scatter dots. It will be something like this. So from the past data, we have observed that if the person's tumor size is this, on the x-axis, we are representing tumor size. Let's say there is a patient whose tumor size is this much. Around, let's say a number 120 here, 135 here, 140 here, 150 here. So tumor size, brain tumors, you must have heard about it. So suppose there is a tumor that is happening. It's like some kind of stone kind of thing, that is collected in the brain. That is a tumor. If it starts to increase, that takes up a lot of area in the brain and that becomes fatal. Now, so we are talking about the past patients. We have observed that those who have tumor size, they were not having brain tumor. They were okay till this much tumor size. But as we move forward, when we came to this much tumor size, then what it was observed, it was said that the patient is now not belonging to good, okay patients. They belong to serious patients. So this data was shifted here. So it means that you can now think of like there is a boundary somewhere here. And this boundary says that if a person has a tumor size below this, then they were found to be not having serious case of tumor. And if any patient has tumor size more than this can be, let's say, 155. Suppose there is kind of a boundary between that. So we need to identify this boundary. And if we are able to identify this boundary, then we can convert a linear regression output to the classification output. So this is the kind of data. You understand the data easy? If I take this data and I'm trying to solve it with linear regression, what is going to happen? Linear regression makes a best fit line. So it is making a line which is passing through all the data points. It is close to all the data points. That is how that line is being made. It is okay. And it is going to give me some continuous output, some continuous. Now, so here, what do we say? We basically say that if I take this point, which is the middle point, your output is going to be what? 0 means no, 1 means yes. That is your output going to be either 1 or 0. But when I'm making this line, it is giving me something like that. See, so we say that why don't we take a threshold? At 0.5, we take a threshold. What is this threshold going to do for me? This threshold is going to be connected here on this linear regression line. And wherever it touches this linear regression line, make a line through that. Wherever that intersection is happening, make a line through that. This is called what? This is called decision boundary. Yeah, decision boundary. So decision boundary says that if I have to identify this data point, suppose I get a patient whose tumor size is this much. I don't know whether this patient who has this much of tumor size, whether this patient is going to belong to no, or whether this patient is going to belong to yes. Which category this patient is going to belong. So I have to categorize this patient. I have to put this patient into one of these two groups. So is this patient, does this patient have serious case of tumor or non-serious? How do we know? So see, if I had taken a linear regression line, what I will do, I will take this value and I will touch it on the linear regression. And what I will say, it will give me some number, which is here. So suppose it is 0.8. So 0.8 means what? What can I say? Is this 0? Is this 1? What can I say about that? So here, for that reason, what do? We take our input and we say that I don't want the continuous output. I don't want to get a number 0.81, something like that. I don't want an output like that. So what should we do? We took the linear regression line, we took a 0.5 value, and we touched upon this. And we created a line by touching upon that through that intersection. And we get something called as decision boundary. When we take this decision boundary, we are able to easily classify any value. It will work very well. What we can see, where this tumor size is. Let's suppose this is 155. It is observed from the past data that any person below tumor size of 155 was okay. They did not have serious case. But the patients above 155 started to show some serious problems. Right? Yes, to get answer in yes. So can you now, with this decision boundary, can you say the answer of this person, whether this person is going to belong to this group, the yes group or the no group? Can you say about that? Yes group. Why yes group? Because now I have a decision boundary and I just have to see whether this patient is on the right side of the decision boundary or on the left side of the decision boundary. This person who has this much of tumor size, this size is obviously more than the boundary size, the decision boundary we have created. So with this, it becomes very easy. I can just make an answer as yes or no. If it is more than the decision boundary, say yes. If it is less than this decision boundary, say no. Right. So what we have done, we started with here. We said that if I have to use linear regression for this, so I will take a data point. And this data point, if I try to identify whether this data point belong to class of yes or class of one, there will be some problem. What will be the problem? Let's see this. I will have to touch this X on that. And then I will have to see whatever is the answer here. Suppose this is the value 0.6, 0.5 or something like that. So 0.6 is a number related to this patient, 0.6. That is the output which has been predicted by my linear regression. So by looking at 0.6, can you say that this person belongs to class of yes or class of no? Will you be able to make a confident answer by looking at this number, 0.6? Okay, you can do some kind of, take some kind of idea in your mind, but this is the answer being predicted by linear regression. Making sense? That I have a person who has a tumor size of this. I need to predict whether this person has serious case or non-serious case. I have to predict that. How do I predict that using my linear regression line? I will just be touching that upon this and I'll be getting a number 0.6. This is the prediction made by linear regression. That's a continuous output. This is not yes, not no, not 0, not 1. I need an answer in 0 and 1. So I said that this is not giving me the required answer. So what we should do, why don't we take a 0.5, touch it here, make a decision boundary. Decision boundary is like a number, let's say 155. So with this, when we take this data point, I don't need to check it with linear regression, not required. What I just need to see, whether this person is on the right side of the boundary or on the left side of the boundary. That boundary I have decided 155. So any patient comes up, I just check the tumor of that person. If that person is found to be, let's say 178 tumors, what can I say? I have a boundary. 155 is the boundary. Where 178 falls? On the right side of that. So I can say this person is yes. If a new patient comes up in the future, let's say their tumor size is 143. Is this patient less than the boundary which we have picked on the left side? Yes. So I can say that this patient is not going to have a serious tumor. So you see that we are able to convert the continuous output into the categorical output by taking a decision boundary. So this was an approach taken by the people who have created logistic regression, that they tried to solve the linear regression like this. So instead of making a new algorithm, why don't we take a decision boundary and remove this problem? No, it is decided that it is 0.5 they have taken. 0.5 is commonly taken. This is to be decided by us. Okay, I can see a lot of people running away. So let me know what you're not understanding, but don't run away, because this is very important and it can't be okay now. Yes. See what I have done. Are you able to understand that or not? It is very simple. Yes. First, if you give any data, what will happen to that data? If you're having any data and you try to solve it through linear regression, what linear regression does? Linear regression creates a best fit line. So why this has created the best fit line? Okay, why we have created this line? This is the best fit line which my linear regression has created. How it has created that? So it is seeing that this line is closer to all the points. Here also, it is here also. So it has seen those kind of things and it has created a best fit line which is closer to all the point. This is your best fit line because linear regression knows this. We said that, okay, we have got the linear regression, but what is the problem happening if I take any input, any future input, and I have to predict what will be this future input? Correct. So what we are going to do? You remember what we did in the linear regression. So I said that if you have made this best fit line, what we do with this best fit line? Let's say this company has to spend this much money. We don't know what will be the output. So did I not say that we touch upon this and then we touch upon this and we get this output? We were doing that, right? All of you understand this much, correct? So what I said that if a future input is taken 5.3, we take that future input, we use the best fit line to make a prediction. This is my prediction answer. This is my result output. That is what linear regression does. Same thing we will do here also, that if I have this tumor size, how will I identify this tumor size? Whether this is belonging to where, what is the output of this input? How will I identify that output? So I will take this tumor size. Will I not touch it here? Yes, I touch it here and then we are touching it here. So I get an output. This number is something we are going to get in as an output. What is this number? Since 0 to 1, this is a number, let's say 0.5. So for an input which is taken, a new patient that has come up, their tumor size is this much. Suppose their tumor size is 165. And for this patient who has the tumor size of this much, this is my input. The output given by my line, the linear regression line, is 0.5. This is the output you have got. But what kind of output do you need in the classification task? The output that you need in classification task is either yes or no, or it should say me either 1 or 0. 1 means yes, 0 means no. You're looking for this answer, but you're getting an answer which is in continuous form. That is the problem I was talking about. Make sense? Now, so I said that if you look at 0.55, can you look at this 0.55 and tell whether this is 0 or 1 or this is yes or no? Is it possible for you? No. So we said that this is a problem. Whenever we use a best fit line for predicting something, that's a problem. Now you see, suppose I take a patient here. A patient has come up whose tumor size is this much. What I say about this patient? Is this patient serious, not serious? What do I say about that? So if I have to predict the answer for this person, I have to predict some output. What I will do? I'll take this and I will touch it on the line and it is going to be this. So now this is a number beyond 1. See, what it is telling me, it is beyond 1. So it might be, let's say 1.7. This is again a continuous output. Can you look at 1.7 and say whether it is yes or no, whether this patient is going to have tumor or not tumor? Can you say that? Not possible, because this is a continuous input which does not tell you whether the answer is yes or no. That was the problem. I hope all of you understand that when I try to do the prediction using the line, the linear regression line, it gives me continuous output and I'm not able to say whether a patient is yes or no. Serious, not serious. Correct? Yes. So then what we said, let's take a threshold. People tried this. People said that let's take a threshold at 0.5. And using this threshold, just touch it on the linear regression. Wherever it touches on the linear regression, let's make a boundary there. Boundary is going to be a number again. Let's say this is 155. We have created a boundary by taking the help of linear regression. So this is the boundary created. Now, if a patient comes up, now I don't have to touch this patient on the y-axis or on this, and I have to do that kind of thing. What I can say now, when the decision boundary has been created, I just need to see whether this patient is on the right side of that or on the left side of that. Now you ask your questions. This 0.5 is given in most, it is the common thing taken, but you can play with that number. Okay, I will tell you when you can change this number 0.5, but commonly it was taken 0.5 always. That is the basis upon which this decision boundary concept was created, 0.5. Okay, so 0.5 you take, you just make a line through that, somewhere it will touch the linear line and make a boundary. And when you got the boundary, you just need to see whether this new input is on the right side of that, left side of that. You have a boundary now. So what is this boundary? You have got a boundary at 155. Now, if any new patient comes up, what you have learned the pattern from the data, that it was observed that if a patient has anything less than 155, it was observed. You have learned the pattern. This answer is about learning the pattern. So now, what do you say? Earlier, when this patient has come up, this patient, what we were doing, we were connecting on this and we were giving a continuous output like 0.6. For this patient, earlier we were saying 0.6. Correct? Now, what is this X? This X is some tumor size of a new patient, future patient. Let's suppose this X value is 163 here. So for 163, which was the input, the linear regression was doing what? When we give this input to linear regression, it was giving me an output as 0.6, which was not telling me yes or no. But I said that take this input now, take this input 163 and give it to logistic regression. And what does it do for you? It gives you an answer as 0 or 1. Is this better or is this better? So I was talking about this before, the first method, when we have a line and then we changed this, we converted that to this, method number 2. Correct? So how we get to this method number 2? We get to method number 2 by saying that 163, any input we have taken, just put a boundary. This boundary is at 155. There's a number we have understood. So if a new patient comes up 163, is 163 greater than 155? It is greater. So it means that somewhere it will be on the right side of this. Then I can say my patient is having a serious case. Yes, this person is going to have a serious tumor in the future. If a patient comes up 148, their tumor size is 148, a future patient. What can I say about this patient? Serious or not? So we compare with this boundary and we say if it is falling on the left side of the boundary, it is no. This is not the actual algorithm. I am talking about what people did to solve the problem. Okay, this is not my logistic regression. I'm not talking about logistic regression here. I'm just talking about when there was this problem. When people had to solve a classification problem with the linear regression, what problem they faced and how they approached that problem to solve that problem. This is what I'm talking about. So instead of this linear regression line, they created a decision boundary. And they said that we will be using decision boundary to make a prediction, not this linear regression line. So they have taken the help of linear regression line to make a decision boundary. Once the decision boundary is made, we don't care about the linear regression line at all. Then decision boundary is what matters to us. If our data point is beyond the decision boundary, more than that, yes. If it is less than decision boundary, no. This much. So here, what we have seen, we had input and we were able to understand the pattern. First, a linear regression line we tried to use. So linear regression line, we saw that if we take any future input and we have to predict the answer. So for a future input, when we take help of linear regression line, it gives me continuous output. That was the problem. We solved that problem by taking a decision boundary. So when we take a decision boundary, our answer becomes yes or no. We are able to solve that one problem. So there were two problems, right? the values predicted by linear regression will be continuous, whereas expected result will be discrete. So we were able to solve this problem through the decision boundary concept. We took a line, which was our decision boundary line. We made that, and we were able to solve this problem. Now, when we are able to solve this problem, then comes the problem number 1, which is outliers that can affect the best fit line and thus the decision boundary. See this. This is very interesting. I take the same example. Now, as I told you before also, that if you have outlier, so your linear regression line was like this before. It was something like this before. That was your line before, best fit line. Now, what is the property of best fit line? The property of best fit line is that it tries to be closer to all the data points. Then an outlier has come up. So this outlier is what? In the data set, we saw that there was a patient. In the past, there was a patient who came to the hospital when they had the final case of tumor. That patient could not be saved. They had a very big tumor, and then they came to the hospital. So when the patient was checked and the data was collected for that patient, this is also into that data set. So now, because of this one patient, your linear regression line or the best fit line is shifting from here to here. That is what happens. I told you yesterday also that if you take any outlier, your best fit line shifts or goes towards that outlier. Now, so our best fit line should have been actually like this, but just because of this, our best fit line becomes this one outlier. What is the problem? Can you tell me the problem that is going to happen? What is the problem now going to happen? Can you see any problem with this? Just a small answer, not any big explanation. Nothing? Yes. So your boundary shifts. Boundary shifts. What happens now? You see. So I take again 0.5 now, because that is the number we take. So from 0.5, now I want to make a line. And I have to touch this linear regression line. And there I make a decision boundary. Earlier, if you remember, our decision boundary was where? Somewhere here. And now, because of this thing, because of this outlier, my best fit line has shifted. And because of shifting the best fit line, what is going to happen? This is going to be new decision boundary. That is what is going to happen. Now, because of this, a disaster is going to happen. Our model will become so bad that it will do a lot of incorrect predictions. What we are saying now is a patient now is supposed to be more than this decision boundary to be said as serious, and less than this, not serious. So earlier, if I took this point, data point, there is a patient whose tumor size is, let's say, 167. Right, 167 is the tumor size of the patient before. So what it was, according to the earlier decision boundary, it was yes. This patient was yes, that they have a serious case of tumor, since it belonged to on the right side of the previous decision boundary. What has happened to my new decision boundary? It is this one, which is suppose, let's say, somewhere at 175, earlier it was at 155. Now 167 is where? On the left side of it. Left side means no. So this patient who has been identified as yes, according to correct decision boundary, is being identified as no. Don't you think it's a very big problem? All the patients who had tumor size of 155 and to 175, they should be classified as serious cases, but they are being classified as non-serious cases because of this new decision boundary. Is this a problem? Yes, this is a problem, because you're making a very incorrect prediction. You're saying about a patient who should be considered as serious, you're saying that they are not serious. Is this making sense, this problem? Yes. So my decision boundary has shifted from here to here. That is what happened to my decision boundary. Because of what? Because of presence of outlier. Should this happen? Of course not. This should not happen. This kind of problem should not happen. So that is why this is second reason because of which we cannot use the linear regression. Even though I am able to make a decision boundary, but decision boundary is not going to be perfect every time. If there is even one outlier in the data, my decision boundary is going to be very wrong. And if my decision boundary is wrong, my predictions will be wrong. So because of these two main reasons, that our expected output is discrete, one yes or no, 0 or 1, but linear regression gives me continuous output. And second problem is that linear regression is very easily affected by this outlier. So we cannot use linear regression for the classification. They sat down and then they thought, okay, these two problems are there. If I'm trying to fix one problem, then the other problem is not fixable. So then what they said, let us create a new type of model which will not be affected by any outlier and which will also give us some kind of yes or no answer. Okay, that is going to do that. Now, see, so these two problems are there, because of which I cannot use my linear regression line, and this is a problem. Now we said that we were making a decision boundary, and we made a decision boundary here. This was my decision boundary. There's a small problem with this kind of decision boundary. When I'm making a very strict decision boundary, there's a small problem with that also. Suppose you are saying 155. What if the patient is very close here and a new patient comes up whose tumor size is 154? Let's suppose from 155, you're starting to say that a person has a serious case of tumor. And then there is 154. There's a patient with 154. So are you going to say for this that this is strictly no? Is this going to make sense that you say it is strictly no? Let's see this with another example. Let's not take tumor size. Let's take an example of sugar level. Sugar level, you will be able to understand better with this, and a diabetes patient. Diabetic or not? Let's see this example. This is much easier to understand. Let's suppose there is a patient again. We have made a decision boundary here. And then we say that if a sugar level of the patient is below this boundary, then they don't have a serious diabetes case. Okay, they're not diabetic. And if a patient has sugar level beyond this, we say that they might have diabetes in the future. We are predicting for that. So suppose the sugar level is again 155 at this point. Can I say for a patient 154, if they have a sugar level, can we say that they are non-diabetic? Is this so easy to identify that if just one value is less, one value is more? Can we have a very strict decision boundary like that? That is also not correct. What about a person who has this much sugar level? So sometimes what can happen is, let's suppose a patient, when they came to the hospital for a checkup, this patient who has this much of sugar level, they came to hospital for the checkup. One day before, they went to some kind of party and they ate some sweet items, little lot. So because of this, one day before they took a lot of sugar content. Because of that, their sugar level is little high, but that does not mean that they are diabetic. Because of something they ate before coming to hospital, that sugar level is showing high because that food item is still there in the body, and because of that, the sugar level is showing high. Does this mean that this patient is having a diabetes case? No, we cannot say that. This is just a patient, a normal patient with little higher sugar level. That is this patient. So this is why we say that we cannot have a very strict boundary for that. We cannot say that any person who has 155 and higher than that is going to be considered as diabetic. This does not work like that. Then it is going to be some kind of very strict case. This is not learning the pattern properly. So our model need to be better than that. So what we do, we bring a concept of probability. Any patient, we will not say that this patient is going to have a tumor, this patient is not going to have a tumor, we will attach a probability with a patient. If a new patient comes up whose tumor size is or sugar level is 163, so we will not say as yes or no, we will just attach a probability that this patient has 80% probability of being diabetic and 20% probability of being non-diabetic. So when we say something in the basis of probability, on the terms of probability, that becomes more dynamic, that is more understandable. So suppose there was this patient who comes up, so we can say for this patient that this patient has 60% case of being diabetic, and this patient had 40% chance of being non-diabetic. So we are leaving room for both of the interpretations. This patient can be diabetic, cannot be diabetic. We are attaching a probability. So if the probability of this patient is little higher, then we can do a certain test to be sure about that. If this patient has a very low probability of being diabetic, then there is no need for that. We can just say there is a low probability. So we represent the terms in the case of probability. That is what happened in logistic regression. Now let us talk about that. I'll tell you a few things, not going to depth of that. I think now it should start to make sense. The doubts which you had before now, I think, seems to be a little clear. So we now say, yes, consider data after, before both. Before is no, after is yes. So we are talking about logistic regression. Let's see. What do we do with logistic regression is this. We do what? We represent the relationship like this, like a S curve. Instead of representing that into the decision boundary or anything like that, we represent that as a S curve. How this S curve they have reached to this point? They've actually taken the help of this linear regression to reach to that S curve. See, there was one more problem happening with this linear regression, which is something related to what we have seen before. Let's say a new patient comes up. What is our expected output in the case of logistic regression? It is either yes or no, or 1 or 0. These are the two numbers, 1 or 0. We are not expecting anything more than 1. We are not expecting anything less than 0. Our expected output is 1 and 0. So now, if I take this patient, where does it touch? It touches the linear line here, and it basically goes beyond 1. Since it is a regression output, it can be any number. It is not going to be between 0 and 1. It can be anything, as we have seen. So suppose this number came out to be 1.7. What is this? This is no, this is yes. So this problem was happening that sometime your output code can go beyond 1 and it can go less than 0. See, if I take a new patient who comes up this is a new patient. What is the patient? What is the output of this patient? According to linear line, we touch upon this here. And this is what? This is a negative output. Some negative, let's say 0.6. Negative output. So the problem with linear regression is that first it gives continuous output. Second problem is that it gives us an output more than 1 and less than 0. That is also a problem. So they said that let us take the help of this linear line and we convert this into this S curve. We convert this into an S curve. This is what we do. So when we convert this into S curve is very dynamic. This is given according to a function. I'll talk about it with a mathematical function. So basically what we do here is this. They created in such a way that you take a linear regression line and you pass it through a mathematical function, which is called sigmoid function. Okay, you take a data. On that data, if you want to make a linear regression line, make a linear regression line. But then that linear regression line, you pass it through a sigmoid function, and then it will be converted to this S curve kind of thing. Do you remember when I was talking about standard normal distribution? There was a normal distribution that I passed through z-score. It became standard normal distribution. So same thing we are doing kind of here also. We are doing the transformation of the data. We take a linear regression line and we are passing through a sigmoid function. It becomes something that can be represented as an S-curve. This is what happens in logistic regression. Why do we do this? Because the answer which we were trying to represent in probability term, that will be given by this S-curve that cannot be given by linear regression. And this S-curve is not affected by outliers present in the data. That is going to be very good, very robust in that.
Just a quick info guys, Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
So I said that linear regression can be used for classification if we define some kind of threshold. The 0.5 threshold that I was talking about, if we are able to define some kind of threshold, so we'll be able to use it for the classification. But even after that, there are two more problems that happen. One, the outliers which are there can affect the best fit line and thus the decision boundary. The decision boundary that we were making is dependent upon the best fit line. So you have to touch the best fit line in that way and you have to make your decision boundary. And the values predicted by linear regression will be continuous, whereas we expect answers in that categorical form. So what we said that, okay, this linear regression, if I apply to a data, which is a classification data, what problem will happen? So I said that if you're training a model, right? And when you're training the model, you applied linear regression to that. So a model will be created. So in this case, what will happen is, suppose you have created this model, you have created this. Now a new data point comes up, which is this much tumor size. And I said that, would you do this with this new data point? How would you find the output of a future input? How would you predict the output of a future input? So I said that if you have a new patient whose tumor size is this much, now you have to identify for this patient whether this patient will belong to the class of no or the group of no, or whether this patient will join the group of yes. We have to decide that. So how do I know? To predict a future output, we have understood the past data, and we have represented a pattern in some form. So we have represented that pattern in the linear regression form. We have created a best fit line for that, and this is our best fit line. So if I use linear regression for prediction for a classification data, linear regression line has been created. So how do I predict the output of this input? What is the way? So I said that you take this data point and you have to touch it on the line. And when you touch it on the line, you touch it here. So it will be some number between 0 to 1, somewhere here it will be a number. Let's suppose 0.6. Similarly, if I take a data point here, a person has come whose tumor size is this much. What will we predict for this person? According to linear line, we just have to touch it. We just have to touch it here, and we have to touch it here. So now, in both the cases, if we see, we can see that the answer we are getting, the prediction answer we are getting is 0.6, 1.4 is a continuous output. So what is our output format in the classification? Our output is in this form. Either it is yes or no, or it is 1 or 0. 1, 0 is the representation of yes or no. So we are expecting an answer either 1 or 0. But what have we got? We have got 1.4 here, 0.6 here. We are expecting not like this. What do I do with 1.4? What do I do with 0.6? So 0.6 is what? I don't understand whether this patient is yes, means he is going to have a brain tumor in the future, yes or no. What do I say about it? So is it possible to say anything about this number by looking at it in this task, classification task? No, we cannot predict any output by looking at these numbers. So I said that, is there a way that these outputs that we are getting can be converted to a categorical output? So we don't get an output like this, we get an output like 1 or 0. Can we do something like this? So now what we said, let's take a line. Line is already there with us. So let's use this line to create something else. We will not have to use this line for prediction purpose. So we said that we already have a linear regression line. So let's put a threshold value here. Let's do something. So I said we take a threshold value 0.5, and this 0.5 we touch it on the line. Okay. Let's touch it on the line. So when I touch the threshold on the line, then what happens? Then you see you have to make a boundary wherever the intersection is happening. Whenever my threshold line is touching the linear regression line, just from there, I have to make a boundary. I have to make a straight line. And I said that this is my decision boundary. Decision boundary. Then what I said, let's take the patient again. Now I have this patient. So when I did not have this decision boundary, when I was just having a linear regression line, so what I had to do, I had to touch this and then touch this. That was what I was doing. Right now what I will do, I don't have to do anything like that. What I have to do, I have to see whether this X value is on the right side of the decision boundary or on the left side of the decision boundary, on the higher side or on the lower side. So where this is present. So this point is of course present on the higher side of the decision boundary, on the right side. So it means that whatever data points fall on the right side of this decision boundary, everything will be considered yes, and everything on this side will be considered no. So that decision boundary works like a point which is dividing the groups. So I said that 155. That is the decision boundary we have found out. That's not a random number. We have actually found out that 155 is a number that can be treated as a threshold. So now what we said, if we have found out that this is the boundary. So what can we say about this? We have created a decision boundary. How we're making a prediction. Let's say a new patient comes up, future. And when we check the tumor size of that patient, I said, let's say their tumor size was found to be 163. Now we have a decision boundary 155 that you can see this one. So what do we say about this patient? 163. We just have to compare 163 with 155. Is it greater? Yes. So if it is greater, it will fall on the right side of this. Yes. Right. If it is less than 155, then no. So we are very easily able to convert a continuous output that was 0.4, 0.6, 1.4, a continuous output. We are now able to convert that to categorical that we needed. So they thought that now it looked like a very good solution. It looked like we can use linear regression for classification tasks. Just we have to do this extra thing. We have to take a threshold 0.5, touch it on the line, we get the decision boundary. And with decision boundary, we can get the answer in 0, 1 or yes and no that we wanted. So now this felt like a very good solution that they have found. So they said that they did some more experimentation with some more data. So now the data they updated some data, maybe they took some other data for different patients in different hospitals. So then what they found out is this, a data which has outlier, because they have to test on extreme cases whether before they use it in the real world. So now there is a data which has an outlier. There's one patient, like this one, two, some patients would be there, who came to the hospital in the very late stage of the tumor. They cannot be saved. They are almost having a critical case of that, a very high critical case of that. So they came to the hospital. Now, so when you have this data here, then what you do, you first have to make a best fit line. Then you have to make a decision boundary. So how do you make that best fit line? So we said that best fit line has that property, it is affected by the outlier. So our best fit line, which should have been like this, now that best fit line is being created like this green one. Why? Because it is being pulled towards the outlier. So our best fit line changes. Our best fit line gets affected. If our best fit line gets affected, then that decision boundary is dependent upon this. So we'll do the same thing again, 0.5. And now we have this here. Okay. And we'll say that we touched upon this point here and we make that. Now, our decision boundary is here. Where it was supposed to be, actually, it was supposed to be somewhere here. This is the correct one. That here it was supposed to be. And you can see that so all the data points are on the right side of this and left side of this of yes and no. That is the correct classification. But what is happening now? We are getting a wrong decision boundary because of this change in the linear regression in our best fit time. So that is a problem now. Why this is a problem? If I talk about the same patient that was having tumor size of 163, right now, so what will happen with this patient? Actually, this patient should be classified as yes, that this person has a serious case of tumor. This should be classified as yes. But what we are saying about this patient, according to new decision boundary, according to new decision boundary, it is on the left side of that, lesser than that boundary. Right. So now this number is, let's say 175. Earlier, the decision boundary was 155. Now it is 175. So it should be treated as yes, but now it will be treated as no. We'll have the answer as no. Isn't that a big disaster if you're doing this? That is a very big disaster if you use this kind of model in the hospitality industry, the medical industry. So that is a very big problem. And because of this reason, those people who were experimenting this, they said that we cannot use linear regression for classification tasks because the decision boundary is working in the case of balanced data. But if we have imbalanced data, then it gets destroyed. It becomes very bad, and the prediction we are going to get will be very bad, very wrong. So that is where they now have the motivation. They now have a clear idea that we have to do something and we have to create a new algorithm. Okay, so that is where the concept of logistic regression came because of these two problems. One, the outlier can affect the best fit boundary. Two, linear regression will be continuous, whereas expected result will be discrete. Now, one more problem was happening, that continuous answer we were getting. Continuous answer also we would have been able to convert that into classification somehow. We would have said that, okay, remove the outlier first from the data, then make the model. These kind of things we could have thought about it if we wanted to fix that problem of outlier. But again, one more issue comes up. That's not a very big issue, but it's a small issue that comes up. So somewhere, if I take a data point for which the line goes beyond this, beyond one, you see, so our minimum answer is 0, maximum answer is 1, 0 or 1. We are expecting that. But sometime for some data point, linear regression also gives us an answer more than one. And for this patient, if I take a patient here, for this, what will be the answer? I have to touch the line here. And this point is below zero. Below zero means somewhere negative, some value negative. So we are getting answers from linear regression line. We are getting answers in negative also, which is less than zero. And we are getting answers more than one. So that becomes very difficult for us to understand that what should I do with this number, which is more than one? What should I do with this number less than zero? Those were also creating problems. That was the third problem with linear regression line. So we said that we have a very good solution of all of that. Linear regression concept, we have already seen, the best fit line concept. Why don't we take this line and pass it through a sigmoid function? That's a mathematical function. Okay. And instead of using this linear line, which linear line has a lot of problems. So let's take the linear line, our best fit line. First, we made a best fit line, and then we pass this through a sigmoid function, and we transformed this linear regression line to something called as S-curve. How do we get the S-curve? S-curve is the property of the sigmoid function. Whenever we use sigmoid function on the data and we plot it, we get S-curve. We are plotting the data and we get an S-curve like this. So now we said that we will not be using linear regression line. Let's take that linear regression line and convert it to an S-curve, which is like this. So now the property of S-curve is that it will never give you answer above 1. It will never give you answer below 0. And also, this S-curve is never affected by outliers. It will be affected very small, little bit, but it is not affected that much that will give you a very big problem in prediction, very incorrect output. So we took the linear line, we converted it to S-curve. S-curve looks like this. What we have to do with the S-curve, we'll talk about it, but that is what we do in logistic regression. Okay, now we talked about one more thing. What was one more thing? That we can also not, if I was using a decision boundary concept, that decision boundary will be made by this sigmoid curve also. But it will not be in the format of like a very strict decision boundary. When I said that in the previous case, that if you have set up a boundary 155, you are saying that anything which is greater than equal to 155 is yes. So we said that we cannot have this kind of strict boundary. That is not going to work in this case. So why we said that? Because if suppose there is a patient this, that is very close to 155, maybe this patient has tumor size of 152, 153, 154. So are we going to say that this patient is belonging to no? Maybe this patient is critical, but they have a small tumor size for now, less than our boundary. Again, I took an example of sugar level. So if a patient has this much of sugar level, can we say that he is non-diabetic just because he has little bit of sugar level less than our decision boundary? So we said that no, we cannot have this kind of strict boundary. That is not going to be correct. There can be a patient who is diabetic, but they have sugar level showing less than our decision boundary, right? So we cannot have this kind of strict boundary. So that kind of problem is also solved by sigmoid function that gives us an output in the form of probabilities. Let's see what. Let us understand about this logistic sigmoid function and whatever it is. Let's see. So the work of sigmoid function is what? The work of sigmoid function is to give you an output in the range of 0, 1. It should not be more than 1, less than 0. That is one thing. And it should not be affected by outlier. Those were the two problems which my linear line was suffering from. So my sigmoid line or the S curve should not be suffering from that. Right. So what we are doing now, when we took the scatter plot, when we took the data for regression, we passed a line through that and we said that this is the line we are going to use for prediction. Same thing we are doing here. We are saying here that we don't use a straight line here. We use a sigmoid function. Right. Same thing we are doing here also. There we used a linear regression line, a best fit line. Here we use a S curve. That is the change that we have done. Now, why did we do that? So we did this because we wanted this. We want output that is between 0 and 1. That is our first motive, what we wanted. Okay. And we need something that is not affected by outliers. And also it should represent the output in probabilistic terms. In probabilistic terms. What is this probabilistic terms? Let's see. So earlier, when we took a new patient whose tumor size was 163. So we said that 163 is greater than 155. So we'll say yes. If a patient is there which is less than 165, 155, then we say no. So we were having a strict boundary. So we said that strict boundary is not very good. It is not going to help us much. So we should have something more dynamic, more generalized, which can be used properly in the real world. Right? Yeah, should not provide definite results because that is not something which is very accurate in the real world. So what we do for this, we use S curve to solve above issues. We use S curve. How do we get the S curve now? We get S curve with this. We use sigmoid function. Sigmoid function. Now, this is the sigmoid function. And what is the formula of the sigmoid function? It's a mathematical formula. Like we have taken beta naught plus beta 1x in that linear regression. Similar to that, there is a formula here also. So the formula is like this. Don't worry about this formula. I'll explain. So it is said Gz is 1 upon E 1 upon 1 plus e to the power of minus z. And this Gz is always between 0 and 1. So this term means the formula is this. The formula is, and we are saying that the Gz that we are going to find is the output, right? This is going to be the output Gz. And how do we find the output? There is a formula to be used 1 upon 1 plus e to the power minus z. That is the formula we are going to use. Where the Gz, the output that we are going to get, will always be greater than 0 and less than 1. 0 and 1 not come, you will not get the answer as 0 ever, and also not 1. It will be somewhere in the between, and then we have to transform it. We'll see how. So Gz, here is the output. And for getting the output, we use the formula 1 upon 1 plus e to the power minus. What is this? What exactly this is doing? Let us simplify this. So what we have in this formula. So now this formula is going to look like this. Z will take the equation of a linear line. The Z here you see, which is this one, it will take some kind of linear line equation and it will convert that into this form. Okay, it is going to convert that into S curve. So what we were talking about, we talked about that a linear line is taken, the best fit line, which is linear regression line, and that is converted to this S curve. How that is done exactly, I'm showing you the formula for that. You know that line is going to be converted to S curve. How? So there is a formula. And how do we convert a line to a curve? So this Z you see is going to take the equation of a linear line and it is going to transform it into a curve. So now the formula looks like this, where we have the Y predicted, the Z, okay, or output you can see, or let's represent as GZ for now, is equal to 1 upon 1 plus e to the power minus beta naught plus beta 1. That is what we said. So we said that first we make a linear regression line, our best fit line, and then we convert that best fit line to a curve, to a S curve. So that is what we are taking here. First, you will have the line which is going to be created. That line gives you a continuous output. So that continuous output will be given here, and that will be converted to a number between 0 to 1. So let us see. Let us see that how is it going to help us exactly. This is the formula we are now going to use. So this sigmoid function takes the equation of a line and converts that line into a S curve. See, if a patient comes up whose tumor size is 163, okay, so if a tumor size is, let's say, 163. For 163, what will my linear regression tell? Linear regression for 163 will give me a continuous output. So that is what will happen? The beta naught plus beta 1 x. Okay, it will be passing through this. So 163 is the x value, and it will be multiplied by some beta naught and some beta 1 will be there, whatever is the line. So whatever is the answer you are going to get is what? What answer you are going to get? That answer might be, let's say, 7.2. Because we are using a linear line, beta naught and beta 1. This beta naught and beta 1 always gives the answer into some continuous. It can be less than 0, more than 1. It can be from minus infinite to plus infinite. Any output can be given by the linear regression. So suppose we have got 7.2. Now we had this problem that 7.2 is yes or no. How do we know that? That we are trying to solve. So whatever I have shown you in a visual format, I am showing you with the formula that how exactly that happens behind the scene. Because there should be some formula which is working to do all of that, which I have told you about. So this thing is my Z. Okay, this answer we have got is my Z, that is my output, the predicted output using the linear regression. So we say that if Z is equal to 7.2, then GZ, we are now transforming this 7.2 into some number between 0 and 1. So we said GZ is equal to 1 upon 1 plus e to the power of minus 7. And the answer we are going to get will be something not exactly 1, but it will be something closer to 1. It will be something which will be closer to 1. Right? Why it is closer to 1? Because you say 1 upon 1 plus e to the power minus 7.2. So this number, e to the power minus 7.2 will become a small number, and the whole denominator, this whole number will become a very small number. Like what we will have, 1 upon 0.0000 something like that. It will be a very small number. And because of that small number, if you divide 1 by a very small number, it is going to be somewhere close to 1. That answer you're going to get will be like 0.9, 0.99, 0.95, which is almost closer to 1. It is not exactly 1, it will be closer to 1. We'll see about that also. Similarly, if a new patient comes up whose tumor size is, let's say, this much. If tumor size of a new patient is what? Is suppose 144. So because of 144, what my linear regression will tell? Linear regression might say that the answer is something in negative, maybe. Okay. Suppose something in negative, it says minus 6.8, and that is my Z, right? That is my Z. That is the predicted output from the linear regression line. So what do we say if Z is minus 6.8? So then what we are doing now? Then this 6.8 is going to be transformed, and it is going to go into this formula 1 upon 1 plus e to the power minus of minus 6.8. So it becomes e to the power of plus 6.8, and it will become a very big number, a very big positive number. It will become, and 1 upon a very big number, the bigger the number is, the closer to 0 it will start to go. It will not be exactly 0, it will be something closer to 0. So now what we are getting for any input that you take, any future input you take for any patient, the tumor size, the sugar level. So you get a continuous output first. Then what you do with that, you take that through this formula, which is GZ, and it will be converted to your S curve, or a number between 0 to 1. So it will not be exactly 0, it will not be exactly 1, because we have to predict the answer in probability terms. But it will be closer to 0, it will be closer to 1, something like that. Now, what we have said, that we have Z is equal to beta naught plus beta 1x. We were using this first. Wait for a few minutes, you will understand what I did. Right, so I had this. What I do with this, I take it through the sigmoid function. And when I take this equation through the sigmoid function, I get this function as gz is equal to 1 upon 1 plus e to the power of minus z. Then what I get output between 0 to 1. We took a linear regression, an output which is given from a linear regression line. This Z is an output which is given by the linear regression line, like 1.5, 7.2, 10.9, 100.6, whatever you get, that is in a continuous form. That is Z. So you take that Z and you take it through the sigmoid function, which is this formula, Gz is equal to 1 upon this. So that continuous output, when passed through the sigmoid function, is transformed between a number from 0 to 1. It is being transformed. So what we are transforming, 7.2 we have taken, that is the continuous output passing through this function, 1 plus minus 7.2. So it becomes somewhere between 0 to 1. Some number between 0 to 1, which is 7.2. That is what we are getting. Now, right. So let us see what exactly you're going to get. You're not going to get exactly 0 and 1. You'll get something between 0 and 1. Now, is it making sense till this much, what we have done? Whatever I have explained it to you, that I'm just talking about in the formula terms. Okay, yes. So now, how do we interpret the result of logistic regression? That is now I'm going to talk about that probabilistic terms. Let's see. Okay. Now we have interpretation of logistic regression out. Okay, logistic regression out. So what have we seen at this point? We have seen that there is a formula which is GZ, that is the output, and it is the output is found out using this formula 1 plus e to the power minus n. Now this formula, what does this do? This formula actually gives us output in the formula, gives us gives us the output as the probability that you will understand where that 0.5 fits into this threshold. How do we make use of that threshold? So this formula gives us the output as the probability that the class of the data, that the class of the data point is 0 or 1. Okay. So we get the answer as probability. So what I said now is the answer we will get from this is going to be somewhere closer to 1 or somewhere closer to 0. But it is not that it will be closer to 0, closer to 1. It might be somewhere 0.5, 0.6. But always the output that you're going to get with the sigmoid function will be some number between 0 and 1. Always. So now let's suppose for this patient, which was 163, we don't get an answer as closer to 1. Suppose if I write the exact answer to represent it, let's suppose we get 0.8. And this thing we will get as, since it was closer to 0, so it might be, let's suppose, 0.1. Now, we had this answer 7.2 before, we had this answer which was a negative, but those two things have been converted into a number between 0 and 1. This is 0.8, this is 0.1. Now, can you say what is this? This is the probability of a patient falling into class of 1. Probability of a patient falling into class of 1. Class of 1 means the group of yes. What does the 0.8 means? So a person who has a tumor size of 163, they have a 80% probability or 80% chance that they will have a tumor in the future. We are now representing this patient who has a tumor size of 163 with the probability, 80% probability of having a critical tumor. What we are saying about this patient, 144. So 144 is a smaller number. Now, with this 144, we got an answer as 0.1. We got this 0.1. So when we got this 0.1, what we are saying that there is 10% probability of this patient having tumor. We are not saying that this patient is completely no. You can never say that a person is not going to have this disease in the future. Maybe this person goes and have the tumor because they have some kind of tumor, right, in their brain. So there is still a possibility that they might have this disease in the future. But the probability is very less because they have a very small tumor size that can be treated when they have come to hospital. So we are saying for this patient, which is having tumor size of 144, for this patient, we got the answer as 0.1. We have got this answer. With this formula, we are not making anything from our side. So how do we read this 0.1? 0.1 means that there is a 10% probability that this patient is going to have tumor, 10% probability. That's very less. So we can say that he might not have the tumor. So every time when we represent something, we represent that in the probabilistic terms. And that is what we do in logistic regression. That is how logistic regression works. Right. So this is the formula of that. I hope now it is making sense. So let me talk about the last thing from this. Where does that 0.5 comes in? So 0.5 comes in here. As I told you, any number, any future input you take, tumor size or sugar level, so you will always get an answer between 0 to 1, always. So suppose I have got, for one patient, I got 0.8. For one patient, I got 0.1. What is the boundary? Right? What is the boundary above which I will say that he must be given a treatment and below this person is not does not require a treatment of now. He can have a treatment later. What is that boundary? What is that percentage? Above 50% will say, or above 60% will say. So we decide that criteria, right? The common answer is we decide a criteria which is that 0.5. 0.5, which I was talking about, that is the criteria we decide. That what? If the patient's probability is 0.5 and more than that. Now you can see, we have put up a criteria, a threshold in the middle, that if a patient is having greater than equal to 0.5, if the output, the GZ value, if it comes 0.5 or more, we will say that for this patient, since this patient has more than 50% probability of getting a tumor, so this person should be treated as yes, and this person should be given a treatment, because now there is more than 50% possibility that this person might have a disease. Right now, we don't, this number is not fixed. 0.5 is not fixed. We can change this number. Suppose we are talking about cancer patients now. Tumor is something which can be treated at a later stage also. If some kind of misclassification happens, then also it can be treated. But now, what we have about a cancer patient, you all know that cancer is a very, you can say, deadly disease. And also the cost of treatment is very high. Very few people who have the signs of cancer can get treated. Very few people can afford that much of amount. It is around like 5 lakh, 10 lakh rupees per day. So no one, not everyone can afford that kind of treatment. So in that, saying every person has 50% and more, they should be getting treated, that is not what we can say in that case. So there we will have to make a boundary which is around 0.7 or 0.75. We need to be very sure, we should have a very high probability of that patient to say that this patient should get a treatment. So we can change the decision boundary based upon how critical a case is or how normal a case is in that scenario. So we don't go beyond less than 0.5. That is not where we go. In the normal term, if you're talking about anything which is not very critical, let's say you're talking about whether a person should be given a loan or not, whether a transaction is fraud or not. These are all classification problems. So these are something which is not going to take someone's life. If you give a person who has more than 50% probability of returning the money, you can give them loan. If they don't return money, then you're not going to have something which can kill you. You might have a loss, a bank might have a loss. That's okay. That's a part of the business. So we can give the loan to a person who has 50% or higher probability of returning the money. Understand? But in the case of such kind of critical cases where you know that cancer treatment is very expensive, so if you say about a person that this person might have more than 50% probability of, or let's say this person has 55% probability of having cancer. So saying to this person that you should get treated is going to be very difficult, should not be done because it's a very expensive one. So that is why what we say is 0.7, we say a high probability, a high threshold we put up. So if any patient is more than 70%, is having more than 70% probability of having cancer, it means that now some serious signs are showing up. Then this patient might be serious. So he can go to some kind of treatment. Yes, Nitin, this topic is subjective. Your team, when a team is working on some kind of project, they have to decide it according to their domain understanding, according to the importance of the task at hand. If you're taking some business decisions which are very, very critical, that can kind of hurt your company a lot, then you change these threshold values. Okay, perfect till now. So here we have basically completed the theoretical concept of logistic regression. See, linear regression is different thing, logistic regression is different. You cannot say both will do the same thing. Stock prediction is a linear regression task, and S-curve does not talk about stock price prediction, right? Stock price prediction is a continuous. When you want answer in continuous, you go with linear regression. When you want answer in yes and no, then you go with logistic. They both are different. Now, what about the outlier? So outlier is such a way that suppose now I have the outlier. Then what? So S-curve is such that it is not affected by outlier. Why? Because you see, there was this best fit line, and when you get this outlier here, when you get this outlier here, then this best fit line is shifting towards this, will become this. Outlier has a property that it attracts the best fit line towards itself, and that is the problem with linear regression line. We were solving this problem also. So what we said, we took this linear regression line and we converted to S-curve, which is not affected by outliers. So when I take, suppose, this outlier, do you think I need to change my S-curve anything at all? Do you think there is a requirement of changing the S-curve? What we are saying about the S-curve, you see the boundary of 1 is above the S-curve. So if you see, we extend that S-curve also, then outlier is above that. Now S-curve need not be changed, since any point you take is going to be above the S-curve, and S-curve is going to identify everything with that. There's no requirement of changing the S-curve, right? If you have any value, which is a very small value, and you know that it is below this part, this S-curve tail that you have, it is below that. So you don't need to change the S-curve in the case of outliers that you're getting. So it is kind of thought it like that, that you stretch it and the points are above that and it is below that. Got it? That is why S-curve need not be changed. Now, so what do we have here is we got that S-curve and it is not affected by outlier. It gives us, limit is 0 to 1. That is what its values are, 0 to 1, greater than 0, less than 1. It does not touch 1, it does not touch 0. So whenever you make S-curve,
Let's have a quick quiz question, guys. And the question is, what does the term precision refer to in binary classification? And your options are the ratio of true positive predictions to all positive predictions, or the ratio of true positive predictions to true negative predictions, or the ratio of true positive predictions to all actual positive instances, or the ratio of true negative predictions to all negative predictions. Please mention your answers in the comment section below.
Just a quick info, guys. Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
S-curve is such that there is a line of 1 if you see. Okay, there is this line of 1, which is like this. So S-curve will be created in such a way that it does not touch the line of 1. It is less than that, just very close to that. And the tail of this S-curve will also be not touching the line of 0. That is why we said that the output of the sigmoid function is greater than 0 and less than 1. It is not greater than equal to 0 or equal to 1. It is the property of sigmoid function. It is a mathematical function, and it is the property of the sigmoid function that it does not give you answer in 0 and 1. So why is it helping us? Why are we taking such a sigmoid function which is not giving 0 and 1? So this gives you a probability. So we think about that. Let's say a person is having 128 tumor size. So for this person also, we never say that there is a 0% probability. We never say that we have a 0% probability for a person to have a tumor. Nothing is 0%. Okay, that he's never going to have tumor. He might have a tumor. That is why we represent something. We might represent 1%. That's okay. But we still leave some room for something that he might have a tumor in the future. So we assign, currently we don't see any signs of that. So we can assign a very small probability, but it will not be 0. That is why this kind of thing has been used, and we represent it in this. So GZ is not our answer. We take the threshold, we compare with the threshold. And if it is lesser than threshold, no. Greater than threshold, yes, but with a probability. There's a concept of best S curve. There's a concept of best S curve. S curve can also be created in a very different ways. So we have to do something to find out best S curve. What exactly is best S curve? What does it do for us? We are going to talk about that. That's a, if someone is going to ask you any question in logistic regression, there is a very high probability that they will be asking about this, because everyone knows that sigmoid function, everyone knows what is happening. A continuous output is converted into categorical with a probability that everyone can answer. But how that S curve is created, that is very important to understand. The questions might come from this high possibility. So let us talk about this now. What is the best S curve that I'm talking about? They are not ignored in SF. They are what if any outlier comes up. Any outlier is what? Let's suppose a new patient comes up, or any patient who is there who has a very high tumor size, 209. Okay, which is a very big tumor size as compared to what we were seeing before. We were talking about 165, 143. But there is a new patient who is having tumor size of 209. What we do with that? For 209, we'll get a continuous output. Let's say the output comes out to be 43.2. That is what my linear regression says for this person. So I just have to give this 43.2 to what? To this equation, minus 43.2. What will happen with this? You're going to get a number which is going to be like 0.98 or 99, which is going to be very high number. Since you are dividing 1 upon this number will become very small, because e to the power minus this will be a very small, very big negative number. And when you take that and you say 1 plus this, you will have a very small number, this total. So when you have this very small number, 1 upon a very small number becomes closer to 1, 98.9. So are you able to handle an outlier and you're able to get the answer in probabilistic terms? So the property of sigmoid function is such that even if outliers come, you will be able to handle that in a very easy sense. Okay, you will be able to handle that easily. Correct? Okay. Now, so the concept of best S curve, let me talk about that. Then you will have a little bit more idea about this. Now, what we have in this equation, we have this 1 upon is equal to 1 upon 1 plus e to the power of minus z. We have something like this in the equation. So this z was taking what? This z was basically nothing but 1 upon e to the power of minus beta naught and beta 1 x. Right. So I'm explaining you for one input, x, like the sugar level. The diabetic patient might have other conditions, right? The blood pressure, the cholesterol level, we can check multiple things. So this equation will simply take a form of beta naught plus beta 1x1 plus beta 2x2 plus beta 3x3. So I'm just explaining you now for a simple case where I have one input. So that is why I have written beta naught plus beta 1x. I'll write that also, but let us understand with this. So we have the beta naught and beta 1 in this equation, which is actually giving me the answer of S curve. So now what happens is, if we change beta naught and beta 1. Then S curve also changes, right? If we change the beta naught and beta 1, then S curve also changes. Because the S curve we are making is according to a line, right? We took the help of the best fit line and we made the S curve. Suppose I change the beta naught and beta 1. First, we had a line. So if I had a line, it must be having some beta naught and beta 1. It must be having some equation in the form of beta naught plus beta 1x. So that was a line, and we took that line to make a S curve. So according to a certain line, a certain type of S curve was created. But if I change this line from this to suppose this, then what will happen to that? The beta naught and beta 1 changes. Earlier, for this, the beta naught and beta 1 would have been different. And for this, the beta naught and beta 1 would be different. So an S curve which is going to be created according to this line will be different, will not be exactly same as that the previous one. So in basic, you have to understand that the S curve is dependent upon beta naught and beta 1 values. If I change or if I modify the beta naught and beta 1 values, my S curve changes. If my S curve changes, the probabilities that I get changes. And sometimes it becomes good, sometimes it becomes bad. Let us see what I'm talking about. Now, so just showing you example of it. So suppose an S curve look like this. Sometimes what can happen if you are taking a bad S curve, which is bad. So it might also look like this. It might look like something like this. Okay, it should be something like this. Curve, you're having a top here, then we have a tail kind of thing. It should look like this, which you're seeing in the blue color. But sometimes it might happen that it looks like this. Sometimes it might even also happen that it looks like this. Okay, very bad as well. Sometimes it can even look like this, which is at a very low level. Actually, it should be at this blue level. But these type of S curves also you might see, which does not look like S curve, but essentially it is an S curve. So which one is best out of that? The blue one, which you see, is the best out of that. We should try our best to get a S curve like that. That is how an actual S curve is like. Then it will perform best. But if you have taken any beta naught and beta 1 values, which is creating either this type of S curve or this type of S curve or this type of S curve, that is bad. So we need to change the beta naught and beta 1 values and keep updating it until we get the best S curve. So how do we reach to that point? Okay, how do we reach to that point? So to reach to that point, there is a very interesting concept given here. That is this. Okay, why it is showing like that? It is that line goes till infinity. So it is said that it touches the line of 1 at infinity, somewhere at a very high value. That is why it is shown touching, but it does not touch it. So what we have is, if we change the beta naught and beta 1, then the S curve also changes. So how do we know what is that exact beta naught and beta 1? In the linear regression, we had the gradient descent, which was helping for us. So gradient descent says that start the beta naught and beta 1 at 0 and 0, then keep updating it till you get your best one. What we do here, we have a concept of maximum likelihood estimation. What is that? Let us see. We have this. So what are we talking about? We are talking about, let's say, the diabetes case. That will be easy to understand. Now, what do we have on this side? We have probability, let's say probability of diabetes. Okay, probability of diabetes. And then on this side, we have the blood sugar level. Blood sugar level. So now we have what? There will be 0 here, 0.0, say, and then we have 0.25, then we have 0.5, then we have 0.75. I'm just breaking down that 0 and 1 into more intervals for ease of understanding. 1.0. Now, what do we have here is there will be a line at this point. Now you can think of that there is a line at 1. See, now how our best fit line should be created. We're taking the blood sugar levels on the bottom side. So if I start from, let's say, there is a 0 at this point, and suppose I say 50, 100, 150, 200. See, I'm not talking about the actual sugar level. This is just an explanation for that. So if sugar level does not exist beyond some number, don't worry about it. Just an idea. So suppose the sugar level of the patients are something like that. There's a data which we have. In that data, we have found out that the sugar level maximum was found out somewhere around 300. So your range will be like that. And the probability of diabetes is something like this. Now, what do we do to solve this case? We have understood about the S-curve. So how the S-curve will be created? There can be one S-curve that goes like this. And then there can be an S-curve which is actually like this. How do we tell to the logistic regression? Logistic regression is just a mathematical, it's just a function, it's just a code. And that code has to make this kind of line. So how does it know that how a S-curve has to be created? So it should be created like this or this. Both look like an S-curve, but which one is better? How do we know that? So there comes the concept of, we use the concept of, maximum likelihood. This maximum likelihood. What does this maximum likelihood does? It's a very interesting concept. And this concept says that we will be using some kind of likelihood to get our answer. What does it say? So an S-curve should be created in such a way that there should be something like this. Let's see. So if I suppose have a patient, there's a patient here, there's a patient here, there's a patient here, there's a patient here, there's a patient here. We have these kind of patients. And suppose we have a patient here, have a patient here, we have a patient here, we have a patient here, and we have a patient here. Now, there can be some patient of class 1 here also. There can be some patient whose sugar level is very low, but they are diabetic. There can be some kind of like that. Now, how exactly we make a sigmoid function is like this, right? Yes, outlier, you can say. How exactly we make this S-curve? What is the property of that? So we talk about something called as likelihood maximization. Likelihood maximization says that if there is some patient, right? If there is some patient who is having a chance of having a diabetes, who has a probability of, or you can say who has a more inclination towards being diabetic. So we should attach a higher probability to that patient, right? If I'm talking about this person, or if I'm talking about, let's say, any new person, this is that person, right? So the middle point is somewhere like this. Just think of a boundary as of now to understand it easily. Let's say the boundary is at 200. We don't use it something like this, but let's suppose I'm using it to explain it to you. Let's suppose the boundary is at 200. 200 and less than 200, we give a possibility of no, and above 200, we give a possibility of yes. So this patient who has the sugar level more than 250, around 255 or something, what should happen with this patient? Should this patient be going to yes or no? We know that clearly that it is a very big number as compared to the boundary. And this person should be given a very high probability of being diabetic. Then we are doing a good classification. If I say for this patient 0.6, is that better? Or if I say 0.87 for this patient, is that better? For this patient, he is quite away from the 200. He is around 265 to something like that. Then what we are doing with this patient? Since it is very far away from the threshold value, above 200 is the threshold value. If you're talking about that, so should this patient have a 0.6 probability of 0 or 0.87? This person should be given as much higher probability as possible. So we create an S curve which gives it a higher probability. Right. Now, let me just make another S curve and then explain it to you. Let's suppose there is this S curve. Yes, we should try to be closer to 1 or 0. Yes, perfect. We should try our best to get a number which is either closer to 0 or closer to 1. That is the best type of classification. Let's see. If I talk about this patient and I'm using this S curve, what will happen this patient with this S curve? You touch it here and it will be somewhere here. So according to this S curve, what is the probability coming for this? Around 0.45. For this patient, according to this S curve, the probability comes out to be 45%. But same for this same patient, if I just stretch it and I touch it on this line, what is the probability coming up? It is coming up to be somewhere around 0.8. What do you think now? Where we are doing a proper classification of that patient? This patient, we know the patient is this one. This patient is very far away from 200. So which S curve? This is also an S curve, 1, and this is also an S curve. Which S curve do you think is doing a good classification in this case? The curve number 2, because the curve number 2 is attaching a higher probability to this patient, which should happen, which we should do to get a perfect answer, to get a proper answer. So that is what we will have to do. That is why out of all the S curves possible, we should take an S curve which is attaching as higher probability to a patient who is going to have a tumor. All this pattern is going to be learned by logistic regression. You don't have to make this S curve and anything like that. But in the interview, it is going to be asked, how do you decide which S curve is better? Is this S curve better? Is this S curve better? How do you decide that? So we decide it on the basis of likelihood maximization. Likelihood maximization says that for this patient, we are saying 80% probability, that there is a likelihood of 80%. Likelihood means probability. There's an 80% probability that this patient is going to have tumor or diabetes with this S curve, but here we only have 45% probability. So whichever S curve is going to maximize the probability for a patient, we do that. We take that S curve. So for all the diabetic patient, it should give a very higher probability. And for all the non-diabetic patient, it should give a very less probability. Both things should happen. Right. Now, let's talk about one more case. I talked about the higher cases, right? Let's see for a patient who has smaller case. Let's see if a S curve is this. This is also S curve. Now, suppose if I have a patient, a new patient I'm talking about, and this new patient is, let's say, somewhere here. This is my new patient. So which line do you think is doing better in this case to classify this patient? Whether this patient should have diabetes or is this patient not going to have diabetes? Which one is predicting better? See, you know that this patient who is somewhere here around 55 or 60, something like that, this patient have a sugar level of 55, 60. That's very lesser than 200. So it is very obvious that this person is not diabetic since their sugar level is very low, not diabetic. So now, according to my line number 2 and curve number 1, curve number 2, according to both of them, which one is doing a better task? So for this patient, we know we should be giving a very low probability. Since this person has a very less chance of having a diabetes, so we should have a very less probability for this patient. Which line is doing it better? See, if I take on this black one, it is giving it a probability of somewhere around 0.10. But if I talk about this line on this S curve, it will give me a probability of what? 0.20. Which one is doing better task? So my S curve is saying that this person has 10% possibility of having diabetes, but my curve number 1, which is the blue curve, is telling there is a 20% possibility of this person having diabetes. So you understand, for a person who is not diabetic, who is very safe, they should be given as lesser possibilities as possible. That is what our best S curve will be. So we have to maximize the estimations. So we have to give as lesser possible for a non-diabetic patient, and we should be giving as higher probability as possible for a diabetic patient. That will be very easy estimation to be done. Is it making sense at this point? Yes, exactly. So it should have a steep curve according to this. Now, let us see. What happens when something is closer to that? What happens if a person is closer to this, according to this? Suppose I'm talking about a patient who is here. So if a patient who is here, then which line? This line is going to attach a probability, which is this, which is around 0.6, and we use it like that. So there is no issue with that. How do we make a best S curve? Is we study the past data, we study the previous patient, and in the previous patient case, we have seen that these are the patients who have very low blood sugar level, and it was observed that they did not have diabetes. And this patient who had a very high sugar level, they had diabetes, we studied those patients. And by studying those patients, we represented the pattern in this S curve, which is very good. So what essentially we are doing, if I'm talking about this point, so this patient was here, then this patient was here, this patient was here, this patient was, all of these patients were here, they have been classified as class 1 and they have been put here. So what we do basically is we do this. Let me explain about it. To summarize what we have talked about is this. All right. So now for this X, the possibility for this X, the possibility should be this much. For this X, the possibility should be this much. Now, this is what you can say that these are the possibilities of these data point of being in the class 1. That is why I put that. I have put this data point. Why I have put that data point in class of 1 or class of yes, 1.0 means yes. Why I have put it up? Because there was a very high probability of this point, and the probability was somewhere around 0.8 and higher than that. There was this kind of probability. That is why I have put this data point, this X, into the class of 1. Right? Now, what we do here, we do the maximization of this. Also, what we have to do, we have to do minimization of this. This, and this. We should be minimizing the red lines and we should be maximizing the green lines. Correct? Now, why I'm saying that? See, if I make a curve like this, according to the black one, you see the lines are very higher. But according to the blue ones, will it be same height? No. The possibilities will be like this. Till here, till here, till here, which is like attaching a very small probability to a patient who has a higher sugar level. So what we do now, we make a S-curve like that in such a way that these green lines which I have made should be maximized, should be as tall as possible. When it will be as tall as possible, when this point of the S-curve touches or goes very close to the 1, then only it will be maximized, these buildings, these green lines, right? And similarly, the red ones we have to minimize. How will we minimize those red lines? When our tail is touching the 1, it is not exactly on 0. When it is touching the 0, then it is going to minimize those red lines. Can we say that? Are you getting this idea? What I'm saying is we should maximize these lines and we should minimize these lines. We should maximizing what? We are basically maximizing the probability of a person to have diabetes. So this is the line here, it is touching for this particular data point. This much is the probability, which is very high. And for the other data point, for the other patient, it is even higher. So we have to maximize this and we should be minimizing these lines. Now, can we say that if I want to minimize these red lines, then we should be maximizing this? If I say this much, just understand this, I'll repeat it multiple times, don't worry. Okay. Now, can I say that by maximizing these green lines, the red line which is at the bottom will be automatically minimized if I maximize the green ones here? Will they be automatically minimized? Can we say that? Yes? Correct? So obviously this is going to minimize. So if I'm just doing that, make these lines as tall as possible. So what will happen? To make these lines as tall as possible, these red lines have to become smaller. So when we are trying to maximize these lines, the red lines which is at the bottom will automatically be minimized. Why we are talking about this? Why I'm talking about this reverse thing? So that I can put it into some kind of formula. Let's see what. Let me explain that to you and you will understand. So let's say this was, let's say all of these red lines that you see, let's say this is the probability. The probability of this patient having a diabetes is very less, 0.1, 0.12, 0.13, 0.15, like that. So that is the probability of the red lines. So can they be represented as P1, P2, P3, P4, P5? So I'm saying that this line should be given P5, this line should be given P4, this line should be given P3, P2, P1. Right? That is the possibility. The height of the red line is the possibility. So I'm attaching that P5, P4, P3, P2, P1. If this is P5, if this red portion is P5, probability 5, can I say this green portion for P5 will be 1 minus P5? If the possibility of X to have diabetes is 10%, can I say the possibility of having no is 90% for this person? 1 minus P5. Similarly, for this line also, we can say it is 1 minus P4. And 1 minus P3, 1 minus P2, 1 minus P1. Why I'm representing in this terms is like this. And similarly for this, I can say it is P6, probability 7, probability 8, probability 9, probability 10. 10 values are. So these P1 to P5 we are minimizing, but P6 to P10 we are maximizing. So I can't represent something in both terms, minimizing also, maximizing also. So what we do, we represent everything as maximizing. That is why I've written that. Let's see. Let me write that final thing and it will be clear. So the best S-curve, yes. Yeah, you must have got it. So the best S-curve will be the one. Yes, either we can maximize or we can minimize, both things we can do. Will be the one that maximize. But we talk about the maximizing case. That is what has been discussed in logistic regression. That maximizes. That is why maximum likelihood you are talking about. We try to maximize. Minimize also you can do, but that has not been done in logistic regression. So we need to do this. We need to maximize this. 1 minus P1 into 1 minus P2 into 1 minus P3 into 1 minus P4 into 1 minus P5 into P6 into P7 into P8 into P9 to P10. This is what we need to maximize. 1 minus P1, 1 minus P2, 1 minus P3, 1 minus P4, 1 minus P5. They will all have the probability. Let's say 1 minus P1 is 0.7. If P1 is what? This P1 is this red line. If you see here, P1 is what? See, this height that you're seeing for this X data point, the P1 is this much, which is, let's say, 0.1. So if P1 is 0.1, what will be 1 minus P1? 0.9. Similarly, if P2 is, let's say, 0.12, this line is, let's say, 0.12, means 12% possibility that this person is going to have diabetes. What will be the 1 minus P2? 1 minus 0.12. That will be 0.88. So similar to that, when we are talking about 1 minus P1, 1 minus P2, 1 minus P3, 1 minus P4, and the P6, P7, P8, P9, P10. When we maximize this, whatever number we are going to get, that will be our best S-curve. So if 3 S-curves are there, and whichever S-curve is maximizing this. So the final answer is this. Suppose I have an S-curve like this, and suppose there is an S-curve like this, and suppose there is an S-curve like this. Which one is better? 1, 2, 3. So out of these 3 S-curve, there is a, which one maximizes this probability? So what we do now, we will have to make many S-curve and see which S-curve is actually maximizing the likelihood of that. We need to talk about this. So whichever S-curve is maximizing this. So same thing comes up here. In the linear regression, we were making many lines and comparing which one is giving least total error. But here what we talk about, we make many S-curves and then we see which S-curve is exactly maximizing that likelihood. The first one, the second one, the third one, 100th one, 200th one. So there we were making like 700 and 1000 lines. Here we will have to do the same thing by making 700 S-curve, 1000 S-curves like that. Then here also what happens, there comes the gradient descent. Gradient descent is applied with logistic regression. It says that don't make 700 S-curve and compare that. I'll tell you something that using which you can get the S-curve easily. Why we are using gradient descent here? Because an S-curve is dependent upon beta naught and beta 1. Right? Beta naught and beta 1 is the value on which the S-curve is dependent. So that optimal value of beta naught and beta 1 is best calculated with gradient descent concept. That is what we have seen. Right. So that is the final concept. You go through this video, understand this. Any question, you come back, I'll be talking about it. But if you look at this explanation, you will not have any single doubt whatsoever anytime. So we have understood the logistic regression at this point. Okay. Now, so logistic regression, remember one thing, it is used for binary classification. It is used for binary classification mostly. It can be used for multi-class classification, but it is used for binary classification, where the answer is yes or no. Okay, now it is used for binary classification, which is yes or no. If you are talking about multi-class means yes, no, maybe, or any example of multi-class would be. So in the case of multi-class classification, we don't use the logistic regression. That does not give us the best answer. So for multi-class classification, we use either decision tree or random forest. These are some of the advanced algorithms which we'll be talking about in next week. So they will better perform in the case of multi-class classification. Multi-class means whenever your output is more than 2. If your output is yes and no, then logistic regression can work well. But if you are dealing with yes, no, maybe, or 3 outputs are there, 4 possible outputs are there, then you use decision tree random forest for that. We don't generally use logistic regression in that cases. Now, so can we have multiple inputs? Now, in the case of multiple input, how will that formula change? So suppose you have 4 input columns. We have x1 input, we have x2 input, we have x3 input, we have x4 input. So what will happen with that? You will just, your formula will be just like this. 1/1 plus e to the power of minus beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 and plus beta 4. It will just change like that. Okay, and what do you need to do? This particular thing will give you a continuous output. Take that continuous output, put into this formula. It will just convert that to a number between 0 to 1. That is the probability. Perfect. Okay. So now we have 10 minutes remaining with us. I'll not go into anything of depth as of now. But let me talk about this, the project question. Just a basic practical implementation of that I'm going to talk about. So it will be better if you study 2 times. Now, what we have here, we are just importing some packages. Don't worry about it. We'll see. The first is NumPy, then we have pandas, and then some sklearn, something like that. So there is a, what is this sklearn? Sklearn is the name of the package. Like matplotlib, Seaborn, pandas, NumPy was there. So for machine learning, we have this package which is called scikit-learn, which is my scikit-learn. So scikit-learn is said or written as sklearn in a short form. That is the name of the package. So this scikit-learn package has all the implementations. Whatever algorithm we are going to study, you have the code for that written inside this package. So you can use the code and you can do your task. That is why you don't have to write the code from scratch about implementing everything. So whatever I've explained in logistic regression, if I say you to implement that, you write the code for implementing all the logic, like a line is taken, converted to S curve, represented in possibilities, then there is a 0.5 you need to take as a threshold value. Compare that. If you have to write a logic for all of that, it will be very difficult. Most of you won't be able to write if you don't have a very strong programming background. That is why they have been written for you so that you can use them. Now, so 3 functions we are using from the sklearn package: the train, test, split, logistic regression, accuracy score. Let's see where do we use it. So first, I am going to show you the example of a heart disease prediction data. Take a look, you will understand it. I'll talk about it once again. So we have a heart data, we check the head of it, you check the tail of it, everything is easily understandable. The shape, the info, the missing value, if there is any missing value, describe whether you have outlier and everything. So about outlier also, I'll discuss what you have to do if you see outliers in the data. Talk about it. But for now, we have this thing. Now something new starts from here. Whenever you're talking about the classification problem, there are two types of data sets that you will get. A balanced data. Balanced data does not in the terms of outlier, not outlier. That is not I'm talking about. But balanced data and imbalanced data, what they are. This is one very common thing which you will see in the case of the classification task. So in classification task, let's suppose we have taken the we have the data for multiple patients. So suppose we have the data for 500 patients. We have collected the data. What we should have to make a good model that can do a very good prediction, what we should do is we should take 250 non-heart disease patient and 250 heart disease patient. That is what we should take. So we can understand properly what all things lead to a heart disease and what are all the conditions which show no heart disease. So we should have equal number of data points for both the classes, for both the outcomes. That is what our training data should be. But so balanced data would be like 250 patients for no heart disease, NHD, no heart disease, and 250 patients for heart disease. That is what a balanced data would look like, balanced training data. But there will be a lot of places where you will have imbalanced data. What is this? So imbalanced data means you have taken only 50 non or heart disease patient, and you have taken 450 non-heart disease patient. Now, this becomes a small problem. You have a lot of examples. You're giving a lot of example to your machine learning to understand the pattern of non-heart disease, but you're giving very few examples to learn about the heart disease patterns. So this is called imbalanced data. And we need to find out this, whether the data is balanced or not, because based upon that, we need to do some modifications. What? We'll be talking about that in the next week, and it is going to be very interesting. So this is imbalanced data, balanced data. What after that? Can you tell me any use case where you are going to get a imbalanced data? Always, no matter what you do, you will always have the imbalanced data. Can you tell me some examples of that? What kind of problem you're going to solve where you will always see imbalanced data no matter what you do? Can we say there is a problem of credit card fraud detection? Will this have imbalanced data or not? Yes. Why? Because suppose any company wants to do fraud detection. Suppose Amazon is a platform where some kind of fraud happened in some of the transactions. Transaction means one person came to Amazon, they purchased something, second customer came, purchased something. Whenever a purchase happens, that is a transaction. So in that, suppose in 1 month, 150,000 people are making purchases on Amazon. In 1 month, 150,000 customers are making purchases. So out of this 150,000, there might be only 100 people, or there might be only 100 transactions which are fraud, but there will be 149,900 which will be not fraud. Is it understandable that on any platform the fraud happens is not even 1%? It is like 0.1% of that, 0.2% of that. The fraud transactions are very less, and you cannot do anything like that. Can you say to a platform that more fraud should happen on our platform? Of course not. So whenever a data you're talking about, any month, any year, the fraud transactions will be very less as compared to the non-fraud. So this is a case of heavily imbalanced data, not just imbalanced. It is the case of heavily imbalanced. Getting it? So when I have this kind of problem, I need to take care of something in this case. I cannot just apply the algorithm directly. I need to take care of something. So we'll be talking about this. So somewhere in the classification, the balanced and imbalanced data, we need to take into consideration. We should identify that. In the practical case, the imbalanced data problems will be there. Similarly, if you're talking about cancer prediction, okay, cancer prediction. So for cancer prediction also, the patients who will have cancer will be very less, and the patient who don't have cancer will be a lot in any hospital if you talk about. So balanced data is also a part of the data sets. It is the part of the industry, and in many industry that happens. In finance, in medical, in pharmaceuticals, every industry has the case of both the balanced data and the imbalanced data. But we check the imbalanced using this value count. So you take the output column from the data frame and you check the dot value count. So it will tell you that how many examples of both the classes you have. 1 means yes, 0 means no.
Just a quick info guys, Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
Okay, so now we will start. You don't need to write the code for now. You can write the code later. First, try to understand it very properly. The code is given to you. Try to run that for now. Later, you have this. Just follow this, and you'll be okay. So I'm going to talk about few things to make it clear what is logistic regression and what are the things you need to understand in classification tasks. Okay, now, so we were talking about some classification tasks. And the first algorithm we talked about is the logistic regression in that. Now, logistic regression, we understood properly how does that work. The explanation I've given for the logistic regression is the easiest and the best understandable explanation I've given. So if you just go through that once after I've taught it, you'll be able to remember everything. You can even explain it to someone. It is very easy explanation that I've given. Just go through it once, and if you want to write, you can have a notebook in front of you with you, and you can write down the things in your own way in a rough manner, just for you to remember it once. Now, these things are, see, one thing I'll say, when you remember any algorithm, you will be forgetting it multiple times. So you need to keep practicing it maybe every 10 days or 12 days. You just have to look at it once so that you don't forget it completely. And that happens in all the fields, not just in machine learning. When you're learning software engineering, there are some concepts of data structures, algorithms. You forget that also when you're preparing it. So in ML also, you will be forgetting the algorithm, how it was working and what were all the concepts in it. So you need to keep revising it after a few days. And after trying for a few times, then you will be able to remember it. You won't forget it. So let us talk about this. So this is a logistic regression, which I'm going to take with an example, heart disease prediction data I'm going to take. And we will be classifying patients on the patient basis of who is going to have a heart disease, who is not going to have a heart disease. And we'll be talking about a lot of things. So I don't remember if I told you this, but logistic regression is used for binary classification. I think I told that. Binary classification. Remember this. It can be used for multi-class classification whenever your output is 3 or more type of classes. You can use it in that also, logistic regression, but it does not perform very well in that case it is seen to be performing very well in binary classification. And for the other one, where the output is one of the three values or four categories, if more than two is there, then there are some other algorithms which works best in that case. The decision tree is there, random forest is there, and boosting algorithms are. So now, let us understand what is this logistic regression. So I'm just reading some packages here. What are these? You will get to see now. I have a heart disease data. And in this heart disease data, if you observe here, we have some columns. And out of these columns, there would be multiple input columns and there will be one output column. Now your task is to identify which is your output column and which is your input column. Now you don't have to do any guesswork at this point. Whenever a data will be given to you, it will be given by someone or you will be collecting it from some website. So on that website, there will be the details of it will be mentioned. Every column that you see here will be explained what they mean exactly. And then which are the input columns, which is the output column. Everything will be mentioned on that website from where you download these. Okay, so why that is important? Because the examples which I'm talking about, these are easy examples where your input columns are first and then at the end your output column is there. But it will not happen always. Your output column can be somewhere in the middle of that. And you have to find it out what is the problem we are solving and accordingly, which is the output column. Okay, so you don't have to make a guesswork. The person who is giving you the data, they will tell you that. Or if you're downloading it from any place, any website or something, you will be able to see that from there also. So now we have a heart disease data. In that we have the patient's condition. As you can see from here to here, we have the patient condition, medical conditions, and then we have the target. Target is the output, right? Now, let's see what is 1, what is 0. Let's see. Before talking about it, there's one thing that you have to understand. What is it? So what you need to know is, if you take a look now to this data, you won't see any text value being used, not a single text value. All of them are number, either they are integer numbers or they are float. You won't see any text. So what happens in machine learning? Machine learning does not work with any textual data. If there is any text data, you need to convert that to numbers, right? What we do some sort of encoding. Okay, we do some sort of encoding we'll be talking about. So there is a process. Let's suppose there is a column where yes, no kind of things are mentioned. So what you need to do, you need to convert it into either yes, you can make as 1 and no, you can make as 0. 1 you can make as 0. Okay, so all the values which are there, if you can convert that into some sort of numeric, you have to convert it into that kind of numeric. So sometimes it is very simple. If two classes are there, which is very simple. So one we can say is class of 1, one we can say is class of 0. 0 means negative value, 1 means positive value. Negative means no, and positive means yes. Something is yes, something is no. So we encode that into these numerical terms. Because machine learning does not understand these things and does not work very properly, it will give you error if you try to use it like this. So you need to encode it. How do you do that? I'll be telling you that. But there are other techniques also, which I'm going to talk about in the upcoming session. We will see. Okay. It is called encoding of the data. Some cases, what will happen? There will be multiple categories, not just yes and no. There might be 5 categories. So we don't do that 0, 1, 2, 3, 4 for 5 categories. We have other options also that we need to take into consideration. We will be talking about it. So now, once you see all of those things are there, there is one more problem that we will see in 2 minutes. Now let's see. We have the data. We are just checking the head and tail of it. We're just checking the shape of it, info of it. All of these things. Why do we do? To check the whether the columns are proper or not. Now here in the machine learning, what you need to check in info is there should be no column whose data type is object. That is what you need to check here. Okay, not a single column where the D type is object written. It should be either integer or it should be float. Only two things are allowed. There is one more, which is the date time kind of value, which is allowed here. So there is a data type which is called date time 64. Like this, it will be written for a column. So that is also allowed, but we will see about it when it comes. That is a specific case. It does not come in every data, the date. So info, when you're checking, first thing you check, obviously, the missing values. Object means text data. Whenever you're talking about object, some kind of text is being written. That is what object represents. Okay, now, so what do you check in info? Basically, you know that the number of missing values, you check that, and the D type. Two things you need to check. So here, earlier when we were doing just the analysis with the Pandas, I told you you need to check the D type to understand whether that column has a correct form of D type or not. If you're talking about a price column, so price column should not be object data. It should be float data. So you need to make sure that it is correct data type or not. Now here, what you need to do in machine learning, you need to check that, of course, whether a column is of the correct data type or not. Second, you also need to check whether all the columns are of integer and float type or not. It should not be of any other type. Only float and integer allowed. So these two things you check, then you can do isNull.sum to verify the number of missing values. Then dot describe also we have seen statistical things, mean, standard deviation, minimum, percentiles, to basically see that if some sort of outliers are present or not. Do you see any column has any sort of outliers in this case? The age column or the sex column or the CP column, trust, DPS, and any column. Do you feel like any column has outlier problem? Anyone? If you feel that there's a chance that this column has outlier or this or the data feels balanced to you. No, 303 is the number of rows. No outliers. See, 303 is what? 303 is the number of rows if you see. Where the shape. Okay, and 14 columns are there. So 303 rows, 14 columns are there, and you see all of these columns. Now you have said, some of you said the cholesterol maximum, and yes. So those who are saying no outlier, that is correct, because if you see here cholesterol, what did I tell you? That you don't have to take a look at the maximum directly. Okay, maximum you don't have to see. You have to see how they are increasing with regard to each other. Okay, so you can see here 126 to 211, 211 to 240, 240 to 274. So you can say here that there is a bit of increase in these values. From here to here, there was not much increase. From here to here, not much increase. From here to here, not much increase. But you can say that there is a bit of a chance of a outlier, but it is not very heavily imbalanced. You can say maybe some sort of data is shifted on the right side. Okay, some sort of a thing is there. You can say that there is a chance of presence of outlier between these two, but it is not very heavy. Like if it was 274 and it was 1000 something, then it would be a clear indication of outlier that after 75 percentile, there is presence of outlier. But at this point, it is not very extreme. It is comparable. It is understandable. Now, taking a look at any other column which feels to be having imbalanced data? No. Any other column does not seem to be having any such of very highly increasing value. That does not fit. So we just check that basically to understand where we need to remove the outlier. From which column we have to remove the outlier, we get to understand that. I'll take one example to show you how do you remove outliers if there are. The formula will be same, which I have taught to you in the interquartile range concept. It will be same. Just you need to see how it will be written in the code part and where exactly. So now what we have done is, I'll tell you that what is the process to check outliers. I'll show it. The concept is same in IQR, which I have told you. There is a formula Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. Less than that, more than that. That is the same process. You just need to write the same thing in the code form. So we'll see about that. Now, I was talking about this one thing, if you remember, about the balance and imbalance of the data. So I discussed about that there are two cases you're going to see in machine learning. One will be you will have a balanced data, and one you will have a imbalanced data. So for both, you need to do some different type of treatment, different type of things you need to keep in mind. So it is very important you identify whether your data is balanced or imbalanced before moving to the machine learning process. Till this point, we are just checking basic info about the data. We're just trying to see what kind of data we have. So what need to be done? What kind of cleaning need to be done? What kind of manipulation need to be done? We're just checking the basics of the data. Until now, whatever I have told you, you understand that easily. So here, always you need to take that column, which is your output column. Always. To check the balance or imbalance, you need to always take the output column and do the dot value count on that. When you do the dot value count, what does it do? In the output column, your answer will be yes, no, yes, no, yes, no. Or if there are three classes, then it will be mentioned three classes. So your output column can only tell you whether your data is balanced. Means in the output column, you have the information about which patient is suffering from heart disease, which patient is not suffering from heart disease. So that information is present only in the output column. All the other input column, they don't tell me which patient is suffering from this heart disease and which is not. Only the output column can tell me that. That is why we check the value count of the output column always to see whether my data is balanced or not. So it will tell you that how many data points are there belonging to two classes of patients. One is yes, defective heart, means that patient have heart disease, and one, how many patients we have for non-heart disease, mean healthy heart. So 165 patients we have for defective heart and 138 for healthy heart. So this is not exactly balanced and this is not imbalanced also. So it can be said as the normal data. There is no kind of balance. See, the example that I'm taking for now for the explanation is very small, very simple. You will never be seeing such a less amount of data. You'll be having 1 lakh rows, 5 lakh rows, 1 million rows, something like that. The data will be too big. But for now, you just have to work on something like this. I'm telling you to give you sort of comparison. Now, after this point, there are few things which start. We talked about few things, and let's see what happens. So as you have done that, the basic introduction to the data, you have used. It will not be same, Shiva. The number of yes and no will not be same. Let's suppose if 300 is there. So it will not be like 150 patients are having yes and 150 no. Perfectly balanced, you will not get to see, but some sort of things will be there. Like we can have 155 of yes and 145 of no. So this is almost balanced. Some kind of this example you will be seeing. If you have 160, 140, that also seems to be balanced. No issues about this. But now if you have, let's suppose 250 patients belonging to yes and 50 patients belonging to no. So whenever you see a very huge amount of imbalance, it has too much of examples of yes and it has very less examples of no. So then it now seems to have the imbalance. We don't have enough examples of no patients. We have a lot of examples of yes patients. So we can study these patients properly, but we don't have enough example to study the problem of these patients. Okay, yes. So that is the thing. You will see that there will be very clear indication in the data which tells you whether it is balanced or not. You will not have any borderline kind of thing. It will be pretty clear. So now you need to know about one very important process. After you have done the process of data manipulation with pandas, the pandas function, whatever you wanted to do, the grouping of it, the selection of the data, the cleaning of the data, whatever you wanted to do, you have done that. Then comes the concept of data visualization. You make some graphs and plot to understand a bit of relationships. And then you move to the machine learning part. After NumPy, pandas, and visualization, you move to machine learning. So when you move to machine learning, you don't directly apply the machine learning on the data. That is not what should be done. There is some sort of preparation required. Preparation of the data. That is required in the classification problem or any machine learning you talk about. But something will be specific to classification problem and something will be specific to regression problem. So what things are there in the preparation of the data? The first thing that you do is identify input and output columns. Identify input and output columns. So input, where do you put it? You put the input in X and you put the output in Y. You take two variables and you have to just put it there. Right, input and output. That is the first thing you need to do. Second thing, what you need to do is split the data into 4 parts. One is X train, X test, and Y train, Y test. So we've already seen why we need to do this. We train the algorithm or train the model. Any algorithm we take, we give it a data for the learning purpose. So for the learning purpose, this data and this data is given. And for the testing purpose, this data is given. This is for testing. And what does it do? After we give this X test value for the testing, it will give me some prediction results. That prediction result is compared with the Y test value. So if you take a look at these 4 splits that you have done, Y test you never show to the algorithm. This thing is never shown and it is always excluded from the machine learning. Never sees that. It is only brought at the end when all the training and testing, everything has been done. After both the processes are completed, then you bring in the Y test value and you compare this Y test with the Y prediction that you have got. So Y prediction is the predicted output given by your model, and Y test is the actual value which your model should have predicted. So you compare them and you get your final answer. So these are a few things you need to do to make sure you have done the preparation of the data properly. But not just that, steps that we need to perform. But after that, there are a few more steps to be performed. Let's see what. The next step that you will do is standardization of data. Standardization of the data. What is standardization of the data? In the standardization of the data, we take the help of Z-score. Z-score we were talking about in normal distribution. We take the help of Z-score to do something. What exactly? You see. So when I show you the data, there is a small problem. It does not create problem in all the algorithm, but in some algorithm, it creates the problem. Okay. When the algorithm, when you have to do the standardization, basically, is when you have when you are using linear algorithms for the training purpose. Okay, just understand this, that you have to use the standardization of the data, not always, but when you're using linear algorithms. Linear algorithm means you have linear regression, that is a linear algorithm. Why it is said linear? Because you are making a line, a straight line to make the prediction. What does logistic regression do? Logistic regression also takes the linear regression line and convert it to S-curve. So that is also called a linear algorithm. Okay, what does it do? After an S-curve is made, it makes some kind of boundary to identify that from here to here your values are no, and from here to here your values are yes. It makes some kind of boundary which we don't get to see. But with that boundary, it is decided that the numbers below that are yes, above that are no, some kind of things are there. So it is said that whenever an algorithm uses some kind of linear boundary to make a prediction, that is called linear algorithm. So linear regression, logistic regression, support vector machine, these are three algorithms which are linear algorithms. In that case, the standardization of the data is a very important process. Other than that, there are some other algorithms also, which are tree-based, not linear. They don't have such kind of requirement. You don't have to do this there. What is the standardization? Why that is required? So if you look at it, understand this very carefully. What is the work of input column from here to here? These are your input columns. So the work of input column is to make a prediction about the output column. Then what happens is, if let's suppose 13 or 14 input columns are there, out of that, every column is not going to be equally important to understand the whether the patient is going to have heart disease in the future or not. All of these will not be equally important. Maybe to understand the heart disease might be that it may be the case that chest pain is more important than the gender of the person. Because gender does not matter, any male or female patient can have an equal chance of having heart disease. It is not dependent upon the gender of the patient. But of course, you can understand the chest pain is a clear indication of heart disease. If someone has more chest pain, more frequent chest pain in month, in the 30 days, they get chest pain in 20 days. So what does it do? It tells you that there is a very high chance, a very high probability that this person might have the heart disease. So some of the columns will be much more important to do the prediction than some other columns. That is the case. But we don't know that your logistic regression or linear regression, your algorithms will identify which are important columns and which are not important. We cannot say anything about that. We don't, but it will understand this. Now, what happens is, before understanding that, before finding out which columns are more important, there's a small hurdle. If you take a look at these columns, this, the cholesterol, the phthalate, and the age. What is the problem do you see? What sort of problem do you see here? I'm saying that these columns are going to create bit of problem, but how? Okay. So now you can see that the range of values are very different. Here, if I just talk about this stressed BPS, and if I talk about cholesterol, so see here, the numbers are like 145, 130, 130, 120. If you talk about cholesterol, you have numbers like 233, 250, 204, 230. Similarly, if I go to, let's suppose, old peak column, what is this old peak column? In here, you see the numbers are like 0 0.6, 0 0.8, 1.4, such small numbers. So this column has the data which is very small, and these columns have the data which is very big. The problem with this kind of data is that whenever the machine learning takes a look at these columns, before understanding, before identifying which columns are important for us, they will be saying that these two columns are more important as compared to the old peak column, or as compared to chest pain or the gender of the person, or whatever is this FPS, stress, ECG. So whichever column has very small value, machine learning will have a thinking that they are not important. That is why their values are very small. They are not important for us. But this stress, BPS, the cholesterol are very important. Now they might be important, they might not be important. That should be decided after the training process. But during the training process itself, the machine learning will make an assumption about these two, that these are more important than the old peak column or the rest ECG or the chest pain, since they are very big number and they are very small. That is the problem. So what do we do in that case to solve this problem? To bring every column to same scale of values. Okay, what do we do to solve this problem? The problem is happening because of the scale of values. Some column is too big, the number are very big, and some column, the numbers are very small. So what we need to do, we need to bring every column to the same scale of values. If the scales are same, then no column is bigger, no column is smaller value. All the values will seem to be a small number. Then machine learning will not have some kind of inclination or assumption about the data. So how do we solve that problem? There is a process called as standardization, and it will be done here. This is the third process. And then there's a fourth process, which is called, so we need to encode the categorical text data to numerical. That we need to do. So if there is a column like the this gender, men and women. So men and women should be converted into 0 and 1. Anything you can give 0, anything you can give 1, but that is the kind of thing. Now I'll be talking more about this. How do you encode this? There are different ways of doing it. There are different reasons of doing it. Okay, different processes are there, and we'll talk about it. Now here, let's see the processes which I've talked about. The very first process I talked about is the X and Y. Identify X and Y. So in X, your input data goes, and in Y, your output data goes. So your input data is all the columns apart from the target column. And your output data is only the target column, which is your output column. Only one output column will always be there. And apart from output, all the other columns are X, which is your input. So we're taking that. And now the next step is to split that data into these 4 parts. Okay. Those who joined later, I've shared these code files with all of you. So if you don't have it, I'll tell you, I'll share it with you. See, this axis is nothing but it says that the column. This is not required to mention because we have already said that columns is equal to target. If you don't write columns is equal to target, if you just write the name of the column, then you need to mention axis is equal to 1, which means that the target is the name of the column. It is not the name of the row. It is not an index number. It is the name of the column. So you basically write it this way. If you're just writing the target, then you need to mention axis is equal to 1, like this. But if you're mentioning that columns is equal to this, then axis 1 not required. Axis 1 is there to tell that the target is a column. It is not a row index number. That is to tell to the pipe. So you can skip that axis 1. Now, so we have the splitting of the data into 4 parts. I talked about it. There is a package from which this is a function. This function is some pre-written code, how the split has to be done of the data. There is a function written for that. So we are using this function to do the splitting of the data so that we don't have to do it manually. Which rows will go into training, which rows will go to testing. We don't have to identify it. This function will do it for us. We just need to use this function. So we say that we are going to make this much data, 4 splits of our main data set. To make this 4 splits of the data set, we are using this function, train test split function. Inside the train test split function, we are giving the x and y, the test size, and then there's something called as stratify is equal to y. What is random state? Random state, don't worry about it. But there is this stratify. What is this stratify does? This stratify is equal to y is important when your data is imbalanced. When data is imbalanced, then this thing is used. Stratify is equal to y. What does it do? I'll explain in few minutes. But when the data is imbalanced, then it is to be used. If your data is not imbalanced, then we don't use this thing. Only in the case of imbalance. What does it do? I'll tell you in few minutes. So we have just done the splitting of the data, and you can take a look at it. Now, after splitting the data, you have to do the standardization. But standardization I'll cover after some time. First, let me go through the process of logistic regression. Let us see. Now, we come to this point. Random state I'll cover. I'm going to talk about random state in few minutes. So how do you do the training of this? Data is imbalanced. See, I told you multiple times. Here you get to see when you check the dot value count. Here you get to see whether the data is balanced or not at this point with the dot value count of the output column. Now we have this training, which is what we are starting now. So once the preparation of the data is done, once you are clear with these 4 steps, identifying input and output, splitting the data into 4 parts, standardization of the data, and encoding categorical text into numerical. Once you're done with these 4 steps, then only you move to the machine learning part. Before doing these 4 things, you don't move to machine learning. Otherwise, you will get not the optimal answer. You might get an answer which is not the best answer, best predictions. So how do we apply logistic? Again, there is a package we have read for that. There's a package which is sklearn.linear model. This is the package from which we are importing this function, logistic regression. So let me write it down. See, this is the name of the function. So someone has written the code for you, whatever we have understood in logistic regression, that there is a function, sigmoid function. It takes some value, it converts that value from between 0 to 1, and that value is compared with 0.5. And then after comparing, you get to see whether the class is 1, class is 0. What is the prediction value? Whatever steps we have seen in logistic regression is written down for you by someone. They have written the logic. If you try to write the logic yourself, it will be very, very difficult since you're not like expert in programming at this point. You can do this later if you want to write it down, but it does not help you. Either you write it yourself or you use the pre-written code. That will be same. The output will be same. There will be no difference in that. That is why you don't have to write it. If you want to see about it, you can just search logistic regression Python implementation. Just you can search for it. You will get multiple code which can show you what is it. But you will not be able to understand at this point. After 1 or 2 months, you can understand. But if you want to see, just search for it. Logistic regression implementation with Python. Okay. Now, so once we have got this logistic regression function, what does it do? What do we do with this? We are going to use it for prediction purpose. So now we will say logistic regression. As I told you, logistic regression, we use this function and we fit this function to the data, to the training data. Xtrain, comma, ytrain. For now, please everyone understand this. Later you can write and follow the code. The code is given to you. The code is not difficult. First, properly understand it, later practice. So what we do is the process to train the algorithm. This is the algorithm. And when you give it the data, the training data, then a model is created. Okay. And that model is what? That is a trained model that understands the pattern in your data, and it is now ready to make the future predictions. A model is created. So now what we do, instead of doing this in one single line, what is generally done is this. The logistic regression, this function is loaded into one of the variable, like I can say logreg. And then you use that logreg variable in which you have loaded the algorithm to fit it. Why do we do it? I will be explaining that, but this is the general thing that. Now see, there's some sort of warning that has come up. Why that warning has come up? We'll see. How do we remove it? We'll see. Now there comes the concept of hyperparameters. Hyperparameters. What are hyperparameters? You have seen that when you train the model, your model might not be 100% accurate. Okay, it is not going to be 100% accurate. But what do you want? You want as higher accuracy as possible. You should have like 90% accuracy, 92% accuracy, 95% accuracy. Whatever best you can achieve, you try that. You try to achieve that. But again, when you're training the model for the first time, what I did here is just train the model on the data directly. I did not do any kind of modifications anywhere. Modifications on the data I have done, but not in the algorithm. So now what happens is, this is the very first output you have got. This is the very first performance of the model you see. Whatever is the accuracy, you get that. But I told you there is a process of tuning the model. Remember, tuning the model. Tuning the model means what? Trying to increase the performance of the model by doing something. So what do we do exactly? We take the help of hyperparameters. Hyperparameters are something, I think you remember parameters, right? What is a parameter? So parameter is, let's say you have defined a function. Let's suppose there is a function maximum, and then this function takes some parameter, num1 and num2. These are what parameters? Correct. Now, the parameters that you see are there in a function. What is this logistic regression? This algorithm that we are using, this is a function. Someone has written it def logistic regression, and then some parameters are there, right? So when you call this function, what do you write? If def maximum and then some code you have written, what do you write to call it? You will be writing maximum with few numbers, right? Let's suppose I give 10 and 20. So 10 will go here, will become the value of num1. 20 will go here, will become the value of num. That happens. And this is what you're doing. You're calling the function. You might define it, or you can use the code written by someone else. Someone might have defined the function. You're just calling it. Where you get to see the result of this function, you get to see the result of that function when you call the function. When you define the function, you don't see any output. Nothing will happen. But when you call the function, you see the output. I think everyone should be clear about this. And these are called what? The num1 and num2, these are called parameters. Parameters of the function. So parameters of the functions are something which are used inside the function to do some sort of calculation. Num1 and num2 will go inside the function. They will be used for some sort of calculation, comparison. They will be used inside. These are parameters. Similarly, when you're talking about logistic regression, someone has created that logistic regression. And what you're doing now, you're calling that function, like saying logistic regression. And then there is a bracket. Why there is a bracket? Because in this bracket, you have to mention those parameters. That is why there is a space given to you. That is why after every algorithm, you will see there is a bracket. It means that there is some parameters expected. Now, you don't need to mention any parameter. There are some default parameters which work. Even if you don't write it, there are few parameters which are working by default. And you can modify them, you can change them. Like when you're calling maximum, you can give 10, 20, you can give 40, 50, any two numbers you can give. Similarly, these parameters also you can change. Where you get these parameters? See, let's go and see where you get these parameters. Any function you're searching for, any algorithm you're searching for, it is present in this sklearn package. Sklearn is the name of the package, scikit-learn. Like matplotlib, cbond, pandas, scikit-learn is a package. Inside that, there is a logistic regression code written for us. And you see, sklearn.linear model logistic regression. Now, if you come here, then this is the explanation. This is the guide for that function. What all parameter this function can take, there is a guide to that. And if you look at it here, you can use these many parameters inside. There is something called as penalty. There is something called as dual, tall, C, fit intercept, intercept scaling, class weight, random state, solver, max iter. Multiple things are there. These are all parameters that you can change. What will happen if you change them? These parameters, if you're changing, what will happen? You are going to do the tuning of the model. Tuning of the model means the performance of the model will increase or decrease if you change these values. So suppose there is something called as this C is equal to 1.0. If I make C is equal to 1.5, if I make C is equal to 0.5, then what happens? It will change the tuning of the model. Perfect. This is what is going to happen. Similarly, there is a penalty. There is different penalties which are available. Why there is a penalty? What kind of thing does it do? We'll talk about it. So penalty is there. Now, if you take a look at it, what penalties can be used? So there is a default penalty being applied, L2. But you have another options also. In penalty, it is saying that you can use L1 also, some kind of penalty. You can use L2 also. You can use elastic net, and you can use null. 4 values are possible for this one parameter You can use L2, L1, elastic net, whichever you want to apply, you can apply that. So if you see here, there are some default values. This penalty is equal to L2, which is written. That is by default working there. So it is like, it seems like an empty bracket. But what is happening? This is there. Since this is the default, you are not writing it, then also this is the default working. Then there is C is equal to 1.0. Then there is one max iter is equal to 100. Okay, apart from that, there are many other default values are mentioned. But these are few, let's say I've written it. What are these called? Whenever you see the bracket of the function, logistic regression is the function which is implementing your algorithm. So inside that function, if you see anything written in this bracket, these are called hyperparameters. Okay, these are called hyperparameters. Why they are called hyperparameters, not parameter? This is for a reason here. It is called hyperparameter because you don't know what will be the value which you want to try. Because let's say you have a function, a maximum function you have written. So you know that you want to find out maximum between 15 and 25. You know this. When you're working on a problem, you have defined a function def maximum. You have defined a function so that you can compare 15 and 25. You know these two numbers. But when you have these parameter here, they are called hyperparameter because they are experimental. You don't know what will be the value which will give me the best model or best accuracy. You don't know. You're not going to know ever. You have to experiment. You might change the C from 1.0 to 0.5, 1.2. You will have to try different, and you have to see how it is affecting the accuracy. I'll show that just in 2 minutes. But this is called hyperparameter for that reason. Since it is experimental, you don't know the final answer. Okay, that is why it is not called parameter, but called hyperparameter. You decide it, you understand it, what should be the case. So when I have used it, you see my model is trained. When you see this such kind of output, it tells you that the model is trained. But there is a warning. What is the warning saying? Now here you don't have to ignore the warnings. The warnings are very important. They are telling you about something. What is the main warning? It has stopped because total number of iterations reached. What can this mean? Okay, what can this mean? What kind of iteration we are talking about? What kind of iteration do you think we are talking about here? Think about that logistic regression. What we did in logistic regression, what was used for logistic regression? What was the main concept of logistic regression? This number of iterations reached limit. Why it is saying that it has reached limit? What is the problem here? So see, I was talking about this, right? That there can be S curve created like this, there can be S curve created like this, there can be S curve created like this. How does my algorithm know that this is the best S curve, or this is the best S curve, or this one is the best S curve? How does it know? How does it know it? It has to do this calculation. This 1 minus P1, 1 minus P2, 1 minus P3. This calculation it has to do for every curve. Then what it will do? It will, at the end, it will try to understand which S curve is doing likelihood maximization. Okay, so this max iter 100 which is written 100, max iter 100. What does this 100 means? That there are 100 S curves created. Okay, there are 100 S curves created like that, and this algorithm is checking out of those 100 S-curve, which is the best one. Okay, where we are doing the maximum likelihood estimation, which one is maximizing this multiplication, that is what we are saying. Right? So we are comparing 100 S-curve, we are making 100 S-curve and we are comparing it. So we are getting a warning because it is saying that 100 S-curve is not enough for me. I need to make more S-curve and I need to try. Maybe I can get even better answer if I try more than 100 S-curve. Correct. So what I will do now, I'll say, okay, take 200 S-curve. Again, the problem not fixed. I say 400. Again, the problem not fixed. Let's suppose 700. Again, the problem not fixed. Let's suppose 900. You see now the error is gone. Okay, the error is gone. So what does it mean? At 900, the error is gone. You can try some other number like 850. No, till 850 you have the problem, but when you're going till 900, the problem is gone. So this max iter 900 means that your logistic regression for this data, it is asking to make 900 S-curve, then it will be able to find out the best one out of 900. Because by making 100, 200, 300 S-curve, it is not able to find the best one, which is going to do the maximum likelihood estimation. So it is asking for that. Why it needs to make 900 S-curve? Does it seem to be too much for us? If it seems too much, why do you think it is taking 900 S-curve to give you final answer? Can you think of any reason for that? Because 900 S-curve seems to be little too much, right? Perfect, Nitin. Perfect. Why it is asking 900 S-curve to be created? Because we have less data. Very, very less data we have. Because of which my logistic regression is not able to learn the pattern by making few S-curve. So it is trying to make more and more S-curve to be sure that whatever I'm learning is good learning. I'm not learning something bad. So we have less data. That is why it is asking to make 900 iterations. If I give it enough amount of data, then it might be doing the same task. If I increase the number of rows, there's only 303 rows which are there. So if I increase that 300 to maybe 3 lakh, so you will see in that case that it will not ask you 900 iterations. It might be done in 250, 300 iterations also. Okay, so the problem that is happening is we have a very less data and you have to change these parameters to do this hyperparameter tuning of the model. Now, since it is not having any warning and anything, which means that it has been trained. Let me show you now what happens. Why does it matter? What do we do next? Once we have fit the X-train and Y-train, we do this log right dot predict, and we give our X test. So at this point, what happens? The training of the model. Training of the model. Once we get the trained model, we use it for the prediction purpose and we save it into one variable called as y-thread. You can use any variable, but this is common. Everyone understands this y-thread. So if you use this, this will be better. Now, I predict the values. So prediction has been done. Then what I'm using now, there is something called as accuracy score. In the linear regression, I use R2 score, but R2 score does not work here. There is something called as accuracy score. What is this accuracy score? How does it work? I'll talk about it. But in this accuracy score, you need to give the same thing. Y-test, comma, Y prediction. Y-test compared with Y prediction, actual compared with predicted value. And it is going to give me something. 0.85.
Let's have a quick quiz question, guys. And the question is, which technique is used to combat the class imbalance problem in machine learning? And your options are data augmentation, regularization, gradient boosting, resampling methods like oversampling or undersampling. Please mention your answers in the comment section below.
Just a quick info guys, Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
Now, what is this 0.85? 0.85 is the performance of the model. It is saying that in the given data, your algorithm, which is your logistic regression algorithm, is able to learn 85% data points correctly, and 85% is the accuracy of the model. Okay, so accuracy score will always be between 0 to 1. So 0.85 means 85%, 0.62 means 62%. That is the accuracy. So this accuracy that we have got is not too bad, but not too good. Somewhere in the middle. It is usable, but you need to take a look at what is the problem you're solving. So we are solving a problem of heart disease prediction. Do you think this accuracy is good enough for that? For heart disease prediction? We have 85%? No. Because we talked about it, it's a very critical case. You still have a chance of making error 15%. Means you can classify or misclassify 15% patients. In this 15%, if a patient has to be said yes, our model said no. When the patient had to be said no, our model said yes. So this kind of error is happening. That is happening in rest 15% cases, which is a very bad thing. You can't have that kind of thing. 15% incorrect predictions you cannot make by dealing with such kind of thing. But this can work well if you're doing loan prediction. Which person should be given a loan, which person should not be given a loan. In that case, you might work with it because no one is going to die. You might lose some money, but that's okay. That is recoverable in some way. So it depends upon what is the problem you're solving, and then you get to see the accuracy. There's no number that above this only we have to achieve, below this only we have to achieve. It depends upon the problem to problem, domain to domain. Whenever you go to industry, you will sometimes see that you have to just be satisfied with 65% accuracy. In industry, that also happens. Sometimes you will have to achieve 98% accuracy. So very different cases you are going to see. Why I'm saying 65% is also going to be good for you. You will talk about it. You will understand when you go to industry, work with that. So what do we do now? We have to see what is this doing. Okay, what is this doing? We have to see. Sales prediction, I told you, Shashank, sales and profit prediction is not a classification problem. That's a numerical problem. A sales number or how much profit we are going to make in 1 month, that's a numerical output. Numerical output means regression problem. So linear regression will handle that, not logistic regression. Logistic is for classification. When your output is yes and no, fraud, not fraud, loan to be given, not given, that. Okay. So in sales and profit, you don't say sales will happen or not. You say how much of sales will happen, how much profit is going to come. Now let's see. Let us try to modify these numbers. Let me have this penalty to L1. And let's suppose this C to 3.0. Okay. So now, if you see there is an error, solver LPFGS support only L2 and none penalties got L1 penalty. See. So there is another thing which is called a solver. What are all these things? You will understand in the further session. This is a solver. If you see, there is called LBFGS that is being used. Let me bring that. Now this solver is something which is using L2 penalty and you can use it. But, and where do you know that it is saying it? See, when you go to solver, it is explained. So algorithm to use in the optimization problem, default is LBFGS. To choose a solver, you might want to consider the following aspect. So what is the solver? It is having a background algorithm for the optimization. Like there is a gradient descent. Gradient descent, what does it do for linear regression? It optimizes the process of linear regression, saying that you don't need to make 900 lines to get the best fit line. You can do that in 200, 300 also. So there is some kind of algorithm for the optimization of the logistic regression also. So the default one is being used. This. We can use liblinear, we can use Newton CG, Newton Koleski, SAG, Saga. We can use that. Which one has to be used in which case? If you have a very smaller data set, liblinear is a good choice, where SAG and Saga are faster for large data sets. So let's use this. Our data set is very small, right? So let's see the solver change this to liblinear. Now I've trained it. Let's see whether some sort of change happened to my accuracy or not. So this is what I've done. As soon as I've changed anything, the default was LBFGS, but I've changed the default to something else. As soon as I do this, this is called optimization, hyperparameter optimization, tuning. When I run this, now you see the accuracy reduced. Why did it happen? Because liblinear is not a good choice, maybe. Or this C 3.0, which I have written, that is not a good choice, maybe. So let me try this with 1.0. Still 81, which means that this liblinear is not good. Let me try L1. Whether this changes something? No. So which means that this liblinear is the problem in this case. Let's see what other I can use. For multi-class problem, you can use Newton CG and SAG and Saga. But our is not a multi-class problem. It is a binary classification problem. So Newton CG, SAG and Saga, we will not be using that. Liblinear is only for that. Newton Koleski's number of sample is greater than number of features, especially one hot and cold. Okay. So it seems like in our case, the liblinear and LBFGS is the good one. Okay, so let me change that now. So let's try this 2.0 with this. Nothing happening. LBFGS. So it only works with LD. Now you see it has done 0.83 accuracy. But here what is happening now, when I use this LBFGS with the C 2.0, then here it is saying that 900 also is not enough. It is asking the iteration to be increased even from 900. So what kind of things are we doing? We are doing some experimental things. I don't know what should be the value of C 2.C. I don't know how many max iteration should be there. I don't know what solver should be there. I don't know what penalty I need to do. You are trying different values. You are trying different combinations of these and seeing which combination is giving you best answer. Now, do we have to keep trying it manually? All the combinations? Is there a way to get it in a very easy terms? So yes, there is a way to do it in much easy terms. You don't need to do this experimentation manually. For the first time when you're training the model, you will do this manually. Okay, that is the work of a data scientist. You can't automate everything. This is what your task is. You have to play with these numbers one by one manually. You have to spend a lot of days, a lot of weeks to do these kind of things. You have to manually change 900, 800, solver, C, penalty These you have to experiment yourself. But again, after doing it, a lot of things, you will be having some other functions also which can do this task for you. So in that function, you need to give the possible values you want to try, and it will try those numbers for you. I'll talk about it. Okay, there is something called as grid search and randomize. Okay, these are two functions. What you have to do in this grid search and randomize search, you will be giving the numbers you want to try. So you say in this grid search that C from 0.5 to 3.0 I want to try. So what this grid search will do, it will run this logistic regression multiple times. One time it will keep the C 0.5, then 0.6, then 0.7, then 0.8. The same logistic regression, it will keep trying it for all the value from 0.5 to 3.0, and it will tell you which one is best. It will tell you that. So in that case, you don't need to manually change it from 0.5, then 0.6, 0.7. You don't need to manually change it. Just use this grid search and randomized search, and they will do the task for you. So what are these? These are some functions which is going to help you. But before bringing these functions, you have to play with it manually. Why do you need to play with it manually? So that you know the range you have to try. From 0.5 to 3.0, you want to try that. How do you know? Once you have done this few times experimentally, then you get to see, okay, I have to try this range from this range. Then max iter, when you're trying this, you get to understand how much max iteration I should try. You get that when you try it for a few times manually. Otherwise, you might give try the maximum iteration from 100 to 500, but the maximum iteration is 900. So you were trying between a range 100 to 500, but it was more than that range. So you'll not get to understand it if you don't do few times manually, and if you directly use that. Okay, makes sense? So are we clear about everything till this point? How we are getting this accuracy score, I'm going to talk about now. There is a concept with that will easily explain you this. Then there is this random state I need to talk about. So I'll come to this now. If we change beta naught and beta 1, then S curve also changes. So now every time you don't need to take a linear line and convert it to the best fit curve. What you need to do, you just keep changing beta naught and beta 1. And according to this function, 1 upon 1 plus minus beta naught and beta 1x, according to this function, if you keep changing beta naught and beta 1, you will automatically get a curve, which is the best fit curve, according to that. So we are saying that how many times this is being done? This process of changing beta naught and beta 1 is done 900 times. That is what max iter is. Okay, 900 different pairs of beta naught and beta 1 was tried. And out of that, one pair, it has seen that it is the best one. The curve that you're getting with a particular pair of beta naught and beta 1 is doing the maximum likelihood estimation for us. So now what we have seen at this point, we did some kind of optimization, but even after that optimization, it needed 900 curves. Okay, some sort of optimization is happening. This solver we have seen is something used for optimizing the process of finding the S curve. It is optimizing that. But even after optimization, we need 900. So now why this is happening? This is happening for a reason, because the data we have taken for the training purpose is so less that the optimization is not being done properly. There's no room for much of the optimization. When your data is good enough, when your model is able to learn the pattern, there the optimization you will get to see better and better and better. But our data is too less, because of which the correct optimization is not working. Okay, that is why even after optimization, it needs 900 S curve to be compared. And that is what will happen in few cases when you have the less data. So what we did understand, we understand about the accuracy, we understood about the performance of the model. we understood about the hyperparameter tuning. Right now, so what do we have at this point? We are going to talk about something which is called confusion matrix. Confusion. So how are we getting this accuracy score? There is a concept that you need to understand for this. So now the 0.85 that you have got, how we have got that 0.85? So what we have done at this point, we compared two things, if you remember. We compared y test with y predicted. Right, y test with y predicted. That is how we got the accuracy score. So accuracy score is given through a formula, and the formula is something which is this. So there is this sort of matrix is created, and this is called confusion matrix. Confusion matrix talks about what should be the accuracy, and apart from accuracy, it tells us about some other measures. In the case of classification, okay, in the case of classification, we don't use R2 score, MSE, RMSE, those kind of things which I have told you in regression. We don't use that here. For classification, we have different metrics. The very first one is called confusion matrix. Confusion matrix will not give you a number like this, that how much is the performance of the model, but it will tell me something. So with confusion matrix, you get to see about accuracy score. Then you also have recall score. You have precision score. Okay. ROC, AUC score. These things are there. These are few of the metrics for performance testing in the classification problem. Either you use confusion matrix. So confusion matrix is a bunch of numbers, but from confusion matrix, you get accuracy score, recall score, precision score, ROC, AUC score. You have different options. So when to use which one, I'll tell you in the upcoming sessions. But you have these metrics which you will be using. A very common one is this accuracy score. But this accuracy score we cannot use when the data is imbalanced. I'll show you why. But this is not used always. When this fails, then we go to recall score, we use precision score, we use ROC, AUC score. So we'll be seeing in what cases which of the metrics are used. So we were talking about this concept of this confusion matrix. So confusion matrix does something as a bunch of value which can give us the formula of accuracy. The formula of accuracy is given by TP plus TN divided by TP plus TN plus FP plus FN. Let us understand what these numbers are. So these two green ones, add them up, the TP plus TN divided by all the numbers. They will all be numbers. We are going to make it. And how do we make it? Let's see. Let's suppose, if you remember here, what sort of comparison we were doing? How do we get an accuracy score? We are comparing y test with y prediction. Let's see what is y test. If you take a look at it, this is the y test. And we are comparing this with y prediction. Now see, the first number is 1 here. Second number is 0. So this first number is being compared with this first number. Actual is this, and my model predicted this. So when it has to predict 1, when actual was 1, my model has predicted 1. Correct prediction. Second one, when actual is 0, my model predicted 0. Correct prediction. When it is 1, my model predicted 1. When it is 1, 1, 0, 0. That seems to be good. The last 5 values are 0, 1, 0, 0. See the last 5 values. this one is 0, but this has been said as 1. This is 1, but this has been said as 1. This is 0, 1, and this 0, 0, this 0, and 0. So if you see somewhere a misclassification or a incorrect prediction is happening. Where incorrect prediction happened? If you take a look at these numbers, right? Here it is 0, but you're getting 1. Here it is also 0, but you're getting 1. So these are what? Misclassification. Means the patient was not having heart disease. The patient did not have the problem of heart disease, but my model said what? That yes, they are going to have heart disease in the future. They predicted that patient to be heart disease patient when he was not. That's a problem. So there is this kind of thing happening. Now, what do you need to do? You need to compare how many times my model has done correct prediction, how many times my model has done wrong. So suppose I was talking about how do you get accuracy? If 100 patients you are testing, in the Y test, if you have the 100 patients, you know what happened with the 100 patients. Which one was suffering from heart disease, which one was not, you know that. But you wanted to test the model, what it is saying, so you kept it, you compared it with Y prediction. So out of 100, if my model predicted correctly 80 times, what will be the accuracy of it? 80 upon 100. So in this case, 80 means we are not just saying 80 times yes, yes, yes. When it is no, we are saying no. When it is yes, we are saying yes, 80 times. Right? So it means that the person who is a patient suffering from heart disease, we are saying he is suffering. Those who are not suffering from heart disease, we said they are not suffering. Two things we did. This 80 does not mean that all the cases we said yes, yes, yes. Sometimes we said no when it was no. We said yes when it was yes. Why I'm talking about it? Because that is the concept of confusion matrix. Let's see, you will understand in 2 minutes. Look at this. So suppose I take one of the example that my actual is the first patient is yes, second patient is yes, yeah, no, no, yes. Suppose these many patients are there with us. That is the actual. The first patient yes, second yes, third no, fourth no, actual. What my model predicted for this yes, let's say yes. This also yes. This no. Take a look. This is what my model said about the patient, and this is the actual. So what do we say here? You take a look, there is a confusion matrix. How confusion matrix is created? The true class, which means actual class, actual value. And predicted class means predicted value. So positive means yes, negative means no. Positive yes, negative no. So on this side, we are writing actual value, which is positive and negative, but predicted negative and positive. Two things we have written. How you are going to get this? So when my actual is yes, and we are predicting yes, we say it to be true positive. TP means true positive. That whenever a patient was positive, you truly identified that patient as positive, true positive. So what is this TP? It is going to be having a number. Let's see how many TPs are there in our case. So first see wherever the actual is yes. 1, 2, 3, 4, and 5. 5 times actual yes is there. Can you tell me what will be the number of TP? It will be number 3, 4, 5, 2, something like that. Think about it. What is true positive? Actual positive, predicted positive. How many cases are such? Take a look. Make your guesses fast. Very, very easy. See this. Okay. What is true positive? How we are getting this true positive? I'm saying that when my actual is positive and my model is predicting positive, that is called true positive. How many times we are doing true positive case? Here, the first one. When my actual is y test is actual, it is yes, and my predicted is also yes. True positive, one time. This yes, this yes. True positive twice, second time also. And here, one more case of true positive when actual is yes, and my predicted is also yes. So total 3 times we have this number where the actual is positive and our model predicted it to be positive 3 times. Tell me about Tn. Tn is what? True negative. So we just need to do same for the no cases. Take a look. So what will you observe first? First, just mark the no's. And true negative means wherever no is there, no has been predicted. So no and no, no and no, and no and no. In the other cases, an incorrect prediction has been done. So Tn means true negative. True negative. True negative means no was there, no has been predicted. Correct prediction. And how many times? 3. What is this Fn? Fn is false negative. False negative, we are talking about predicted. So actually is positive, but my model predicted it to be negative. Actually is yes, but my model predicted it to be no. What is the case of that? How many times this is happening? Okay, see this thing. The actual is positive, but my model predicted it to be negative. Negative means no, positive means yes. So how many cases are happening like that? First, check the positive yes. Wherever the positive yes is there, 5 times. Negative is being predicted. So one case is here and one case is here. See, here the actual is positive, but my model predicted this patient to be negative. This patient is positive, but my model predicted it to be negative. So there are 2 cases. This is called false negative because you are falsely classifying a patient to negative class. This patient is actually positive and you are falsely classifying that patient to be negative when he is not. Then the last one, negative, this FP means what? False positives. Right, so where is false positive? The false positive case is this, no and yes and no and yes, which means that our patient who was no has been falsely classified to be positive. The patient who was no has been falsely classified or predicted to be positive. That is called false positive 2. So whatever number of actual and predicted we get, you can do it for 500 values, 1000 values. So whatever y test and y predicted you do, this kind of comparison happens. When this sort of comparison happens, this confusion matrix is always created in classification problem, always created. Even if you don't make it, it is being made in the background for you to use it. So what happens with this? With this confusion matrix, this does not give us any performance directly. It does not give you that 80% is the accuracy or 90%, but it helps us in some formula, where the first formula is TP plus TN. This is the formula of accuracy. So TP plus TN is 3 plus 3 and divided by 3 plus 2 plus 3 plus 2. 6 plus 4, 10. What is the performance of this model, which has made this kind of prediction? 3 plus 2 plus 2 plus 0.6. So 60% is the performance of this model, which has made this sort of predictions. When this model has done these many errors, so how many total errors we have done out of 10? How many total errors would you say we have done? 10 predictions we had to do. Okay, we had to do the predictions of 10 patients. How many incorrect predictions we have done? 4, 40%. So this is incorrect. This is incorrect. Because here, this is false positive, means actual was negative, but we predicted it to be positive. That is why it is called false positive, means falsely predicted to be positive when it was supposed to be negative. False negative means falsely classified as negative when it was actually supposed to be positive. So these two cases are incorrect predictions and the green ones are correct predictions. And that is how the formula of accuracy score goes in. Very similar to that, there is a precision score, recall score, everything is calculated using this confusion matrix. This confusion matrix can work for multiple categories also. If there is third category, there will be one more box created, one more box like that, and you will be able to do the prediction. One more, and one more bottom end also. So it can be used for multiple class classification. It does not need to be for two classes. See, it will become something like this. 3 into 3 matrix it will become if 3 type of output are there. Like this, 3 into 3. So it does not need to be just binary case. It can have multiple case, multiple class, and that can be written like this. Now, so some ideas clear. Let me tell you about these two things, which are the stratify and random state. Understand this also carefully. So see, I've used some number which is random state 100. Let me use random number 30. Random state is a parameter where you have to give just a number, integer number. It can be any number. It can be 13. It can be 13,000. There's no number, set number for that. You can give any number. What is the work of it? Earlier, I was using 100 for that, and now I'm using 13,000. Let me use it. Let me show you what exactly happened with this. So now if you observe that if 2.0 is there, some sort of change will happen in the accuracy. If I use random state to be 25, take a look at it now. With this, what I have is, earlier it was 0.83 for 13,000. When I run it now, it becomes 0.85. For which? For 25. Right. So when I'm doing this, when I'm changing the random state, it might change the value, the accuracy value, little bit. So in my system, it might be showing 0.85, but if you try that on your system, it might be something either less than that or more than that. You will not be getting the exact 0.85, might be. Maybe you get that, but maybe you don't get the exact 0.85. So what is random state actually? Why does it, what does it do? That is very important to understand. You can try that. You run the code on your system, you see, you will not be getting, all of you will not be getting 0.85, which I'm getting. You might get 0.84, 0.87, something you can get. Why does that happen? So when I was talking about this data, suppose this is my complete data, 100% data, I said that. So I said that we have to divide this data into training and test. This is the last thing I'll talk about. We have to divide our data, split our data into training and test. So I said that, let's suppose we take this as the test. Can we do that sort of thing? Is this possible that we take just the last few rows into the test of the data and the above rows into the training? Okay, can this happen that we take that? This can happen. But again, it does not happen like this. It does not happen like this that your above are getting, yes, Amit, that is what. So I'm talking about that exactly, why you're getting a different number than me. If you all try, you will be getting a different accuracy score for the same number. If you use random state 25 and if I use random state 25, we'll both be getting different accuracy scores. Why is it happening? So when I was talking about, we have to split our data into two parts. One is the training data, which is, let's say, 80%, 70%, 75%, and the test data. Does it happen like this? Does it say that the middle or the last few rows I will take for the test and the top rows we will take for training? It does not happen like this. But what has happened? Random selection happens. Why random selection happens? Because if you see here, if I would have done it like this, in the test, you only have the examples of 0, 0, 0, 0. And there is no single example of a patient having heart disease. Here you see the output have a mixture. There are some patients of 1 means having heart disease, and then there are some patients who did not have heart disease in the training part. But when you're testing the model, you only have the patients who have no heart disease. Is this a good thing to do while you're testing? Of course not. You should have some examples of 1, some examples of 0 to be able to predict the data points correctly, to make a correct prediction. So that is why whenever you say that 20% should be test data does not get picked up as the last few rows. So 20%, let's say out of these is 6 rows. So 6 rows will be randomly selected. Let's say this might be 1, this might be 1, this might be 1, this might be 1, and this might be 1. Like this, 6 rows are randomly selected in my system, and they are selected in your system randomly. So because of this random selection, it might happen that all the rows which are getting selected are of all the 0, or all the rows which are getting selected for test are all 1s. This might happen. Okay. So that is why what we do, we have a concept of stratify. Are you understanding this random state? What is random state doing? Random state is a number. Let's suppose I say 25. 25 is a number. It's just a number. According to 25, let's suppose these rows are being selected. If I change this 25 to, let's say, 130, any random number I can try. So according to this 130, what will happen? Some other rows can get selected for the testing. This might selected, this might get selection, this might get selected, this might, and this might get selected. So if you're trying different random state, different rows can get selected for test. So row number 159, 164, 169, 174, 179, these rows are getting selected for test, and the rest one will be automatically going for training. This is what random state does. Now, what problem happens with this random state concept? It is not used in the actual project. It is just done for now. We have better measures to do this. See, can you think of a problem that might happen if I use the random state concept? Or even if I don't use the random state concept, see what will happen. There is a client who has given me a project to work on. Okay, client is there who has given us a project to work on. And now, as Amit said, he got the accuracy of 0.81. Okay, 0.81 is what Amit said. So suppose Amit is the client and I'm working for Amit, and I'm making the project. So what will happen in that case? I made this project and I use a random state. For me, the rows which were getting selected were different. So I got an accuracy of 0.85. And I said this to the client that when you run the code, you will see there is an accuracy of 85%. You said that, you claimed that. The client took the same code, did not make any changes. 25 random state you also use, client is also using, but what they are using on their system. So it might happen that on their system, according to the same random state, different rows will be selected, not the same rows. That is going to happen. If I'm using 25, in my system, these rows are getting selected. In your system, maybe these get selected. These. What will happen? It is going to affect the accuracy in some cases. So my client sees this and I have claimed this. Is there going to be a problem? Of course, there is going to be a problem that you have said a wrong result to the client. You have said a wrong interpretation to the client when the actual answer was very different. You said higher, but when the client ran, they got. So they will not understand this concept. They'll say that you said this, but we are getting this. So this is a problem which happens with random state. For now, we are using it. Later, we will replace it with a more dynamic concept. So in my system, whatever is happening in other person's system will also happen the same. So there is a concept of cross validation for that. Okay, cross validation. What cross validation does, it makes sure that whatever I'm doing on my system, whatever accuracy I'm getting, that same thing should be shown to the client also. Cross validation. This cross validation has other tasks also, not just this, but this is one of the places where we can bring this concept. I've used few terms today. You just remember those terms, that for grid search CV is for what purpose, cross validation is for what purpose. Few terms I've used. I'll be taking it up whenever it comes, so don't worry, you will understand 100%. We'll take the concept regarding that. We'll take a data set regarding that. We'll talk about it.
Just a quick info, guys. Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
Processing of the data required few things, which I discussed. One is splitting your data into X and Y, then splitting your data into 4 parts, X train, X test, Y train, Y test, these, and then standardization of the data and encoding the categorical text values into numerical. So few things I was talking about, and a few points that you need to remember is standardization of the data is done to bring all the data to a similar scale, the complete data set. Every column should be of similar scale. There should not be some column which is like a very big value and some columns like very small value. Where does this matter? It matters in linear based or linear algorithms. Which are the linear algorithms? Logistic regression, and then there is a SVM, support vector machines. So these are linear algorithms, and also a linear regression is also linear. These few algorithms are there which make a straight line kind of thing to make a prediction. They use a straight line kind of thing. So now what happens is, in this case, in these 3 algorithms particularly, doing the standardization of the data is very, very important. Very important. Otherwise, they will give you some result which is not optimal. They will give you some result, but it will not be optimal. Like I said, they will be giving priority to the columns which are having big values, specifically these 3. But the algorithm which I'm going to talk about from today, there are some tree-based algorithms. Tree-based algorithms. No need of standardization. There is no need of standardization in the tree-based algorithms. But in the linear algorithms, it is very important. Which are the tree-based algorithms? I'll be giving you some idea what this tree-based algorithm means. I'm going to show that to you. So this is one thing you need to remember just for now in the case of standardization. So that is the thing. Now what standardization basically does, it takes a data and how does it change to change it to the similar scale of values, to a small scale of values. It uses the concept of Z-score. So it will take a column. It will pass it through the Z-score, which is Z is equal to X minus mu upon sigma. Sigma is the standard deviation, mu is the mean. This is, let me write it in simple term, X minus mean upon standard deviation. It will be passing it through the this formula, any data set you give it, and then what it will do, it will just give you a standardized column. Standardized column. That is what you will get. So now you already know this formula, Z-score, X minus mean upon standard deviation. So in that column, X is every value, it will take one by one, subtract mean from that, and divide standard deviation. So every value, if there are values like 100, 150, 125, these values, so there will be some mean of that. So 100 will become, let's suppose the mean is 130. Okay, and the standard deviation is suppose 10. So what will happen? You will have minus 30 divided by 10 is equal to minus 3.0. So it will be doing something like this. It will just convert this 100 into minus 3.0 like this. That is what you will be observing. So now let us see what is the process of this. What do we do? Where do we do it? Okay. So you don't need to write it. Just take a look at it for now. Let us run the code again. Yes. So yesterday, one more thing I said to you, that if you have to check whether the data is balanced or not, then it is very important to check the output column dot value counts. So in our hard data, the output column is the target column. So when you take a look at the target column, you check the dot value counts of it. You understand here whether the data is balanced or not. So what do you see? There are two classes of data. Means there are two types of patients in our data set. One who has a defective heart, one who has a healthy heart. Defective heart means the person who has a heart disease. Healthy means who does not have a heart disease. So we have 165 patients of heart disease, 138 patients not heart disease. So it is not exactly balanced, but it is not imbalanced also. There's not a very big difference. If you have a very big difference, then it is going to be imbalanced data. So I said that after you have done the basic pandas part, visualization you have made, then you come to the processing step of the machine learning. In the processing step, the very first thing you do is you divide your data into X and Y. X, all the input column, Y, the output column. Then split your data into 4 parts: X train, X test, Y train, Y test. I talked about few things. Random state I talked about. Stratify I have to talk about. So stratify is only used when your data is imbalanced. We don't use that when your data is balanced. What does it do? We will see today. Then after splitting your data, then you do standardization of the data. Before splitting into 4 parts, into X train, X test, Y train, Y test, you don't do standardization before that. You do it after that process. Now let's see what we are doing. So for doing this standardization, you're taking a column and you're passing it through a Z-score formula, and then you're converting it to a standardized data. There's a function written for that. That logic is written inside this function, which is present inside this package. Okay, standard scalar is present inside the package sklearn.pregraph. So we are using that. Let me run that. Now what we do, this function is also loaded like this into one of the variables. Like logistic regression, I told you yesterday, we load it into a variable and then we use it to learn the patterns. So what does this standard scalar is doing? Once we have imported this function from one of the packages, we are saying store this or load this into a variable called scalar. Then use this variable and fit the X train. What we do always we follow the same steps which I'm talking about. See, first you will be loading the package, and then you will be loading the function into one of the variables, and use this variable in here to say dot fit X train. You just need to give X train, no Y train, nothing like that, just X train for now. And Y train will never be that having the problem of scales, because Y is what? Y is the output column. Output column is always either 1, 0, 0, 1, or yes and no. So it will never have the values like 100, 200, 500 in the case of classification. It will happen in regression, but regression is not something we are talking about. So now, standard scalar is scalar.fit X train. We give X train. Why we give X train? What we are doing here, is we are saying that we are saying to the standard scalar, this is the scalar variable is holding the standard scalar. Okay. No, we don't use y-train because y-train does not have that scale of data. We don't have to change the scale of the y variable. Y is what? Output. That is what I'm saying. Output has what? In the classification, does your output have 100, 200, the values like this? No. Your values are 1, 0, 0, 1, or yes, no, yes, no, yes, no kind of thing. So we don't use y-train. We can't not, we don't. So we say to the standard scalar dot fit x-train. Where our problem is in the input columns. If you look at it, if we go here, you see our input data is from here to here, and you look at it, our output column is what? 0 1 0 1 0 1. 0 means a healthy heart and 1 means defective heart disease. So do we need to scale these output column ever in the classification task? No, never. But where is the problem? Our problem is present in my X train only. Okay, this will be divided into X train and X test, the input part, but we are just taking X train. We don't even take X test, just the X train part. So we take the X train part and we show it to the standard scalar. And then we say what we are doing here is basically in this step, we are saying to the standard scalar that learn the pattern, that how you have to modify these columns, in what range of value you have to modify these values, learn the pattern. So now what will happen is when you run that, it is going to learn the pattern at this point. It did learn the pattern. So it will give you an output something like this, that it has completed learning the pattern, how they have to be changed, how those numbers have to be changed, in what range they have to be brought down. It has learned the pattern. Once it has learned the pattern, then what you need to do is you say x train is equal to scalar dot transform x train, and x test is equal to scalar dot transform x test. So what we did now, we loaded this standard scalar. Okay, we then gave it to x train. What happened when we gave standard scalar the x train data? It learned the pattern. Okay, after learning the pattern, what we are doing now, the scalar variable which I have used, which is here also. So scalar variable is nothing but it's just a variable which is holding this formula, which is holding this function. So scalar means standard scalar. It's just a variable. So scalar is the variable which has learned the pattern, how it has to transform the data. It has just learned the pattern when I say dot fit x train, just learning the pattern, how it has to transform. Once it has learned the pattern, what we are saying, okay, whatever pattern you have learned, according to that, transform the x train and save it into this x train. And whatever you have learned, transform the x test and save it back to the x test. Now, so what will happen if you run this process? The columns which are there, all the columns in the x train and x test will be modified. But again, as you can see here, all the columns need not be modified. If you look at it, we don't want to modify every column. What we are specifically worried about, we're worried about this, we're worried about this, we're worried about this and this. These 4 columns are something which you are worried about. We can leave age also if you want, but mainly trust, PPS, call, thalac, these are the main important columns which I want to modify. If I am giving just complete extend to transform, then it is going to transform everything from here to here. I don't want to modify every column. All the other columns were of good scale. They need not be changed. Only the 3 columns need to be changed. So if you write this, there is not a very big problem that will happen. When you're writing this, when you're transforming the complete extrain, it does not create any problem as such. But what we basically do, we say this. Instead of this, you can also write this, that take the columns which are there, and only modify these columns. So what we need to say, dot scalar dot transform and give this, right? And where do you have to replace it? Where do you have to replace it? Like this, correct? Yes, Nathan, it works only with normalized data. The data which is in normal form, which does not have any sort of outliers, it works in that only. Okay. If outliers are there, you have to remove it before that. When you're talking about the pandas concept, before splitting X and Y and doing all of those things. So we have to remove the data which is having outlier. We have to do something about it. And I will show it to you. Okay. So your data should be balanced, means your data should be in the normal form. It should not be having outliers kind of thing. So that you need to do. So once we have done this, what I'm saying is this and this is the same thing. Same thing you have to do for the X test also. You just need to write X test dot transform the same columns. And these are things which you need to do. If you say this, scalar dot transform X train, so it will transform every column which is there. And here you are saying transform the specific column, which only has the problem. So now when you run this, then what you observe. So you need to say, this one is asking, there are two things to this. There's a fit transform and then there is a transform. So what does fit transform means and what does the transform mean? There are two functions. So one, if I'm saying one time, I'm saying scalar dot fit. And then I'm giving X train here. What this is doing, this is learning the pattern from the X train, that how it has to be converted into a range of values. Then in the next step, what I'm saying, scalar dot transform the X train. Transform the X train. That is what we are saying. But you can combine these two steps into one step where you can just say scalar dot fit transform. This is one of the function which will do both the above tasks in just one single line, both together. So fit transform means learn the pattern and at the same time transform the X train by learning the pattern. So first, once you have learned the pattern, you don't need to wait to tell me to transform it. You learn the pattern and then you transform the X train variable and then you save it into X train. So these are the few things which you can do. Either you can do it like this, scalar dot fit X train, and then you scalar dot transform X train you do. But if you do scalar dot fit transform X train. So what error it has shown us basically is, if you look here, it is saying that if you want to modify the specific columns, these, if you want to specify the specific column, if you want to change that, transform it. So in this case, you need to use the fit transform function. It does not use the transform function. It has to take this fit transform function. But if you want to use the fit and transform like this, fit into one and then transform it later, then you have to give the complete input columns, all the 13 input columns which are there. Okay. So what we have discussed about cell number 17 and cell number this. Okay. No, you need to mention the column names like this. A range and everything, don't give that. You have to, you should be mentioning that as it is. Got it? So now that is one thing. That is what I've discussed about. You can try it later. This is the thing. That is how you do the standardization of the data. And after standardization of the data, if you want to look at these columns, see what has happened to these columns. So there was age column, chest BPS, cholesterol, thal. These were the columns. Look at it. What were the values before? So when you have seen this before, there were the values like 57, 45, 68, in chest BPS 140, 110, 130, and thallic 124, cholesterol 241. These type of values were there before. But after I have done this transformation of the data, I've changed the scale of the data. What does it do? it is now the age which was like 45, 63, 27, like that, it has become such a small value. The cholesterol column has also become such a small value. Just PPS also has become such a small value, and phthalate also a small value. Now, what will be the values you will see? What will be the range of values? You will see the values from basically -4 to 4. In this range, you will see these values being converted. Okay, that is the information. Can anyone say why -4 to 4? Do you remember Z score? What Z score was? Yes, mean would be the standard deviation would be 1 and mean would be 0. Okay, so if you remember Z score, if I talked about, there was a normal distribution, there was there, right? Normal distribution, if you remember, I said that 99.7% data exists between what? -3 to 3 standard deviation, if you remember, 99.7% data. The remaining 0.3% data, if you talk about 100% data, ranges from -4 to 4 standard deviation in the normal distribution. So that is why when we are using the Z score always have the number from -4 to +4, always. Not less than -4, not plus more than +4. In this range of values, all the 100% data comes up. So that is why when you do the conversion of the data, whatever the ranges are, it will be converted into a range of -4 to +4. And that is what you would observe there. This is just an idea. Take a look at it and understand it in a more proper way. But just basic idea I've given for now. I'll show you outlier removal also. How do you make your data normal? We'll talk about that also. This was one thing. Now we are going to talk about something very interesting. This algorithm, this decision tree, which I'm going to talk about, is one of the most popular, one of the most used algorithms in the industry. When I'm talking about when you go to industry and work on it, this is one of the most important algorithms which you are going to use on a day-to-day basis. See, the linear regression which is there, the logistic regression which is there, they are kind of a normal, simple algorithm. They are not very complicated. They are very simple, and because of being simple, they face some bit of problem. Okay, because they are very simple. What kind of problem they face? They face the problem of underfitting. Underfitting means that they are not able to learn the pattern properly. So what has been done? The people who were in the machine learning field. So the people who were there in the machine learning field, what they were doing, they were looking at what the algorithms existed before. So when they looked at logistic regression has the problem of underfitting. Okay, underfitting. And accuracy score we have discussed about, Kavita. Okay. And when we talk about this, whatever is remaining, we'll be discussing with their solution. Any other score, recall score, precision score, which is there, we are going to discuss about that once I talk about the code of this decision tree and the other ones. Don't worry, whatever is remaining will be covered one by one. So now, in that case, what they have done, what is basically this decision tree? It is one of these solutions where you make a tree-like structure. What is a tree-like structure? So if you observe it here, there are some terminologies you need to know. There are some things you need to know. There's a article which is written very well. But see what basically happens. What is decision tree? It looks something like this. So we have seen linear regression is like this. It makes a straight line for making a prediction. Logistic regression converts the same straight line into S-curve kind of thing, then makes the prediction. But decision tree does not do anything like such. It also makes straight line, but it will not make one straight line. It will be making a very complex type of straight line to run that. Now, okay. So just a minute. Now, if you observe here, what we are talking about is something like this. Now I'll explain this in a very detailed manner, but let's see what does it do and how does it look like in a very basic form. So in a very basic form, a tree looks like this. What we do, how do we create that? So we have something like this and something like this, this, and we just keep making it bigger and bigger. This is called a tree. Now, the tree that we see in front of us in our real world, that is a tree which is starting from the root. There is a root of the tree which is in the bottom of the ground, inside the ground, and then you see there is a tall tree, and then there are branches of it, there are leaves of that. So that same ideology is followed by this algorithm also, which is called decision tree algorithm. So it creates some structure like this, where the tree starts from this point, and this is called the root of the tree. So the tree that we see in real world, it is this decision tree is inverted form of that. So the root is not at the bottom, the root is at the top, and then from here the tree grows in the bottom direction, just inverted form. And what are these now? These lines that you see, these lines, these are the branches of the tree. So the trees goes and it branches into different directions, right? The tree, if you see, goes into these branches, goes into these branches. So these lines which you're seeing are the branches of this decision tree, which is going into different directions based on some condition. Now, if you take a look at it, why would we use decision tree? Decision tree has been created to solve the limitations of the other existing algorithms. Whatever limitation they had, it is going to solve that. Now, decision tree is a very interpretive. When you look at the output of that, you can easily identify, you can easily understand what is the output talking about. But it is not very simple in the case of linear regression, logistic regression. It is not simple in that when you take multiple columns. But when you take a look at decision tree, you can easily identify what is the final output and how it has come to that. Now here, what you see is there is something like this. This is the root of the tree. So what we are saying is there is some data given to us, and this outlook, humidity, wind is the column names. These are the column names. So we have arranged the column in such a way that when you take a look at this decision tree, you can say whether something is going to happen or not, yes or no, whether the transaction is fraud or not, whether a person should be given a loan or not. Those kind of things you will be able to understand if you create this decision tree. So if you take a look, yes. This is a data. There's a data given whether the match will be played on a certain weather conditions or not in the future. Let's say a match has to be played on June 5. Okay, a cricket match has to be played on June 5. There's a tournament to happen. So what basically is there? There is a data of the previous conditions. Okay, previous conditions when the match was being played. We have some data of that. So some days, some kind of wind, some level of humidity, some level of sunny, overcast, rain, these kind of weather conditions are there. So there is a data given to us. If you take a look at it, see, we'll be understanding it in much more detail. I'm just giving a basic idea. There is this data given to us. There's an outlook column. Outlook column means whether the day is sunny or overcast means cloudy or rainy. What type of day is there? Then related to that day, what kind of temperature is there? So on sunny day, you will have hot temperature. On rainy day, you will have mild or cool temperature. So temperature is given for that day. Then humidity level. Is there high humidity or low humidity or normal humidity? These kind of things are given. Wind. Is there a storm going on, or is there a normal wind going on? Weak wind, strong wind. So these are the inputs given to us. These are the weather conditions given from the past matches which were being played, and then we have the data about it. Okay, then we have the data about it, which is the output of it. And the output says that when the match was not played and when the match was played, according to these conditions. Now, what we need to do, we need to take this data and we need to not make a curve or not make a straight line. We need to make a decision tree like this. And when we make a decision tree, we'll be able to take a decision very properly. Okay. So now, on June 5, a match has to be played. And when you take a look at the June 5, you can find out the forecast. Weather forecast you can find out for June 5 very easily. Weather forecast. So on weather forecast, you know that there is going to be sunny and there is going to be a normal humidity and rain is going to not be there and some kind of things there. So weather forecast for June 5 is, let's suppose there is sunny. The day is going to be sunny and humidity is going to be normal. The wind is going to be weak and rain, no. Okay, no rain and the wind is weak. These kind of things are given to you. You know the weather conditions of that day. So what can you do? You can take a look at this and you can say whether the match will be played or not, which you cannot tell by just looking at the data. If you just look at the data, it will not tell you whether the match will be played. You won't be able to understand or identify whether the match will be played according to these conditions or not. Okay, when I'm talking about a data. But when you convert that data, the input data which is given to us, when you convert that into this decision tree form, then it is very easily understandable. So see here, it is saying that outlook. Outlook is one of the column where the conditions are sunny, cloudy, and rainy. What kind of conditions are there? So we are just checking the first condition that our day is going to be sunny on June 5. Next thing, the humidity is going to be normal. So with sunny, there is a humidity which is, so humidity is normal. Then what is the output of that? Yes, the match will be played. We don't care whether the wind is weak. We don't care whether the rain is there or not, because obviously when it is sunny, then rain is not going to happen. Of course, both the things are contradictory, so they are not going to happen. Wind is strong or weak does not matter that much, because on a sunny day, it is observed in the past that the wind is kind of normal. It does not be a very strong wind that we cannot play the match. Some kind of storm does not. So now we have seen what we have got a data. We have converted that data into this structure. Once we take a look at a structure, we can make a prediction about any particular day. On this day, the match will be played. On this day, the match will not be played. You can take a weather forecast of that particular day and you can decide. Just a small example of it. But decision tree is very easily interpretable. How a machine learning model is coming to the output of yes and no, you can identify that. But this is not possible in other algorithms like logistic regression and linear regression. Okay. In linear regression and logistic regression, if you remember, I talked about only one input and one output column. If you take like multiple input columns and one output column, it is not readable. You cannot read that what it is actually doing, how it is coming to the solution, the final answer of yes and no. You won't be able to understand that. But here it is possible. So now there are some terminologies which you need to know before I get into the proper explanation of this decision tree. There's a structure being created, and when you are using that structure, there are some terms you need to know in that structure. The very first term is called root node. What is root node? What does it do? So basically, root node is the first point where your tree is starting to make itself. The tree is starting to appear. That is the very first point of that tree. So that is called root node. Root is always a point of the tree where the tree starts growing. Then what we do, when we are going from the tree, we have branches of it, different branches. So when we are going from any node, whether it is a root node or any other node, what will happen? You're going to break it into branches, 2 branches, 3 branches, 4 branches, any number of branches you can make. But this process is called splitting. If you see from root node, you have 2 lines going in. This process is termed as splitting. Means splitting your data into different directions based upon some kind of condition. Splitting your data. So first is root node. Root node is the very first point of the tree where the tree is starting. Splitting means based on some condition, making branches of the tree, multiple branches. Then any other node which you see, because it has to have something like this. So these nodes, these and these, which are not root, they are not root nodes. Root is only one, but these nodes are called decision nodes. Okay, these are called decision nodes. Which is that, why decision node? Because some kind of decision is taken here, and then you decide whether you want to go this way or you want to go this way. If you go this way, you might find out the answer is no. If you go this way, you might find out the answer is yes. So which direction you have to go, you decide it according to that. No and yes. So the final answer that you get, the final answer, after which you don't have to do any splitting. No was the answer which you wanted to get, or yes was the answer which you wanted to get. That is the final point of a tree. Beyond that, you don't make it further. So this thing is called terminal node. Okay, terminal, or it is also called leaf node. So if you look at a tree, leaf is what? Leaf is the last part of the tree, after which there is nothing else. So before leaf, there are branches. Before branches, there is a root. So first you go from root, you have branches, and the last part of the tree is a leaf. So that is the same thing which is being used here also. This no is the last part of the tree, after which there is no other thing. In leaf, from a leaf, there is nothing else coming out of that from a leaf. Leaf is the last thing. Same here also, no is the answer which you want to get. You don't make it anything after that because you have got the answer. So this is a leaf node, this is a leaf node where your tree stops. So this is what? This is the root node, and the other nodes are decision nodes. And this process where you are breaking it into 2 directions, this is called splitting the tree. This is also called splitting the tree. So the tree is split according to multiple conditions going into different directions. And when it goes into different directions, a very good structure is being created, which we call as decision tree. And it helps us to make a prediction according to that tree. Now, there is one more thing which is called branch or the subtree. Take a look at it. So this, when you are going into 2 different directions from the root node, then what will happen? See, if your root node is there, you're going in this direction, you're going in this direction. So any direction you're going, it will stretch from it further. It can become bigger and bigger on this side. It can become bigger and bigger on this side. So these are called branches. This is one separate branch of it. This is one separate branch of it. From this branch, you can have more and more branches. It can become bigger and bigger and bigger and bigger. So these are called branches, which is also called subtree. So this is also can be called as a small tree or a subtree, and this is also called as a branch of the tree. Now, so these are the terminologies: root node, the decision nodes, the leaf node, the leaf of the tree, and then the branch. Now, there is one more term that you are going to hear, which is called pruning. What is pruning? Pruning is a process where you cut down a tree, some parts of the tree you cut down. Suppose I cut down this part of the tree. I say that whatever is this complete branch, I don't require that, because whatever answer I want to get from the data set, I am getting if I'm going in this side. I'm going from here, going here, 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 and here. This side I am able to use, and I'm able to get all the answers which is required for me. Every type of prediction, every type of answer I'm able to get from this. There's no requirement of this branch. I am never going to that side. So if you're never using this branch of the tree, then what decision tree does? It removes that to make the decision tree simpler and more easy to use. So this process where you cut down a branch is called pruning. And it will be done multiple times. Decision tree does that multiple times to make it easy to understand, to make the tree lighter. Okay, if something you're not using, why to keep that into the picture? So it removes that. So this thing is called pruning. Okay. So these are few terminologies which exist in here, and we'll be talking more about it in just few minutes. Let us start the process. How exactly a decision tree is made? What exactly does it do? We are going to talk about it. So if you remember, I discussed about one thing with you in when I was talking about linear regression. So what does linear regression has a problem, or logistic regression, what kind of problem they have? Both are linear algorithms, if you remember. So what I said that, let's suppose if you have such kind of data. Pruning means cutting down the whole branch. Now the whole branch you can cut down from any place. I'll talk about it. So cutting down the branch means not from the start, it can be from anywhere. Let's say your tree is like this. And then you have one branch. And then of this branch, there is another small things. And then for this also, there is another small. This also can have its own. It also can have its own. This also can have its own. So this can keep growing and growing and growing till you don't get the final answer as yes or no. It can keep growing and growing. Now what happens here is when you are saying you are cutting down a branch. So it does not mean that you have to cut the branch from here itself. Branch is what? Branch is anything. If you cut down from here that I don't need these things, these are not helping, so that is also pruning. Pruning does not mean that you're always cutting from here at this point. It means that you're cutting either this branch or you are cutting this branch. Anything which you're doing, this is a branch of it. If you look at it, if it seems like a small tree, like a structure, this is the branch, and if you cut down, this is called pruning. That is what pruning. So we cut down which branch is not important to us. We cut that specific branch in this case. Yes. So what I was talking about is there was a problem which you saw in the linear regression. The sort of problem was that let's suppose your data is like this. Okay, this kind of data is there. So what linear and logistic regression both will do, they will both try to make something like both of them. Either we are talking about linear or we are talking about logistic. They will be making something like this. Now, why I'm saying logistic regression will make a line like this? See, when I talked about a curve, S curve, this S curve we see, we understand the concept of that with an S curve. But what happens is when the S curve is created, this is represented in some kind of line to decide which is the yes, which is the no. This kind of line is being created. You don't have to get into the depth of that. But the S curve which is created, that is for us to understand the output. But in the background, some kind of line is being created. And that is called plane. If you study the mathematical playlist which I have given to you, it is called that a plane. A 3D kind of plane is being created. Let me show that to you. So what S curve is actually doing, let's see this. There is a concept of hyperplane, which is being created. And when you create that S curve, then what that S curve does, this creates this kind of 3D plane, right? What does it do? It creates a kind of a 3D plane. What is this 3D plane doing? It is created in 3D manner in such a way that beyond this point, there is these data points. Beyond these points, there are these data points. Beyond these, these are the patients of diabetes. And below that, there are the patients of non-diabetes. So what we do, we make a S curve, but that S curve makes a 3D kind of line like that. It is called a hyperplane, which is a 3D boundary, hyperplane. Okay, it is not possible to visualize from our side, but some kind of visual form is given to you. So whenever we make S curve, this is going to have a linear boundary. This is also a form of a linear boundary that above this is the answer, below this is the answer. It creates something like this. So these are called linear boundaries. But what happens is, it is not very simple that you just make one boundary and all the data points are above it and all the other data points are below it. It does not happen like that. So now what is happening here also, the linear regression and logistic regression are making a 3D curve like this, a 3D kind of hyperplane like this. But what is this? Is this understanding the proper pattern properly? Of course not. So what we said, we need to use some kind of advanced algorithm which can understand the pattern like this, that there should be one line like this, one line like this, and one line like this. So which one is understanding the pattern more properly? Of course, the red one is understanding the pattern more properly because it is passing through the data points more closely. And this kind of thing is created by what we are going to talk about today, the decision tree. Linear regression will always make this kind of line. Logistic regression will also make one single line. But decision tree is one sort of thing which can become very, very advanced. And by becoming very advanced, it can make or it can fit such kind of line to the data points to understand the pattern very, very properly. So how do we create these type of structure? This is what I'm going to show you now, that how do we get this. Now, the explanation which I'm going to give you is the easiest explanation. Again, you will not find out any explanation which will be easier than that. And once you understand this, you again can use it anytime. You can explain it to interviewer, or you can even explain it to any other person about it. Let's see. So I have such a data, one such data, to explain you the concept of decision tree. What we need to make a tree-like structure like that. Yes, linear regression also makes a hyperplane, Abhishek. That 3D kind of plane I have shown you. So even more complex than that, some kind of plane is created. That's a mathematical concept. We did not go into the depth of it. But linear regression, logistic regression, both of them create a hyperplane like that, a 3D kind of plane, above which some data points are there, below which some other data points are there. It creates some hyperplane like that. But what is the problem here? If you see, it can never be so simple that if you just make one boundary, all the one class data points are above it, all the other class data points are below it. It is not simple like that, right? So our data can be more complicated. And if our data is more complicated, we need to have some kind of more powerful or more complex plane in that case. So that is being created now with the decision tree. And how exactly it is going to be created, we are going to talk about it. Let's get started. So I'm taking an example, a very interesting example to explain you what happens in decision tree. Let's suppose a data set is there. In that data set, there is information about some customers. And who has this data? A bank or a financial company, which has to give a loan to the customer. Okay, there's a data which is available with a loan or any finance company, which has to give a loan to the customer. And when it has to give a loan to the future customer, what it will do, it will study the behavior of the past customer who have not been able to return the loan and the customer who has been able to return the loan back. What the bank will do, what the bank wants, when they are giving a loan to a person, They want that that person should return that loan, right? That person should return the loan back to the bank. And with the interest, basically, they charge some interest on that 11%, 12%, 10%, 9%, some kind of interest they will charge. So this person who has taken the loan, they should return the main amount. Let's say this person has taken a 10 lakh rupees loan. So 10 lakh they have to return. Obviously, that is the main amount. But on top of 10 lakh, some interest also this person has to return. So what bank has been able to do? Bank has been able to earn some extra money in the form of interest. The bank got its money back and also the interest, which is the extra amount for that bank. This is what bank wants. But let's suppose this person uh, took the money for some kind of business and that business failed and this person declares a bankruptcy that my business failed, I can't return the money, it is not possible for me. That was a very huge amount of money. I'm not left with even 10 rupees in my account. I lost every money which I used in the business. What will happen to the bank? So bank will have to just accept that I cannot get this money back. And it is going to just represent into some form which is called NPA, which is non-performing asset. This is a domain thing I'm talking about. When you go and work in the finance industry, you will be hearing about this term very frequently. Almost every single day, you will be talking about this. What is a non-performing asset? When the bank give a loan to the person, it was an asset for the bank because bank was going to make money on this 10 lakh rupees, which bank has given to that. So it was a performing asset for the bank. But now, since this money is not coming back, this 10 lakh rupees is not coming back to the bank, it becomes non-performing asset. I lost the money and it has not given me even the interest. So I lost both the things, the interest also and my main amount also. That becomes a non-performing asset. So now, how does a bank identify which person should be given the loan, which business should be given a loan, and who should not be given the loan? How do they identify? So they, of course, they will study the past customers. What is the behavior? What kind of things we need to understand about a past customer to say that this customer will return it and this customer will not return. Let's say there is a customer in the past whose age is 62. This person took a loan of 10 lakh rupees and this person is unemployed. He might have retired or he is simply unemployed. He does not have money. And there are 4 dependents on this person. One wife of this person and 3 children are there. 4 dependents. So this age of the person is 62. This person took 10 lakh loan for making a house or maybe something like that. This person is unemployed and he has 4 dependents. He has to take care of 4 people in the family. The child would be there, the wife would be there, just taking a basic case. So it is seen in the past that this person who has these kind of condition was not able to return the money. So you need to identify that what is the age and what is the number of dependent, what is the income of that person. So this person is unemployed, so income is 0. So what are those indicators which tells us that this person should not be given a loan and this person should be given a loan? What are those indicators? Should I focus more on the age of the person? Should I focus on the income of the person? Or does the number of dependent matter for given a loan or not? So these kind of things are very important to understand. We don't know what is exactly important in our case. For some bank, maybe the age and income can be very important. And maybe in some form, some of the bank, it is seen that the number of dependent is more important or the amount of the loan taken is more important to understand. So it depends upon data to data. You cannot always say that unemployment or the income and age is the most important thing. It depends upon data to data. And you have to understand that pattern from the data itself. Right now. So we are taking such a such kind of case itself. And here we have a simple example to help you understand it. We are taking two things, two features about a customer. One is their annual income and one is the age of the customer. And what are these data points? These are the data points of the past customers, where all the red dots tell that they have defaulted. Defaulted means the person was not able to return back the loan. And non-defaulted means these are the customers who have been able to return back the loan with the interest. Now, we have to understand the pattern, that after which age or after which income the person is going to return the loan. We need to understand it.
Let's have a quick quiz question, guys. And the question is, in a decision tree, what does the Gini impurity measure means? And your options are the information gain of feature, the misclassification rate of a feature, the variance of a feature, or the likelihood of a randomly chosen data point being incorrectly classified. Please mention your answers in the comment section below.
Just a quick info, guys. Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
So what the linear regression will do, or logistic regression, they will try to make a boundary. Since this is a classification, so linear will not be used, logistic. So logistic will make a S-curve, and with that S-curve, it will try to make a boundary which might go from here. Okay, so this is easy to understand. It is not that difficult to understand. But if I start to put some data points here, suppose some more data points inside here, okay, some more customers are here, then what will happen when you are making a line like this? You see, you are misclassifying this customer, this customer, this customer, this and this. These are your dangerous customers, means here you are going to lose money, but you put this customer on this side. On this side, you are saying all the customers which are there, they are going to return back the money and they will also pay the loan. And above this boundary, there are all the customers who will not be able to pay the loan, and we should not be giving any future customer whose behavior matches these customers. But this is not very easy like that. I've taken a very simple example. And in this example also, if you can understand, this is not working very properly. A linear line, a single line cannot understand the pattern properly. So let me remove these data points and make it simple for you to understand how and what kind of thing we need to do here. So instead of making one boundary, we need to make multiple boundaries here. How will we go through that? We are going to talk about the process. And by talking about the process, we will be understanding how a tree is created from nothing. What exactly is being followed one by one to make a tree. See, I don't have any tree as of now. I have to make a tree, and with that tree, I have to understand the structure of a person should be given a loan or not. Let's talk about it. Okay, so now, if you see here, what are you observing? Is there something which feels different to you, what you're observing? Is there can be first boundary we need to create. A very first boundary we need to create, which is going to be like this. Let's see. Just take any particular point and make the first normal boundary, because I don't understand for now what kind of boundary should be created, and we are going to create such boundary. See. So what I do now, let's suppose I take a line and I make a boundary here. What I'm saying is I have created a very small boundary, and I'm saying that on this side one type of customers are there, and on this side one type of customers are there, which means that I'm saying if a person is having the income of annual income of this might be 37K. So I'm saying that any person who has the income of 37K, more than 37K, okay, greater than equal to, also I can say, these are the customers who can pay the money back. And these customers should be given the loan. We are saying that according to one basic boundary that I've created. Below that, below 37K, if the salary of the person is below 37K, the monthly salary, we're not going to give this person a loan because there is a chance that this person is not going to return it. Now, is this a very clear boundary to make that kind of distinction? No, because on this side, which you're saying this person should be given a loan, there are few customers in the red which were not able to return the money. So this boundary is not a very clear boundary which can help me make a very clear decision at this point. So what I should do now to make it better, I should make another boundary. So what I will do now is I will try to make a boundary from this point. If I take this boundary, then can I say in this area, all the blue points are there only? In this box number 1, there's only all the blue points. And above this, in the area number 2, can I say only the red points are there, which are very clear, and only one blue dot is there, and apart from that, all the red dots are there. What is the point of that? We'll see. But I can say something like this at this point. Again, if I go beyond this, beyond 37K, and I put a boundary which is like this. Suppose I take a boundary like this. Okay. Now, does it seem to be working better than the previous case? Instead of just making one line through that, I have divided what? I have made this into 4 different parts. When I have made this into 4 different parts, there are few customers in this part, point number 1, box number, and box number 3, and box number 4. What I have done? So I have done this. What is this now? This box number 1 says that if a person is having annual income of less than 37K, and if their age is less than 29, let's suppose this value is 29, suppose. So if a person whose value is less, whose age is less than 29, and their annual income is less than 37K, these are the customers who were able to pay the money back. This is what the blue dots are representing, and this is first set of customers. The second set of customers who were not able to pay the money back, who are these customers? The second set of customers are now the person who has the salary of less than 37K, okay, salary less than 37K, and their age is how much? Above 30K, greater than equal to 30, I can say. So if I'm talking about this point, or I can say from 29 also, 30 also, just a basic idea. If you see, this is the point. So if age is 29, I can say greater than 29. I should be saying greater than 29. This is a person, this is the set of customers who are not going to be able to pay the money back. How I know that? I have studied the past data, and they were all the customers similar to this customer who were not able to pay the money. So if any new future customer comes in, we ask about their salary and we ask about their age. If we found this thing, if their age is more than 29, 29 years, 4 months old, 29 years, 6 months old, if their age is more than 29 and their salary is less than 37K per month, this person should not be given a loan. There is a high risk. Next, point number 3, box number 3. What is box number 3? There are, you can see more red dots and 2 blue dots. So more are red, which basically we can safely say that these customers are risk customers. Maybe they can repay the loan back, but we are saying that most of the customers can't repay the loan back. To make it easy, let's have more customer data points at this So what will we say about this? What is the third set of customers in this now? The third set of customers are, if you take a look at this age. Age I can see is somewhere around 43, 44 kind of thing. Let's take it 44. So now this person whose age is greater than 44 and their salary is what? Greater than 37K. Okay. Now these are the customers whose age is above 44 and their salary is above 37K. So in this case, it is observed that these are the customers who were not able to pay the loan. And now this is not common for all the data points. Everywhere it is not common, but this is what has been observed in this particular data. Correct? So age is what? This age is above this point and salary is there's more than that. So salary is more than 37K and age is more than 44. These are the customer whom I'm saying they were not able to pay the loan back. Right. Now, the point number 4, the box number 4 says that the age is this, less than this, and salary is more than that. So if the salary is greater than 37K and the age is less than 43. Okay, age is less than 43. So we can simply say that these are the customers who have been able to pay the loan back, and these customers should be given a loan in the future if any customer comes in around that. Right, age is less than 43 and the salary above 37K. That is the fourth point. So now, can you say that this is much better than making one single line? Does this feel to be better than that? If I'm classifying the customers into 4 areas, into 4 different conditions, does it feel better than that? Will you be confident taking up a decision at this point better than before by just making one single line? So one single line is what a logistic regression will make. But decision tree is a very powerful algorithm which is going to divide the data points into multiple of these boxes. And when it is dividing these into multiple of these boxes, then you are going to have much clear idea, much better idea. So what we have done basically is, yes, it is more clear than any linear algorithm which you can use. So we have observed this, and these are the points which you see. Now, this is a visual way. Once you have seen this, you need to represent that same pattern which you have understood in the form of decision tree. So that once a decision tree is created, then you will be able to take the decision more easily. You don't have to see greater than this, less than this. You will be able to understand very easily according to this. So let us see where we started, and accordingly, we will make our decision tree from that. Okay, let's see. So now, the very first point where we will start. Where are we going to start the tree? From what point? So we are going to start the root node with the annual income. We are starting the root node with the income. And what do we check at this point? Is we have 2 branches. Why 2 branches? Because if you see this first line, we have some set of people on the left side, we have some set of people on the right side. By just looking at the first boundary, by just looking at the very first boundary, not taking into consideration any other thing, just looking at that. So what is there? If you look at this boundary, there are some data points on the left of it, some data points on the right of that. So when I say the customers who are having annual income less than 37K and the people who have the annual income greater than or equal to 37K. So we are making 2 branches of that. One customer goes this side, one customer goes this side. We have 2 branches like that. Now, after this point, it will be much easier for us to take the answer, take the decision if I look at this. Right. So 37K and greater than or equal to 37K, we can say. Or you can say it like this also, not a very big issue. You can say till 37K, you are seeing one set of customers, and more than 37K, you're saying one set of customers. Then what I did, in less than equal to 37K, I'm talking about this area now. Whatever is on the left side of that income, I'm talking about this. So on the left side, what I have done, if you take a look, on this left box, on the left side of this, I have made one more boundary. What is this boundary? This boundary is at age of 29. Okay, this boundary is at the age of 29, less than 29, more than 29. So I will do what now? I will have to make one more node because there is an age concept being used here. So I'll say age. Then what is age now? I can say easily that let's say the person who has age of less than equal to 29 are one set of customers on this side, and the person who has greater than 29 are another set of customers. Then what I have observed, the people who have the age of less than equal to 29 and who have the salary of less than 37K, who are these customers? Are they were they able to pay the loan or not? Yes. So the answer is yes, or we can say not defaulted. Not defaulted means they were able to pay the loan, so it is basically yes, not defaulted. These customers are what? On this side, these are the customers who have defaulted. They were not able to pay the money back, so they have defaulted. Now, what you have done, you have represented this first half into a decision tree format, which you can see very easily, and you can take a decision about any further customer who is going to come. You can predict the answer. So any new customer comes up and they are asking for the loan. What you will do? You will ask for their income. What is your income first? You care about income first. You ask them their income, and they said that our income is, let's say, 39K. So 39K means you will now go on to the right side. If talk about, let's say, a customer comes up whose income is 25K. So you go on the left side. If the income is 25K, you go on the left side and then you ask the age of the customer. Age is, let's suppose, also 25. 25K is the income of that person monthly, and age is also 25. So age is falling where? So you first come this direction, and from here you go to this direction, and this person, you can say that we can give this person a loan because there was a similar customer in the past who has not defaulted according to that. Okay, now it will not be that in the past every customer who was like this not defaulted, but we are talking about most of the customers who have this kind of criteria, this type of thing, did not fault. Okay, and he was able to return the money back. So this customer should be given a loan. But again, a new customer comes up whose age is or whose salary is 39K. We now need to make for that the right side of that. So right side of that is what? This part we are talking about, this complete part. So where is this boundary being created? 43, 44, you can say, is the age I'm talking about. Less than 43, more than 43, something like that. So let us say till 43, there is one set of customer, and above 43, another set of customers. So again, I'm asking the age of the customer, but age matters where? So age is, let's suppose, less than equal to 43, and another set of customers are whose age is more than 43. So what these person are, the person who has age less than 43, these are these blue data points who have not defaulted. So I will say not defaulted. And these are the customers who have defaulted. Now, what we have done, we have taken a data, and that data was telling us something. By just looking at the data, I was not able to take any decision at that point. So what I have done using this decision tree algorithm, using this machine learning algorithm. So using this decision tree algorithm, I have been able to make a pattern like this. I have been able to represent that pattern into a tree format. When I represented this pattern into this tree format, see, whenever you make a linear regression line, whenever you make a curve, that is always done using the past data. You don't know the future data, but whatever was there in the past, you learn the pattern from the past data and you represent that in either a linear regression line or an S curve or the decision tree. So this pattern we are representing from this complete decision tree is what we have seen for the past customer. If any new future customer comes up, I don't know whether this customer is going to give the money back or not. I don't know. Future customer, you can never know. But you can take a decision according to this machine learning, according to the pattern he has learned, this machine has learned from the past customer. So any customer I'm talking about is a future customer who has come. Let's say their salary is 65K and they have the age of 37. So what will you say about this customer? Whether this person should be given a loan or not? If you don't look at the decision tree, it will be very difficult for you to just say whether this person should be given a loan or not. But if you take this answer and if you go through the tree which you have created, this is a new customer, future customer. So tree says that first check the income of the customer. Income is 65. So where do we go? We go on the right side of it. We don't go left side because this is this less than 37. So the income of the customer is 65, which is obviously on the right side of it. So we go on the right side, then we check the age of the customer. Age of the customer is we are saying 37. So first we go this side, then from here we go this side. And what is the answer we are saying? Not defaulted. So most of the customers in the past, we observed that according to this kind of criteria, most of the customer did not default. So there is a very high chance that this customer will not default. But it is not a 100% prediction, of course, we are making. This person can default. But what we have observed from the past data, that if let's suppose 100 customers came in the past, according to these criteria, so like 90% of them returned the money, 95% of them returned the money back, only few customers who defaulted. So most of the customer not defaulted. So we will just say that we are able to take that much of risk. Okay, 95% are able to pay the money. If 5% lose, we don't, it does not affect us much. This is a decision. And this is the easiest explanation by visualizing it you have seen. You will not see any other explanation easier than that. So this is kind of making multiple boundaries in this case. And if you take a look at it, and if you want to make it even more simpler, then what you can write is this. You can make it even more simpler. You can draw a even more clear boundary to represent this pattern. Let's suppose I can say here, if you look at it, what I can say is there is this kind of boundary and this kind of boundary. Now, what we have been able to do? We have been able to make such kind of boundary. And if you just take a look at it, if I just color it all of that, this whole set of area. No, this is not the S curve. This is a different type of boundary. It looks like that. It is not the S curve. Right. So if I talk about this shaded area, what is this? Your decision tree is understanding the pattern that this shaded area is the portion. If any new customer you take whose age is something, whose income level is something, if they fall into this shaded area, they are going to return the money back. And these are the customers who we should focus on, who we should give the money, this shaded area. Is this understandable? What I'm trying to do with this shaded area? These are the person, right? So what we do, decision tree in the background, when you run this algorithm, tries to do something like that. Once it tries to do something like that, it has to see any new customer. So new customer who I was talking about, age of 65 and salary of salary of 65K and the age of 37, this customer, if I'm talking about, where this customer will fall. So salary of 65 and age is 37. So this person will fall somewhere here. The dot of this customer, a new customer, will fall somewhere here. See, salary is somewhere around 75, 65, and the age is somewhere around 37. So this customer is going to fall into the shaded region if any new customer you take. So if this customer falls into the shaded region, then our answer is going to be yes, this person is going to be given the loan. So now we are able to represent so much of information according to the customers, and we see that what kind of answer it is giving us. Got it? This is what decision tree will do. But now, can there be another solution to this? So I'm going to talk about that also. What I can do now is I could do even more things. If the data is even more mixed, so I can go and I can suppose these are the two data points that have come into this boundary. So decision tree can become even more complex, and it can go like this, that let's make a boundary here. Let's make a point from here, and let's make a point from here. It can even do this, which is that for these two customer, if the data is too mixed, for these two customer, it can make even one more boundary. Okay, if such kind of data is there. So if by making this sort of boundary, you're able to classify these two data points also in a more proper way. So decision tree is one of the algorithm which can make boundary and boundary, lot of boundaries it can make to understand the pattern to the last detail. Better than that, better than the decision tree, there are very less algorithms who can perform better than that. Because decision tree is one of the complex algorithm, it can make a tree like this bigger and bigger, different conditions it can tilt, and it can make a very big boundary regarding that. So if your data is mixed, if you're seeing that in this area there are a lot of red data points and blue data points, so you can make a boundary like that, right? So to represent the customer place. Yes, but that is why if you have only two customer on this point, you don't need to do. But if suppose there was something like that, if you have more customers like this, so what you would need to do, you would of course need to make a boundary like this, then it would be very important. But if two customers are there, one customer is there, then it is not important to make such kind of boundary for one or two customers. Okay, if more data points are there, then the tree will have to make that kind of thing to identify these. Okay, so one idea I've given. Let's see the other tree. I'm going to show you another version of that. Where did we start in this case? We started with the point from the income part. Okay, yes, okay, let's continue. It is very interesting, so nothing to be tired about. See, we started with the income. Now, there can be another case that I don't start from asking the income first. I can start from asking the age first. So that is the second example I'm going to talk about. And then we will see which tree is better. Should you ask the age of the person first, or should you ask the income of the person first? That you are going to understand now. Because how do I know I should be asking the income of the person first, or the age of the person first, or whether he is employed or not employed first, or how many dependents are there? We should ask about that, or what is the amount of loan they want to take. Many things are there, right? The amount of loan, how much amount of loan they want to take, for what, how many years they want to take a loan. There are many things. We are just talking about annual income of the person, age of the person. But there can be 15, 20 things about a person which you can ask. So what should you ask first? What should you ask later is very important. Why it is important? See, I'm going to show you the exact example now. So we are talking about this particular case, and we will understand about it. What happens? See, this is my data point, and where I should make a line. Let's suppose I make a line at 30. My decision tree starts here and it makes a line at 30 like this. One line. Is this line helping me identify? But no, because this line is just saying that start from here and any customer beyond this are no customers who will not pay the money back, and less than this are the customer who will pay the money back. But it is not very confident for us. We are not very confident saying that a customer whose age is more than 30 will always pay the money back or will not always pay the money back. There's no clear answer here. There are a lot of customers who did not pay it. There are few customers, good amount of customers who paid the money back. So because of one boundary, it is not easy for us to take any sort of decision. So what we can do now in this case, where we should make the another boundary, you tell me. Anywhere you can make, above, below, anywhere you can make, but you think where we should be creating another boundary. At what point? Correct? Okay, anyone else? Yes. So should we create a boundary, as I can see a very clear indication at this point, that below this and above this, there is clear red points and there is clear blue point in this box, the box number 1 and box number 2. Very clear. So wherever you can see very clear indication, you can just make a boundary according to that. We have got this. So it is around 23, 24, something like that. You can think about it. So we have got this boundary. Right. Now we have got this. So two things are clear. Now we need to make something else. So what we will do at this point, we can just have at suppose let's take it here. Let's take it here. So now if I put the boundary here, then I can see all the red points in this case, in this area, and or even I can take the boundary. Better would be I take a boundary from this point. Okay, on this boundary there is a red dot, right? There is a red dot on the boundary. So it is better if I take a boundary here. Now, I need to make one more boundary, or is this enough? Yes, these boundaries we are making, Nitin, are going to be perpendicular like that. They are going to be like that. So it is much easy to understand. One more boundary is very important. So where should we make one more boundary? It should be created somewhere here, which takes up this also, this data point also. One more boundary should be created. Right. So now between 40 and 50, there is one to be created. Now it is better than the previous case. So what you would see if you observe all the boundaries which we have created, now we are able to identify customers. How many things are there? 1 box, 2, then 3, then 4, and then 5. These are the 5 boxes now we have. Earlier, how many boxes we had? 4. Now we had 5. Let's see which one is better to get our answer. So we'll just start to draw the tree regarding that, and what sort of tree will be created. Let's see. Very easy to understand. What you did first, you write that. What you did next, you write that. And according to that, it will be automatically created. So where did we start? We start with the age first. This is the line we created first. So we'll just start my decision tree. Age is the first thing. In age, what matters to us? So I can say if a person is less than equal to 30, that is 1. And the person greater than 30, that is 1. Now it is not that I need to put it here like this, less than equal to 30. I can put it like that, and I can put it greater than equal to 30. That is upon you, whether you want to take that boundary into the first condition or on the second condition. If I say equal to, so I'm considering all the data points on the line also, on the boundary also. That is the first thing I check. So when I ask the person the age, then I had 2 places to go, one on the bottom of that, one on the top of that. Greater than 30 and less than 30. 2 things. So if I talk about the boundary on the bottom side of it, let's focus on these. So where is this boundary? There is, you can say at 25K, there is a boundary again. Income less than 25K, income more than 25K. So I can say that now we have income. We are next asking about the income, which is less than equal to 25K, and we have greater than 25K. Right now. So what have we seen at this point? Do we know the answer? Yes. So less than 25K, these are defaulted, and more than 25K, not defaulted. So we are going to say for this person defaulted, and with green, I will write not defaulted. Correct? Now, let's see the next one. Above 30, which is on the above side of this line, we are now going to focus on this part. So in this part, there are more boundaries which we have created. Let's see. So first is what? On the above side, what was the first thing we talked about? This line, which is, let's suppose, at 40K, we can say, or 39K, 40, whatever you want. Let's suppose we say on 40K. So less than 40K and more than 40K. But if you see, there is a dot, red dot on the line itself. You see, this red dot is on the line itself. So I will be considering less than equal to for the defaulted ones and greater than 40 to be non-defaulted ones. Right? So now, what we have here, we are asking income again. And in income again, what we had less than equal to 40. And what we found out, less than equal to 40 was default. Then there is another side to go. In another side, do we have a clear answer in this portion if I'm talking about? Can I say defaulted or not defaulted? No. We have again to make one more split. We need to make one more branch at this point. So what we will say, one more branch is more than 40K. If I'm talking about more than 40K. So again, I'm asking about the age, right? Again, I'm asking about the age. So age is what now? So suppose age is 43, suppose I take 43, 44, whatever it is, just as an idea, 43. So I will take less than equal to 43 to be this and greater than 43. Less than equal to 43 and greater than 43. Then less than 43, I'm saying is not defaulted, and greater than 43 defaulted. Defaulted, and these are not defaulted. Now, so again, you are able to make a decision at this point, right? And same if I take the customer who had the age of 65, the income of 65 and age of, let's suppose, 37, same customer if I take, what I will need to do in this decision boundary. So first, the age is being checked, 37. So if 37 is there, where will I go? This side, not the left of the tree, right side. Then when I come here, age is greater than 30, I check. Then I ask about the income of the person. Income is 65K, which is more than 40, I go again. I am checking the age of the person, whether it is less than 43 or 43. So 37 is less than 43. So from here, I come on this side. And my final answer is what? Not defaulted. Right, not defaulted according to this. And according to this, what was the answer? 65 and 37. So 65 on this side, the 37 on this side. Not defaulted both. 37 this side, it will come, right? First you will go here, you will come here. Not defaulted. Clear? So you're getting the same answer, not defaulted, for this customer using both the conditions, both the type of decision tree you have created. According to the both of them, you are seeing that this person is not defaulted. You're getting the same answer. But tell me, take a look at this decision tree. Do you think this is better or the second one is better? think about it very carefully. Don't rush onto this. Whether the first decision tree is easy or which one should you use? You be using the first decision tree, or you would prefer using the second decision tree? Yes. So I have equal number of answers in this case here. But now see, what was your main task? Your main task was just to classify whether this customer is going to be defaulting or not defaulting. That was your only task to identify. And if you go through the first decision tree, you're getting that answer or not. You're getting the answer that this customer is not defaulting, so this person should be given a loan. We are getting the answer. Same answer we are getting here also. So why do you want to ask more questions if you can get the answer in an easy way? Why do you want to invest more time for getting the same answer which you can get easily? See, what has happened? Do you think age we should be checking 2 times? It is good in this case. First, we started with the age and we said that age is less than this, greater than this. Then again, we are asking the age of the customer. Does it feel better to do, or does this one feel cleaner to you? This one, we ask the age once, then we take the income first and then age, and then we got the answer. And this is short and sweet, not complicated at all. And second one is more complicated. Yeah, that is why I asked you. Many of you think that this is more better because this is more detailed. No, what would you do of detail? Because if it is giving you the same answer, why would you want to go into details of that? What is your task is to get whether this person is not defaulting or defaulting. That is what your final prediction output will be. Any machine learning you run and decision tree which you are going to do. So this is going to give you the answer yes and no in a very complicated manner. It will take more time because it has to check more conditions. See, this decision tree feels like more detailed, but it is not detailed. It is asking redundant questions 2 times. About the age of the customer, it is asking twice. So it is asking extra questions which are unnecessary. And if you take this second decision tree, it is going to take more time to give you the same answer which the first tree gave in the very short time. Same answer. Prediction is what matters to you. So if you are able to get a prediction in the shortest way possible, why would you go through taking a decision by asking more questions and going into more details of that? You are getting the same answer. If the answer would have been changed, if you were getting correct answer here and the wrong answer in the first one, then obviously you would go with this because this is the correct answer. But in both the cases, the answer is correct. You're able to make a clear understanding of this is the customer who will pay, this is the customer who will not pay. So why is there a requirement of investing more time to that? It is just going to take longer to make a prediction according to this, and the first one is much lighter. So here comes one principle. Why I'm saying you will focus on this, there's a principle which is used very frequently in the case of machine learning, and that principle is called Occam's razor. Okay. Occam razor says that if you have two options, if you have two or more options, to get the result, right? Then what does this rule says? Considering the output is same in both the case. Okay. Consider the is same or close to same, then always prefer using the simpler model. What is this? So see, this Occam razor is not just for classification. This is a very normal concept in whole of machine learning. This is Occam razor. Occam razor says that if you have two or more options to get the result, right? If you can get a result in this way, so what you should do, you should see first, considering the result is same, the output is same or close to same, then always prefer using the simpler model. Because the simpler model is going to be easy to use, easy to interpret, and it is going to take very less time to make a prediction. Right? It is going to take very less time to make a prediction in that case. That is what Occam razor says, and that is what has been observed. So the second tree is going to give you, yes, simpler the better. Considering the answer should be same. If it is giving you correct answer and the first one is giving you wrong answer, then the idea would have been different. Then obviously you will be preferring this because the answer should be correct. You cannot just take a simpler one and take a wrong answer. If the answer is correct, if the answer that you're getting is same or close to same, then always prefer using the simpler one because it is going to take less time for the training purpose. It is going to take less time for the prediction purpose, and it is going to take will be very easy to interpret because this is short and sweet. Short and sweet. If you ask the income of the person, then age of the person, you got the answer. But here you are asking age, then income, then age again to get some of the answers. Not very good. That is the idea given by that. That is one thing why you should not take a bigger model, but there is another reason for that. Okay, why you should not prefer using a bigger decision tree? There's a reason which is called cons of decision tree. It suffers from overfitting problem very easily. Now, what does this say? It can suffer from the overfitting problem very easily. Overfitting means learning too much. See, this one that we have created, this seems like we have learned the pattern very properly and we are able to make predictions very easily. And there's no problem about that. If any new customer comes up, that new customer will fall somewhere here. Either this customer will fall in this box, this box, this box, or this box. And if you take any customer, you can make an easy identification. Wherever the customer is, that is the answer. And we have made a decision boundary, or we have made a decision tree according to that. Simple. But again, what my decision tree will start to do in some cases, it will start to become more complicated. That this is one thing, and let's suppose there is a point here which is overlapping. So it will try to make one more boundary which is like this, and it will try to just separate every data point from there to there. Very single data point, it will try to classify into this non-defaulting and defaulting. Should we care about single data points also, or are we okay with some of the problems? If something is misclassified, are we okay with that, or should we do for every single data point in that case? We are okay with few of them. We should never be doing that. If a single data point is there, we are making a boundary according to that. This should never be done. For few of the data points, a decision tree should not be making boundaries like that. But yes, we should be okay with it. But what decision tree does, if you let the decision tree do its own task to do whatever it wants to do, so it will make such a complex boundaries. It will make so many boundaries like that. One it will make like this, one it will make like this, one it will make like this. So many things it will start to do that your tree will become bigger and bigger and bigger and bigger. You're getting the same answer, but your tree is becoming unnecessarily big. And for 1-2 data points, it is trying to put a condition. Those 1 or 2 data points are not talking about a trend. They are not any general condition. There are very few customers who might have done or behaved in a different way, but those are 1 or 2 customers. We should not put that into general trend of our output. Got it? So that is what happens. Decision tree does what? Decision tree is a very complex algorithm. It is a very powerful algorithm. So it will try to make such a decision tree, such a big decision tree, that it will classify single data point and it will be very difficult. So it is said that it is identifying the noise which it should not identify. Yes, and obviously the prediction will be same, but for the same prediction, it is making a very big decision tree, which is going to take a lot of time for prediction and it is not easily readable also. So decision tree is said to suffer from the overfitting problem. What is the solution of overfitting problem? Make a simpler model. And that is what Occam Razor also said. That if the output you're getting is same, then always prefer using the simpler problem, simpler model, because it will not suffer from overfitting. But now your model should not be too simple. So you said that, okay, you should, if you want to make it simple, why you are not using logistic regression? Logistic regression will make it simpler, but logistic regression is going to make it too simple. That is, it is just going to make one line, and that is too simple. It is not helping us understand. So I should not be having too complex where I'm making multiple decision boundaries like that. Okay, multiple of these. This should also not happen, and this should also not happen that there is only one line created to make a pattern. It should be good enough that you have made your boundaries are like this. One you have created here, one you have created here. That feels good enough. This is not very simple. This is not very complicated. So now this is the case. If you make very simple, this one is going to suffer from underfitting.
Just a quick info guys, Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
Whatever a difficult to difficult pattern you can give, and it can make a tree which can identify that pattern in a very easy to understand manner. And it represents that as a tree. That is what decision tree. So like linear regression, what it does, it represents the pattern as a straight line. Logistic regression also try to represent the pattern as a curve. But now in the decision tree, it tries to represent the pattern as a tree-like structure. And by making a tree, it basically makes some kind of line, a boundary, which is this pink boundary that you see. And below this boundary, there is another set of data points. And above this boundary, there are another set of data points. So if you see here, what we were basically looking for, if you see all the blue dots are here, all the blue dots are here. Here, most of them are red, few are blue. And here, all of them are red, one blue. So now, we are looking for one thing which is called, we are looking for purity, or this is what we are looking for. Whenever I take a line and I try to split that into two halves, I'm looking for purity or homogeneity. Homogeneity means if you look on this part, then what do we have? We have most of the blue points, but we have one or two red points. That is okay. But since you can say 90% of the dots or 95% of the dots are blue points and 5%, 10% is red point. So what we are trying to do is we are trying to make one box as pure as possible, or we are trying to make one box as homogeneous as possible. Homogeneous means if you're splitting according to a line, let's say this is the line which is splitting it into two parts. So in one part, there should be one kind of dots, okay? And in another, we should have another kind of dots, another class. So we are looking for a concept called as purity or homogeneity. And this homogeneity, if you are able to maximize this purity or homogeneity, then what do you get? You automatically get a decision tree which is very, you can say, powerful, which is going to give you the best answer. So we're looking for a line which can divide it into parts by maximizing this purity, by maximizing the homogeneity. Now the question for today is, that how does it know that first split it has to do exactly at 38K, and then second split it has to do there, third split it has to do here. How does it know? How does decision tree knows that it has to do the split here, here, here? Because we have understood this concept in a visual way ourselves. The algorithm which is there, algorithm will not be drawing this kind of thing. It will have some mathematical formula which will help it to decide where exactly your which line should be. First, you have to split from the income, or first you have to split from the age. There's some mathematical formula which will help it decide that. So this topic that we discussed yesterday, we are going to put this same thing into mathematical terms. How does mathematics help to decide where exactly the boundary should be? So when we take the help of mathematics, it is going to be very accurate that we cannot do. Okay. So suppose we tried to do at 37K yesterday, but it might be 38K or 36K. So that exact answer we will not be able to find, but a mathematical formula will be able to find that exact formula. Okay. So that is what we are going to do today. So remember, there is a concept of purity, or there is a concept of homogeneity that we are trying to achieve when we split that. So when we are splitting, we should have as homogeneous answer as possible. That is going to help us. It is not contradicting. One, you're saying less than 37K and less than 29 years. So that is, you can say, a young person who is earning less. That is what is the audience you're considering. Less than 37K, and if the person is less than 29 years, so you're saying there is a young person who is earning less than 37K per month. That is one person. And second person is who is earning more than 37K, but is age less than 43. 43 means less than 43 means, you see. So what we are now considering another set of people who are above 37K. So when you go to above 37K, that is another set of people. First, you see, first what we did, we have a line here. We have a boundary. What is this boundary saying? That we have first divided our customers, or we have divided the data into two parts. One is a part. If you look at all of these data points in this part, we are saying this is one part of the data, which is based upon age 37, income 37K. So 37K or less is one set of people, and 37K or above is another set of people. So now in this set that we have taken, which is the income, based on the income, we have taken two parts. So in this part, what is the another split, and this part, what is the another split? That is what we are doing, and it is not going to contradict, because you have first divided it clearly into two parts. But okay, so it is not contradicting. Don't worry about it. When you take a look at the data point, when you take a look at the decision tree, it will become clear. Let me show it to you. See the decision tree. So what we are now looking for, age. So first, what is the question? That is what. So if there is a person, you're saying that if the person comes up whose age is 28 years, right? You're saying that if a person comes, if a new customer comes, and whose age is 28 years. So how do we decide that this person should be given a loan or not? Because now here is also age, here is also age. So should I go to this or should I go to this? Because 28 will fall on this side, you're saying, and 28 will fall on this side also, right? So you will now be confused that where should I go? Should I go with this age? Should I go with this age? But before that, you see, there is another question being asked, which is helping us. So I'm asking whether the person is having less than 37K salary. So then you're asking about the age of the person. So there is another question. If you look at the perspective, then we are going through another perspective to take a look at the answer. Right. So that is the thing. You might think that it is contradicting, but it is not exactly contradicting in this case. It is just another way of representing that information It is not kind of contradicting that. Okay, you look at the answer, you look at the solution in the way it is represented. That is why we are representing this into this form. Yes. So if you look at a decision tree, can you say that it is some kind of if-else condition? Can we say that it is some kind of if-else condition that is working in the background? It is nothing but it is a set of if-else condition. So for first, where are you starting exactly? If you write, so we can say if income is less than 37K, then what you're doing? Then you say if age is less than equal to 29, you can say print not defaulted, right? And then else of that, you can say defaulted. And what is the else of that? This first if, the first if else would be this part 37K. So inside also one more if will be there, one more else will be there. So decision tree is nothing which is a visual form of such kind of if else conditions. So now the solution which this tree is giving you, you have to go through that solution, and it is representing a proper conditional statement into easy to understand form, and it has taken care about all the conditions which should be asked. How? Okay, so how are we coming to this solution that first the income should be taken and not the age should be taken? And also the income should be taken at 37K. We are splitting that income. How we are deciding that? That is what I'm going to explain now. So let me go through that and let me talk about it. Okay, now. So this. How do we find this split? See, in this case, if someone feels that it is kind of contradicting it, so I have taken just a basic example of that. Maybe it is not the data which we are looking for. Maybe it is not that type of question which we should be solving. But what we went through, we took a data and when we went through just a way to solve that problem. Whatever decision tree told me, I went through that step and I got my answer. So that is what your task is to do. You just have to follow the decision tree, whatever decision tree tells you to do. You go through and look for it. Now, so what do we have is we have that same question, that how do we find the best fit variable and the value. So where should we split it? Should we split according to income or should we split according to age? How do we decide that? So some of the metrics we are using to find the best split is something called as Gini impurity or entropy and information gain. See, there are two algorithms using which a decision tree is created in the Python. Two algorithms. There are more than two, but they have become old and they are not used now in today's time. But which is being used as of now is these two. One which is called the CART algorithm, and second something is called ID3 algorithm. So they are just two versions of the same thing. They both do the same kind of thing. They both take the concept of purity. When they are splitting it according to some concept, they are looking for purity in the answer. That we should have all the blue dots and red dots here. They're looking for purity. So ID3 algorithm uses something called as entropy and information gain to find that split exactly. And CART algorithm looks for this Gini impurity. Okay, CART algorithm looks for Gini impurity to give you that solution. So these are what we need to write, and you have to use one of these methods to find out your solution. One of these methods. Either you use the CART algorithm to make a decision tree, or you use ID3 algorithm to make a decision tree. They both are same, just there is one small difference. The CART algorithm uses something called as Gini impurity, which is just a formula. And ID3 uses the entropy and information gain, which are also just formula. So we use that to find out where we should split and from what value we should split. Everything it will help us decide. there were two set of trees we created, right? One is income, one where we started with income, and we got this set of decision tree. That was also a decision tree. And when we went through another solution, we got another decision tree. And this was little lengthier than the first one. So here we started with the age first. And when we started with the age, we got a lengthy decision tree. So how is a decision tree going to make sure that from where it should start, from income it should start, or from age it should start? How does it decide that? Now, this is very easy to do if you have 4 or 5 variables. These are columns of the data. The age and income, I'm saying, these are the input columns. And taking the input columns, the decision tree is being created. Now, suppose you have 100 input columns. Okay, 100 input columns. Now, will it not be very difficult to decide out of these 100, which exactly should be your first root node? Root node is the first node where the tree is starting to create. So when there are 100 input columns, how do you decide that? Which one should be taken first? Because we are just taking a column name at the root node. If you see, age is a column name, we are starting with that. And income is a column name, we are starting with that. So and this is the root node I told you about, the root node. So should my root node be this column or this column or this column or this column, which there are 100 options with you. So to decide, and out of those 100 options, there is only one column which will be best to become a root node. Only one of that. So there is always one best fit line. There is always one best fit test curve. So there is always one best decision tree. There can be hundreds of decision tree on a data. But out of those hundreds of decision trees, there will be only one decision tree, which will be best, which will be most efficient, which will be shorter, crisper, and it is going to give you the answer in the shortest time possible, right? So that is what we are going to talk about. So we have this, we are looking for what? We are looking for a solution. We are looking for where to start a decision tree and how a decision tree should be created. At every step, there is a mathematical formula which will help the decision tree to decide, I should take this value, not this value. I should take this value, not this value. At every step, from start till the end, this formula, this Gini impurity is going to help to make a decision tree in the best way possible, in the most efficient way possible on the data. Gini impurity is going to help. Now you can, whenever you have to explain something, no one is going to ask you the mathematics which I'm going to talk about, but you should know it is very important that you understand this mathematics yourself. No one is going to ask you to explain this, but you should understand it very, very clearly. So we are going to take this approach. We will be studying about the CART algorithm, which takes the help of Gini impurity to make a decision tree. This CART algorithm is the most popular in today's time because this CART algorithm can help us to make a decision tree which can do classification also, and it can be used to do the regression also. That is why this algorithm is very advanced, it is very powerful. It can do classification and regression both. So this CART algorithm is being used a lot. CART means classification and regression trees. That is the full form of CART, classification and regression trees algorithm. ID3 is a little bit old algorithm, ID3, which was used a lot like 5 to 6 years back. But now CART algorithm is something which is used very frequently. And that is what you will be using most of the time. So we'll be understanding about this Gini impurity, which is also called Gini index at this point now. So let's see what it is. I am going to explain it to you. Just understand it. Yes, categorical, continuous data, both it will work on. You just need to change something. I'll tell you what exactly you need to change. And this one algorithm, CART algorithm, can make a decision tree to solve a classification problem also and a regression problem also, both. The house price prediction also and heart disease classification, both. I'll show it to you. What do you have to change? So the Gini impurity or Gini index is something we are going to take use of. What does Gini index do? How does it help you decide what column should be taken and what not? We will see that here. So the Gini index we try to find out Gini index at every node. Every node means this. Whenever I make these circles, these are nodes where this is the root node, as I told, and these are decision nodes. Decision nodes, because they help you take a decision. Should I go to the left of this tree? Should I go to the right of this tree? They help you take a decision. That is why they are called decision nodes. So whenever we have something, we have to find out the Gini impurity for every node. That is how it is going to help us, that at root node I should have this column, and at this place this column, at this place this column. So Gini impurity for every node. So Gini index or Gini impurity at a particular node is given by this formula. 1 minus probability of being in class 1. Class 1 means class of yes. And probability of being in class of 0. Class of 0 means class of no. Class of no means all the output which are no, that becomes a class of no or group of no. And all the outputs are yes, yes, yes. So they are called a class of yes or a class of 1. Right? So that is what we have. Let's see in an easy way what this means, how this formula is going to be used. So now let's see, we have again that same problem which we have to solve. And now we have to decide whether my root node should be the age or income. Okay, there were two trees. One was starting from income, one was starting from age. Age one was not very good, but the income was very good. So how do we decide? Let's take a simple solution where I'm taking an input, which is 7 customers. 7 input rows are there, which means that we have the input of 7 customers as a small data I'm taking. Now, we have to decide what we should take. So we start from age here. Okay, we start from age, and decision tree takes a look at the age, and it sees that from 25, it should make the split. It is taking that as a example, that let's split the tree at 25. It does not know whether the 25 is correct or not. It is just going to take a solution that all the ages which are there, let's split at 25. Less than 25, one set of customers, and more than 25, one set of customers. It is just taking that. So when it took the age and it took the this age less than 25, age greater than 25, it went onto two different sites. Now, when there was a data, in that data, it was found that there are 4 customers who has age less than or equal to 25. Out of 7 customers we have taken, 4 customers are such that whose age is less than equal to 25. And there are 3 customers whose age is greater than 25. Left side 4 customers, right side 3 customers. Out of these 4 customers, this in the class of 0, there are 3 customers. In class of 1 customer. So class of 0 or 1, you can take that not defaulted and defaulted. Yes, see. So class of 0 means the person who has not defaulted, and class of 1 means the person who has defaulted. So there are 3 persons who has not defaulted out of 4, and there is 1 person who has defaulted. So it means that when it has taken this and it split on the age, which is 25 is the age here. So what did it find? On the lesser side of that, there are 4 dots. Okay, there are total 4 dots which are there. 1, 2, 3, 4. And on the upper side of that 25, there are 3 dots. Right, 3 dots are there. Now, out of these 4 dots, these 3 points are of class 0, which means that if I take 3 dots, they are belonging to 1 class. Okay, and let's say 1, 2, 3. So which means that there are 3 points which are not defaulted, class of 0, and 1 point of defaulted. As you can see, 3 of class 0 not defaulted, 1 of class defaulted. Similarly here, when we go above 25, greater than 25. So there are three customers above that line, and class of 0, 1 and class of 1, 2. So here the concept is different. You have two people who have defaulted and one person, one customer not defaulted. So now how will it look like is this. So now when it made a decision, what we are doing now, we have split it according to one of the purity concept. So when I look at this now, I can say the people who are age of less than or equal to 25, there is more chance of person being non-defaulting. Okay, there is a more chance that the person will return the money. As an example, we are taking that. And if I go on the upper side of 25, we are saying that more people are in the class of defaulting. So it is said that two people defaulted here, one did not default, one customer did not default. So in total, we can say that since the number of defaulting people are higher, so above 25, we can say that the people generally default. They are not going to pay their money back, they default. But this is just a solution. Now, is this a correct number to take? Should we take the age first on the basis of which we are making the split, or should we take that income first? Or we should have made a line like this first. Which one? So we are going to talk about that. First, we made according to the age, and we are now checking the impurity. There's a concept of Gini impurity, which will help us decide whether this kind of thing was better or not. So now what we have taken is the parent node or the root node we are taking is being split at age less than 25. We are taking a root node and we are going on two sides. One is less than 25, one is greater than 25. So it is being broken, it is being split at the age 25. To calculate the Gini index of this split, we need to calculate the Gini index of each of the child node and then calculate their weighted sum. See, try to understand in a very simple way. No need to remember the solution. I'll give it to you. You can study that. See. So what it is saying, whenever you are making a root node, you have to find out Gini index or Gini impurity of this particular node, which is my root node. You have to find out Gini impurity of that. So Gini impurity is going to be a number which will help me decide whether it is good or not. The impurity, the higher the value of this, the worse that solution is. The lower the value of Gini impurity, the better that solution is. That is what happens. Let's see. Higher value means there is more impurity, which we don't want. Lower value means lesser impurity, which is what we want. See. So to calculate Gini index of the split, we need to calculate the index, the Gini index for each of the child node and then calculate their weighted sum. Index means impurity, so don't confused about it. So we have to find out for left, which is less than 25, and right side, which is more than 25. We have to find out Gini impurity of both, and then we sum it up together. Now, in the left side, you look at it. We are now focused about Gini impurity of this left side. So 3 persons are in one class, 1 person in one class. Here, 1 person in one class and 2 in another class. So I have to find out the Gini impurity of this, Gini impurity of this, and add them up, the two numbers. So when I add them up, it will be the Gini impurity of the root node. Because from there we are splitting and we got this 2 child node. So what do we say here? We are now saying the probability. This is just a formula given. We are not making the formula. So whoever has created the formula, they said they are squaring it for whatever reason. In the left child node, what we have, the probability of being in the class 1 is this much, 0.25. And the probability of being in class 0 is 0.75. So we are saying that on the left side, 3 is on class 0, 3 customers are in class 0, and 1 customer is in class 1. So it is mean that there is 75% probability of being in class 0 and 25% possibility of being in class 1, according to this split. 75% possibility being in class 0, 25% being in class 1. We are taking that. Okay, 1 upon 1 plus 3, 3 upon 1 plus 3, 0.75, 0.25. So once we got these two numbers, we will just use the Gini impurity formula, which is 1 minus probability of being in class 1 square minus probability of being in class 0 square. We just put these two numbers, this and this, and we just calculate this formula. So we get a number 0.375. Now, Gini impurity is one of the concepts whose value will be between 0 to 0.5. No value will be lesser than 0. No value will be more than 0.5. What does it mean? We'll see. But I have got a number which is 0.375. This is the total impurity we are getting. Next thing which we have is this, the impurity of the child right side. We need to find out. In the right side, what is the impurity? So there is probability of class 1 and probability of class 0. So what we are saying now, in the right side now, what is the concept? So 1 belonging to class 0, 2 belonging to class 1. So we'll have 67%, if you can say, in the class 1, since there are two data points there. 2 upon 1 plus 2, 0.67, 67% possibility of being in class 1 on the right side, and 33% possibility of being in class 0 in the right side. We take this probabilities, and then we put this into formula. So 0.442 here we have got according to the right child, and 0.375 we have got according to the left of the tree. Two numbers we have got. Now we have to sum it up together. Now the total Gini impurity of this total split now we are talking about, the Gini impurity of this total split we are talking about is how much? Left plus right, we will get the total. So the total is not just adding them up together. When we are doing the total of them, we are adding up the left and right Gini impurity. We also take the weight of that. How much weight is of the left side of the tree and how much total weight is of the right side of the tree in the total tree. So weight of the left node into Gini impurity of left node plus weight of the right node and Gini impurity of the right node. What is the weight? So weight means, see, out of the 7 inputs we have taken, 4 inputs are on the left side, right? And 3 inputs are on the right. 4 inputs on the left, 3 inputs on the right. So the weight of the left side is called 4 upon 7, which you see, telling that 4 data points are on the left side and 3 data points are on the right side. That is the weight. 4 upon 7 here, 3 upon 7 here. So we say 4 upon 7 into the impurity of this side. Okay, 4 upon 7 into the impurity of this side and 3 upon 7 into impurity of this side. That is what we will sum it up together. This is all the formula given by someone else. We are just studying that formula. So you see 4 upon 7 into 0.375 plus 3 upon 7 into 0.442. And this is the final number we got, which is the total Gini impurity of that complete split. The left side, right side, everything, when we have taken the total, this is the number we are getting. Now, how does this number matter? What are we going to do with this number? Now we are going to make a split according to income root node. And we will see. This Gini impurity is a concept which is going to be everywhere less than between 0 and 0.5. Any Gini impurity we are going to find out will be always. Whether you sum it up, whether you do anything, it will always be from 0 to 0.5. So this represents the total impurity when we are splitting according to the age. When we are making a decision tree starting with the age, this is the total impurity I got. So now I am going to use the income. Let's see with income what is happening. So now I start with the income parameter. Same 7 customers again are there. I have the 7 input data types, data values, 7 customers. So when I take the 7 customers, now I am splitting according to income of less than 25, greater than 25, like that a straight line we are making them there. So when we did the split of income based on less than equal to 25 and this, 3 records are there on this side, 4 records on this side. means 3 customers less than equal to 25 income and 4 customers of greater than 25k income. Out of these 3 customers, what we have now is class 0, 3 customer, class 1, 0 customer, which is saying that the people who were having less than 25k income, class 0, if you assume that to be non-defaulting, so 3 customers are non-defaulting. Just an example, you can treat this as a defaulting and this one is not defaulting, just taking an example. So suppose class 0 means, so it has taken a value less than equal to 25k and greater than equal to greater than 25k. So we got 3 customers according to that, and all of these 3 customers are found to be non-defaulting. But on the right side, where the customer has more than 25k income, one of them non-defaulted, 3 of them default. Again, the weight of this side is 3/7 and weight of this side is 4/7. What do we need to do now? Again, let's calculate the Gini impurity according to these numbers. Again, we will go through that same solution. So Gini impurity of left node is going to be 1 minus 3/0.3 minus 0.0 plus 3 square. So Gini impurity of left node is 0 and Gini impurity of right node is 0.375. Some numbers we have got according to the same formula we have taken. What we are getting now, we are just multiplying it with the weight of that, and we get the total impurity to be 0.214. Okay, that is the final answer we got. Now, what we do with this final answer? See, this one gave us the total impurity of 0.405 and this one 0.214. 405,214. So what we need to do is, what decision tree does is whatever input has been given to it. Okay, whatever input has been given to it. See here, then it takes that input. If there are 2 input columns you have given, one age you have given and one income you have given. 2 input columns are there. So what decision tree will do? One, it will make according to age and it will split that. And one, it will make a decision tree starting from the income, the root node to be income. Now, which one is better in this case? It tries to calculate the total impurity of that, which we have just now calculated. The total impurity of this comes out to be 0.405 and total impurity of this comes out to be 0.214. This. So this is basically saying that when we split according to income, we were able to get more purity. The higher value of Gini impurity means you have more impurity. The lower value of Gini impurity means you have more purity. Purity means you are able to get more homogeneous answers, which you are looking for. So whichever column gives you the least number of Gini impurity is what going to be the value at that node. So for income, when I took the income at the root node, I got this 0.214. Similarly, I can take hundreds of columns. So if you take another column, so it will make 100 decision trees at the start. And out of those 100 decision trees, it will check which decision tree is giving me the least Gini impurity. Whichever decision tree gives you the least Gini impurity, it is said to be the most efficient, most stable, and it is going to give you the answer in the shortest time possible by asking fewer questions. So that is the concept of Gini impurity. Now, the Gini impurity value is 0 to 0.5 always. What is 0? What is 0.5? Let's see. So if you have now, if you are taking some data points, and suppose your data points are like this. You have made a split here. And your data points are 1, 2, 3, 4. And here you have this and this. See. 3.7 into 0 is equal to 0. Yes, so this is 0. That is, of course, 0. So this part is 0 and then plus 4/7 into 0.35. So the answer is of this part, 0.214. That is, of course, 0. So we are doing plus, right? This is plus. If there was into, then total would have become 0. Now let's say when we made a split, we got, according to a split, we are getting something like this. So Gini impurity is what? Gini impurity is having some number between 0 to 0.5. When will you get what kind of number? See, whenever the impurity is less, you get the lesser value. Whenever the impurity is high, you get the higher value. In this case, there is a perfect purity. There's a perfect purity. And let's say all of these dots are representing the customers who defaulted. Let's say these are all the customers who defaulted. So here we are having only the customers who have defaulted. So we can easily take a decision that less than this number, whatever is the age, let's say age is 35 age. So we can safely say that the person whose age is less than 35 is always going to default. You have a perfect purity, perfect homogeneous answer. There's no doubt about it that 10 customers defaulted, but 2 did not default. That would be little bit of impure because 2% are there belonging to different type. But here you can be 100% confident that your customers are obviously going to default because there is perfect purity, perfect homogeneity of the answer. So in this case, whenever there is a perfect purity, then the Gini impurity is going to become 0. Gini impurity will always be 0, telling us that you have got perfect purity. And tree is now created in such a way that tree is now trying to create itself in such a way that the Gini impurity should be achieved as closer to 0 as possible, right? As 0 as possible, we have to achieve. That is what we need to do. Here, what do we have? What do you think should be the Gini impurity of this? From 0 to 0.5, what do you think should be the Gini impurity of this? Yes, it will be 0.5. It will be 0.5. Why? Because you have a perfect impurity. Here we have perfect impurity because can you say here whether the person will default or not in this case? Because you have equal number of customers who have defaulted and equal number of customers who have not defaulted. So this becomes the case of perfect impurity, perfect confusion. You cannot say anything at all at this point. If I say, suppose that 3 data points were there for this and 2 for this. So here little bit possibility is there of this thing being higher. Means the person non-defaulting is, let's say green one is non-defaulting and red one is defaulting. So here you can say at least that there is a higher chance of people defaulting here and lower chance of people not defaulting if I had this kind of data point. But now when we have exactly equal number of data points in both the classes at any point, that is the case of perfect impurity. That there can be never more confusion than that. This is the most confusing thing that can happen. So that is why the impurity is highest, which is the 0.5 in this case. And here it will be 0, telling you that you have got perfect purity. So this is the thing that is going to happen. Now, so whatever number you're going to get, it will always be between 0 and 0.5. When it is getting closer to 0.5, means the impurity is increasing. When something is getting closer to 0, which means that purity is increasing. And that is what decision tree tries to do. Now let's see. How did we decide that when we took the age and this income? You understood now that when I have given multiple input columns to you, if I have, let's say, given age and income column, you're making 2 decision trees for 2 columns, right? One starting with age, one starting with income. Then you see which one is better, but you will make both the decision trees. If I give you 100 columns, so you will make 100 decision trees. This much should be clear to you. Now, the another question is that age I have taken. So age of the customers are from 18 years to, let's say, 60 years. So how are we deciding that exactly that it should be less than 25 and greater than 25, not less than 35 and greater than 35, Why are we exactly choosing 25, not 35? That is another question. So this thing also, that it should be splitting from 35 age, not 25, or it should be splitting at 27, not any other value. That also the engineering impurity takes care of. So it means that when age is being taken, then different values here and different values are here are being tried. And then it is seen that which value, by taking which split of the age, it is giving you the least gene impurity. Right. So if I take 35, it is giving me very bad results in age. But if I take it at 25, it is giving me good results. So that kind of still, you can say, approach, that kind of calculation will be done in the background. And then it will help you identify that there it should be 25, not 35 or 30, any other number. Correct. So we are not deciding that. The decision tree will decide that number also. Getting it? So we are not saying that here always will be 25. I just took one example that I'm taking at 25. It might be 35, it might be 40, it might be 18, anything can be, that will be decided by the tree. Then, does this happen for just the root node, or do we have to do further also? See, the Gini impurity is not calculated for just the root node. How it is calculated? The last thing is this. So how do you make a tree? You make the root node first, then you make this, then you make this, right? So then you make this, then you make this, and you have this, have this. So do we have to just calculate the Gini impurity of this root node and not the further part? It is not like that. The example I've given you was just to explain you that how do we decide the root node? Because where does the tree start? Trees start at the root node. The very first important thing is to decide what will be your root node. Once you've decided that, then only you can do anything further. So if let's say column 1, if let's say some columns are there. Let's say I've taken 5 input columns, C1, C2, C3, C4, C5. The age of the person, income of the person, employed, unemployed, the employment status, the education of the person, the number of years for the loan is to be taken by that person. Different inputs are there, input columns are there. So first confusion is the first task for making a decision tree to decide out of these 5 columns, which will be here. Will it be C1 here? Will it be C2 here? Will it be C3 here? Will it be C4? Will it be C5? 5 different options are there. Which one should we start with? Because one of them will be the most efficient and the other 4 will not be that efficient. So our first task is to identify the Gini impurity according to just by putting one of the column. Let's say C3 is the column which has given the least Gini impurity. So we put the C3 first. Then once this is done, then from here I should take which column? Because now you have 4 other options there. Should it be C1 here? Should it be C2 here? Should it be C4 here or C5? Out of these 4 options, which one should be taken on the left side of this? And which one should be taken on the right side of this? For this also, another Gini impurity will be calculated. For this also, another Gini impurity will be calculated. How that is done, you don't have to go into depth. No one is going to ask you that. The calculation will become little difficult. But Gini impurity is going to be calculated at every step. Whenever you are adding a node, this is called a node, root node, decision node. When you are adding that, at every step, Gini impurity will be calculated to decide which column exactly should be put where. Got it? So you just need to know this much solution mathematics. If this much mathematics you understand, then this is more than enough to explain someone to understand what is happening. Just that thing will be going in the forward calculation, and then that will be done. The identifying of the root node is just that you have to try all of them, and which one is giving you the least Gini impurity is what will be your final answer. Okay, whichever column, whichever tree is giving you the least Gini impurity will become your root node or any other. It is not bottom to top, it is top to bottom. What I have said here is, when I was giving you the formula of gene impurity, you take a root node, right? Suppose I've taken the age to be root node, and my tree has decided that it will split from age 25 on the both side. So when it has decided to do this, then you are checking how much is the total impurity. These gene impurity are not combining to give you this age. But what you're doing, you have taken the age and then you are seeing what is the total impurity in combination. You're going top to bottom, not the bottom to earth. Right? You have taken an age. We are not saying that first we calculate this gene impurity and then say age should be taken. You have taken a tree which is having the root node as age. A complete tree you have taken. And then once you have taken that tree, then you're deciding what is the total of that. So how you are finding the total of that? So age I have taken and we have split it from 25 and here from 25. Right? 25 here and 25 here. So whatever number comes here, you are just adding it up to find out what? To find out what is the total impurity in this case for the tree. So it is always top to bottom. It is never bottom to top. Now, so what is this again? The next algorithm is ID3. You don't have to understand both of them. If you understand one, the other one is similar. So similarly, what happens is, in the other case, if I would have taken ID3 algorithm, there instead of gene impurity, there will be a concept of entropy and information gain. These two will be calculated. They have also some formula, but the process will be exactly same. A tree will be taken, the left side of that, right side of that. There we will calculate the entropy and information gain both instead of gene impurity. So the calculation will be same, just the formula is different. You have to explain it to someone with one of these formula. I have explained this is the most dynamic, which is the most used formula, which is the most used algorithm. So we understood it according to that. And if you want to study about entropy, you can find out a lot of examples on the internet. Okay. See, this when you have taken all the approaches, so of course your accuracy will be the most, because you are taking care of all the possible cases. You are not just studying few cases, you are studying all the cases to make a decision tree. If 100 columns are there, you are making 100 decision trees and then you are comparing them. So when you're doing everything, then obviously the final decision tree that you're going to get will be the best decision tree out that can be made on that data. So that will be accurate. Now, there are other things also which can hamper your accuracy, which I'm going to talk about. But that decision tree which is going to be created, which will be the best decision tree that can be created on the data. Yes, now, when I have got this, so we don't need to further split it, right? See here. As soon as we get at any point, take a look at it. This is a good question. At any point, you see here that you got the perfect split. That in class 0, there are 3 data points and 0 in class 1. At any point in the middle, at the start, anywhere you get such a node, then this node is never split into 2 parts. Never. You have to stop it there itself whenever you achieve the perfect purity in any step. So right, so when you're making this, what I'm saying is, suppose you're making this and you were doing it. And at this point, if you make this, you have to further split it. But suppose you got the perfect point here that you have gene impurity as 0 at this point. So you will not split it further. At this will become your leaf node. This will become your final leaf node. But if the gene impurity is not 0, it will again try to split it further than that. Okay, so wherever you get gene impurity is 0, stop. But if you don't get it 0, then you keep doing it till you get closer to 0.
Just a quick info, guys. Intellipaat offers machine learning course in collaboration with IITM Pravartak. Through this course, you can learn all the important concepts of machine learning from esteemed IIT Madras faculties and industry experts. With this course, we have already helped thousands of professionals in successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your career to new heights. So visit the course page link given below in the description and take a first step towards career growth in the field of machine learning.
So let's start with machine learning interview question. Here is your first question. It is a kind of pretty basic question, and the question is, explain machine learning, artificial intelligence and deep learning. It is very common to get confused between the three in-demand technologies, which are machine learning, artificial intelligence and deep learning. These three technologies, though a little different from one another, but are quietly interrelated. While deep learning is a subset of machine learning is a subset of artificial intelligence. Some terms and techniques may overlap in these technologies, and it is quite easy to get confused among them. So let's learn about these technologies. If I talk about machine learning involves various statistical and deep learning techniques that allows machines to use their past experiences and get better at performing specific tasks without having been to be monitored. If I talk about artificial intelligence uses numerous machine learning and deep learning techniques that enable computer systems to perform tasks using human-like intelligence with logic and rules. If I talk about deep learning, then deep learning comprises of several algorithms that enable softwares to learn from themselves and perform various business tasks, including image and speech recognition. Deep learning is possible when systems expose their multi-layered neural networks to a large volume of data. I hope so guys, you would have got a brief idea regarding machine learning, artificial intelligence and deep learning. So our next question is, what is the difference between bias and variance in machine learning? The answer to the same question is that bias is the difference between the average prediction of a model and the correct value of the model. If the biased value is high, the prediction of the model is not accurate. Hence, the bias value should be as low as possible to make the desired predictions. If I talk about the variance is a number that gives the difference of predictions over a training set and an anticipated value of another training sets. High variance may lead to large fluctuations in the output, therefore a model's output should have a low variance. If you could see in a diagram, you could see the following trade-off. So here is a bias and variance trade-off. Here is a desired result in the blue circle at the center. If we get off from the blue section, then the prediction goes on wrong. I hope so guys, you would have got a brief idea regarding the difference between bias and variance in the machine learning. Now let's move on to our next question. Our next question is, what is clustering in machine learning? If I talk about clustering is a technique which is used in unsupervised learning that involves grouping data points. The clustering algorithms can be used with a set of data points. This technique will allow you to classify all the data points into their particular groups. The data points that are thrown into the same category have similar features and properties, while the data points that belong to a different group have distinct features and properties. Statistical data analysis can be performed by this method. Let us take as some of the examples. Some of the examples can be k-means clustering. If I talk about the k-means clustering, this algorithm will be commonly used when there is a data with no specific group or category. K-means clustering allows you to find the hidden patterns in the data, which can be used to classify the data into the various groups. The variable k is used to represent the number of groups the data is divided into, and the data points are clustered using the similarity of features. Here, the centroids of the clusters are used for labeling new data. Another clustering algorithm can be mean shift clustering. If I talk about the mean shift clustering, the main aim of this algorithm will be to update the center point and the candidates to be mean and find the center points of all the groups. In mean shift clustering, unlike k-means clustering, the possible number of clusters need not to be selected as it can be automatically be discovered by the mean shift. So here are some of the examples of the clustering algorithms. I hope so guys, you would have got a brief idea regarding what is clustering in machine learning. Now let's move on and discuss our next question, which is, what is linear regression in machine learning? This is the most popular questions which is asked in the machine learning interview. Now let's discuss the answer of the same. Linear regression is a supervised machine learning algorithm. which is used to find the linear relationship between the dependent and the independent variables for predictive analysis. Here the equation can be: consider y equals to a plus b dot x, where x is the input or the independent variable, where y is the output or the dependent variable, and a is the intercept and b is the coefficient of x. You can see here the diagram with best fit shows that the data of the weight y or the dependent variable and the data of the x of the independent variable. Here the straight line shows that the best linear relationship that would help in predicting the weight of the candidates according to their height. To get this best fit line, the best values of a and b should be found. By adjusting the values of a and b, the errors in the prediction of y can be reduced. This is how the linear regression helps in finding the linear relationship and predicting the output. I hope so guys, you would have got a brief idea regarding what is linear regression in machine learning. Now let's move forward and discuss our next question. Our next question is, what is decision tree in machine learning? If I talk about the decision tree, a decision tree is used to explain a sequence of actions that must be performed to get the desired output. It is a hierarchical diagram that shows the action. This algorithm can be created for a decision tree on the basis of the set of hierarchy of actions. In the above decision tree diagram, a sequence of actions has been made for driving a vehicle with or without license. So you can see how the decision tree algorithm works in the machine learning domain. I hope so guys, you would have got a brief idea regarding what is decision tree in machine learning. Now let's move forward and discuss our next question. Our next question is, what is overfitting in machine learning? Actually, overfitting happens when a machine learning has an inadequate data set and tries to learn from it. So overfitting is inversely proportional to the amount of data. For small databases, overfitting can be bypassed by the cross-validation method. In this approach, a dataset is divided into two sections. These two sections will comprise the testing and training dataset. To train the model, the training dataset is used, and for testing of the model for new inputs, the testing dataset is used. This is how we can avoid the overfitting. I hope so guys, you would have got a brief idea regarding what is overfitting in machine learning. Now let's move forward and discuss our next question.
Let's have a quick quiz question guys, and the question is, what is the purpose of activation function in a neural network? And your options are to compute the gradient of the loss function, or to normalize the input data before feeding it to the network, or to introduce nonlinearity to the model, or to prevent overfitting by reducing the number of parameters. Please mention your answers in the comment section below.
Our next question is, what is hypothesis testing? If I talk about the hypothesis testing, machine learning allows the use of available dataset to understand a specific function that maps the input to the output in the best possible way. This problem is known as a function approximation. Here, the approximation need to be used for the unknown target function that maps all plausible observations based on a given problem in the best manner. Hypothesis in machine learning is a model that helps in approximating the target function and performing the necessary input to output mappings. The choice and configuration of algorithms allow defining the space of the plausible hypothesis that may be represented by the model. In hypothesis, the lower H is used for a specific hypothesis, where the uppercase H or the capital H is used for hypothesis space that is being searched. So this is what exactly the hypothesis testing is. I hope so guys, you would have got a fair idea regarding what exactly is hypothesis testing. Now let's move forward and discuss our next question. So our next question is, what is the difference between supervised and unsupervised learning? If I talk about the supervised learning, the algorithms of the supervised learnings used the label data to get trained. The model takes the direct feedback to confirm whether the output that is being predicted is indeed correct. Moreover, both the input data and the output data are provided to the model, and the main aim here is to train the model to predict the output upon receiving the new data. Supervised learning offers accurate results and can largely be divided into two parts, which is classification and regression. If I talk about the unsupervised learning, the algorithms of the unsupervised learning use unlabeled data for training purposes. In unsupervised learning, the models identify hidden data trends and do not take any feedback.
The unsupervised learning model is only provided with input data. Unsupervised learning's main aim is to identify hidden patterns to extract information from the unknown sets of data. It can also be classified into two parts, which is clustering and association. Unfortunately, unsupervised learnings can offer results that are comparatively less accurate. I hope so guys, you would have got a brief idea regarding what is the difference between supervised and unsupervised learning. Now let's move on and discuss our next question. So our next question is, what is Bayes' theorem? If I talk about the Bayes' theorem offers the probability of any given amount to occur using the prior knowledge. In mathematical terms, it can be defined as the true positive rate of the given sample conditions divided by the sum of the true positive rate of the said conditions and false positive rate of the entire population. Two of the most significant applications of Bayes' theorem in machine learning are Bayesian belief networks. This theorem is also the foundation behind the machine learning brand that involves naive Bayes classifier. So as you can see the formula here, P of A by B equals to P of B by A dot PA divided by PB, where P of A by B is a probability of occurring B given the evidence B has already occurred, where P of B by A is equals to probability of B occurring given the evidence A has already occurred. Here PA is a probability of A occurring and PB is a probability of B occurring. I hope so guys, you would have got the idea regarding what is Bayes' theorem. Now let's move on and discuss our next question. So our next question is, what is PCA in machine learning? If I talk about the multidimensional data, it plays an important role in the real world. Data visualization and computations become more challenging with increase in the dimension. In such scenarios, the dimension of data might have to be reduced to analyze and visualize it easily. This is done by removing irrelevant dimensions and keeping only the most relevant dimension. This is where the principal component analysis is used. The goal of the PCA is to find a fresh collection of uncorrelated dimension or orthogonal and rank them on the basis of variance, which defines the process of PCA in machine learning. I hope so guys, you would have got a brief idea regarding what is PCA in machine learning. Now let's move on and discuss our next question. Our next question is, what is SVM in machine learning? If I talk about SVM or support vector machines, it is a machine learning algorithm that is majorly used for classification. It is used on the top of the high dimensionality of the characteristic vector, which basically defines what SVM is in machine learning. I hope so guys, you would have got a fair idea what are support vector machines in machine learning. Now let's move on and discuss our next question. So our next question is, what is cross-validation in machine learning? If I talk about the cross-validation allows a system to increase the performance of a given machine learning algorithm which is fed a number of sample data from the dataset. This sampling process is done to break the dataset into smaller parts that have the same number of rows, out of which a random part is selected as a test set and rest of the parts are kept as a train sets. Cross-validation consists of the following techniques, which can be holdout method, k-fold cross-validation, stratified k-fold cross-validation, and leave p out cross-validation. I hope so guys, you would have got a fair idea regarding what is cross-validation in machine learning. Our next question is, what is entropy in machine learning? The answer to the same question is, entropy in machine learning measures the randomness in the data that needs to be processed. The more entropy in the given data, the more difficult it becomes to draw any useful conclusion from the data. For example, let us take the flipping of a coin. The result of this act is random and it does not favor heads or tails. Here, the result of any number of tosses cannot be predicted easily as there is no definite relationship between the action of flipping and the possible outcomes. I hope so guys, you would have got a brief idea regarding entropy in machine learning. Now let's move forward and discuss our next question. Our next question is, what is epoch in machine learning? If I talk about epoch in machine learning, which is basically used to indicate the count of passes in a given training dataset where the machine learning algorithm has done its job. Generally, when there is large chunk of data, it is grouped into several batches. and all these batches go through the given model, and this process is referred to as iteration. Now if the batch size comprises the complete training dataset, the count of iteration is same as that of epochs. In a case there is more than one batch, which is equals to d.e equals to I star b, which is a formula where d is a dataset and e is the number of epochs and I is the number of iterations and b is the batch size. So you can remember d.e equals to I.b, where d is a dataset, e is the number of epochs and I is the number of iteration, and where b equals to batch size. So this equation generally defines the relationship between epoch, dataset, iteration and number of batches. I hope so guys, you would have got a fair idea regarding what is epoch in machine learning. Now let's move on and discuss our next question. Our next question is, what is the variance inflation factor? The variance inflation factor is the estimate of the volume of multicollinearity in a collection of many regression variables, where VIF equals to variance of the model divided by variance of the model with single independent variable. That's it for variance inflation factor. I hope so guys, you would have got a brief idea regarding what is variation inflation factor, and it is one of the most important questions which can be asked in a machine learning interview. Now let's move on and discuss our next question. So our next question is, what is a confusion matrix? If I talk about the confusion matrix, it is used to explain model's performance and gives the summary of predictions of classification problems. It assists in identifying the uncertainty between classes. Confusion matrix gives the count of correct and incorrect values and error types according to the model, where you can see accuracy is defined as TP plus TN divided by TP plus TN plus FP plus FN. I hope so guys, you would have got a fair idea regarding what is confusion matrix. Now let's move on and discuss our next question. So our